predict such a dynamic point cloud. However, this is not executable on a robot, so we also post-train with robot actions to make it executable. Here are some roles.
Testing. Testing. Okay. All right. Welcome, everybody. Can I have the first speaker get set up while we get started? Perfect. Great. Welcome to the first session of Corl. It's my great pleasure to introduce our first speakers for Rewind. As they're getting set up, a few housekeeping rules. If you're the next speaker, please line up. We will have the talks go for 8 minutes. Then we'll do a 2-minute Q&A. And in the period of the 2-minute Q&A, the second speaker will get set up, OK? Great. we have our first presentation from Rewind. The floor is yours.
Thank you. Hi, my name is Jesse Zhang. This is Abrar Anwar, and we're here to talk about our work, Rewind, Language-Guided Rewards Teach Robot Policies Without New Demonstrations. To get an intuition of our approach, let's start with an example. So imagine you wanted to play basketball. Having done my PhD in Los Angeles, I'll use the Lakers for inspiration. You'd see amazing NBA stars like Kobe Bryant or LeBron James. A natural question to ask is, how does one get to being this good at basketball? Well, it starts with having a great coach. Many great coaches share 3 core traits. They provide detailed feedback when you make mistakes. They generalize their guidance to various basketball skills needed to play at different skill levels, whether it's in college, on the streets of Seoul, or all the way to the NBA. And they adapt their teaching style as your own play style evolves. Skilled coaches are necessary for basketball players to master every skill needed in basketball. Now, what would a skilled coach look like for robotics? In robotics, a coach, or maybe more generally, a teacher, is like a reward model. Just like a great coach, a reward model should enable our robots to learn new tasks by providing detailed feedback, even under policy execution failure, generalizing to unseen tasks so that the robots can learn new things, and of course, being robust to how the task is specified or performed by the robot. The challenge is, how can we train such models scalably so that they don't need a lot of successful and failed demonstrations for every new robot setup? Keeping in mind our 3 desiderata, we address these challenges with Rewind, rewards without new demonstrations. The goal here is to train a reward model that enables a robot policy to learn unseen tasks just from language. To do so, Rewind requires just 5 demonstrations per training task. After a human collects these language-labeled demonstrations, we then train a data-efficient reward function and offline reinforcement learning policy on the demos. We then deploy the policy to directly learn an unseen task with online RL and dense rewards coming from this language-conditioned reward model. This results in real-world learning of unseen tasks in just 1 hour.
Given only successful demos without reward labels, we use a simple and stable progress prediction objective to train the reward model. For example, in this demo of a robot picking up a cup, progress is defined simply as the current frame divided by the total number of video frames. This objective directly translates into a dense 0-to-1 scaled reward for training an RL policy. But only training on successful demos won't lead to properly rewarding failed policy rollouts, which is very important when you're trying to learn new tasks. Therefore, we introduce a video rewinding mechanism that generates failed trajectory examples from only successful demonstrations. Let's say we rewind the trajectory at the 4th frame for 2 steps. Until this 4th frame, the progress target increases, and then we split the video at the 4th frame and predict decreasing targets for the rewound video. This video now looks like a failed demo where the robot drops the cup, and we still have dense reward labels for each frame. Finally, to encourage generalization to unseen tasks and robustness to how the policy solves the task, we additionally train Rewind on a subset of the OpenX embodiment dataset. Okay, so are these things good enough to get a great reward model? Actually, no. Early on, we found that naively training an autoregressive video reward model still couldn't generalize well to out-of-distribution tasks. So we made specific architectural changes and choices to resolve this generalization challenge. Language and video inputs go through frozen Dino v2 and mini LM embedders and then get projected to a shared space for a temporally masked transformer, which outputs embeddings per frame and is finally converted into a per frame reward estimate. To handle reversible tasks like pulling and pushing, we do need positional embeddings, but giving them to every frame lets the model cheat by tracking progress directly. Following Jason Ma's generative value learning paper, we give positional embeddings only to the 1st frame to prevent cheating. In the paper, we quantitatively analyze reward function performance in great detail, but here we show a qualitative example from MetaWorld on unseen tasks. These confusion matrices show the dense reward given by each baseline reward model for videos of every unseen task on the rows and the language instruction of all unseen tasks in the columns. Because we want the correctly paired instructions in videos to have the highest reward, the goal is to have a solid diagonal blue line, and none of these baseline methods do. And now here's Rewind's confusion matrix. Rewind is able to best distinguish among different tasks and give the highest reward for the correct unseen task. And not only that, it also works for unseen tasks in the real world. Then we evaluate policy learning with Rewind on new unseen tasks in MetaWorld. Rewind policies outperform baselines in success rate across 8 unseen tasks with image-based offline to online reinforcement learning. We also perform real-world RL on a low-cost 30 Hz bimanual manipulation setup, where Rewind enables real-world learning of unseen tasks in just 1 hour of total experiment time. We compare against VLC, one of the best performing reward baselines on our reward analyses, and an offline RL pre-trained with VLC reward labels doesn't perform well on these unseen tasks, and online RL doesn't help improve that policy. While Rewind's pre-trained policy performance is similarly poor, but it greatly improves after real-world online fine-tuning.
And to qualitatively demonstrate what policy improvement after just 1 hour of Rewind training looks like, here's the pre-trained policy performing the task of putting the orange cup into this tall box. So the policy would typically either miss the grasp, like you see here, or if it grasps it, it's unable to actually bring the cup over the top of the box. Then, when we train online with Rewind, we again see early failures during training, but over time, our policy learned to slow down, to carefully grasp and lift the cup super high to guarantee making it over the box's edge. To wrap up, we'll just play this video of real-world training over an hour to show it learns this towel folding task autonomously. Here's a QR code of our paper, and I would like to mention that one of the first authors of this work, Houston Law, is applying to PhD programs this year. Now we will happily take questions. Thank you.
Great, thank you very much. For questions, please use the microphone closest to you. And can I have the next speaker get set up while we're waiting for questions? Looks like you did such an incredibly good job of explaining that nobody has any questions. That's fantastic. Thank you very much. All right, our next speaker is going to present their work on the sound of simulation. All right, take us away.
Okay, great. Good morning, everyone. My name is Ren. I'm here today to talk about the sound of simulation. This is joint work with a bunch of lovely folks at Berkeley. So to start off our journey, I'm going to present this very simple task that I think everyone in this room can do, and it's a 9 a.m. session, so I'm going to ask for some interaction from the crowd. And what we're going to do together is we're going to fill this bottle with water. And I want everyone to clap when you think that the water is close to the top. Okay, great. Now I'm going to replay that same video, and we're going to do the same task. Again, I want everyone to clap when you think the water is close. Sorry, this video refuses to. Okay, great, that worked out. So we can see that the task was significantly easier the second time around, and this simple illustration just goes to show that many of the everyday tasks that we're accustomed to actually do require a great degree of multimodal feedback. And so now imagine that we want to teach a robot to do this pouring task. How would we go about doing that? So the most natural way to obtain data for doing something like this is just to collect demonstrations via teleoperation. And so this is an example of me doing exactly that. Unfortunately, I'm not very good at teleoperation, and in general, for these kinds of more dynamic tasks, where I've now altered the environment in a way that requires me to spend more time kind of resetting my task and cleaning up the environment than I actually spent collecting demonstrations, teleoperation probably isn't going to scale very well. So as an alternative, we might consider something like simulation. So there's been an incredible breadth of work on diverse, really hyper-photorealistic simulations that have different tasks, different robots operating in vastly different environments. And so we might think about how we can leverage some of this prior work to collect some demonstrations for a pouring task now. So a traditional physics-based simulator is going to give us these really nice-looking trajectories, and then from these trajectories, we're going to try and extract a multimodal data set. So again, simulation gives us video RGB frames. We can get robot action or proprioception. And then for the audio component, we're just going to, well, it's not really clear how we're going to get audio from simulators like Mujoko or Many-Scale. But I think we can agree that audio is deeply important for our understanding of the physical world. Audio allows us to identify state changes, whether it's the sizzle of a steak on a grill, the breaking and shattering of glass. Wow, I'm so sorry, that was not supposed to be like that. The gentle creak of a door opening, the sharp crack of a soda can as it opens, the high-pitched whistle of a kettle as it comes to a boil on the stove. Audio is also really important for our spatial understanding. So everybody knows right now that they're sitting in a large auditorium hall and not an enclosed meeting room, in part because of the acoustics of this room. Audio is also really important for the identity of the spaces that we find ourselves in. A busy beach sounds very different from the quiet countryside. And finally, audio is really important for inferring material properties. So kind of the clink of porcelain glass against each other versus the soft scrub of the sponge against the plastic Tupperware, the noises that emanate from objects inform us something about their material compositions. And oftentimes, when my vision is occluded, I might use audio to tell me, for example, how full I think this tin of chips is. Even for something like locomotion, which is nominally not related to audio. The sounds that come from under my feet tell me something about the surface that I'm traversing. So the idea that we have in this paper is that instead of asking simulation to approximate real-world audio, maybe we can take all of this messy real-world audio and bring it to simulation. And specifically, we're going to take some subset of in-the-wild audiovisual data, and we're going to compress and learn a generative model on this data. So conditioning on a silent video, we can ask a diffusion model to generate the corresponding audio track. Now we have the generation machinery, and we're going to attach that to the previous traditional simulation machinery that we saw previously that gives us video as well as robot action. And now instead of conditioning on real video and generating real audio, we're just going to condition on simulation video and still generate real audio. So specifically for the task of pouring, what this is going to allow us to do is to generate really realistic audio that, for example, matches the change that we heard in the pitch of the water as kind of the water level rises in the receiving container. Okay, so now we have the generation and simulation capability, and we're going to see how we can now deploy policy in real. So it's quite simple, really. We just train a multimodal robot policy on strictly simulated data and deploy directly in the real world. And during deployment, we have real monocular RGB, but crucially, we also have real audio. And real audio during test time matches kind of the real audio that we saw during simulation. And so not only do we have the capability to generate a new modality in simulation, but now this modality actually serves as a bridge between the simulation world and the real world. And that's going to allow us to bridge the sim-to-real gap and execute zero-shot. So our quantitative evaluation is on two different benchmarks. We have an opaque set of containers where you can't actually see the liquid, and a clear set of containers where you can. And the main takeaway from this slide is that audio really matters when your vision is occluded. So this is kind of an intuitive verification that our policy is indeed multimodal and actually requires leveraging both signals equally. This is a qualitative evaluation of such a pouring episode. And the thing to listen for here is the change in the pitch of the water as the water level rises in the log. Okay, great. Sorry. There are other experiments in the paper, but in the interest of time, I'll just highlight one here, which is the robustness to environmental variation. So specifically, on the left, I'm going to show the unimodal policy, and on the right, I'm going to show the multimodal policy. Both these policies are trained strictly on simulation data. And I'm going to turn the lights off. And on top of that, I'm going to play this kind of adversarial restaurant noise in the background. And what we're going to see is that the multimodal policy terminates the pour episode correctly, whereas the unimodal vision-only policy creates another mess for me to clean up. And again, this is just another verification that our policy is indeed deeply multimodal, and this task requires us to reason over both streams. And training at scale in simulation with this generative audio really provides that degree of robustness that we want. So to wrap up, I think this work is very simple. We just present a kind of simple new paradigm for simulation. More specifically, I think that this hybrid marriage between generative models and simulators really is the next natural step in the evolution of simulation. And as simulators get better and better at capturing the physics of vision and action in the real world, instead of asking them to get that last little bit of the real world that's actually incredibly hard to simulate, things like sound or touch, maybe we can get generative models to capture them, generate them, and project them back into simulation. So with that, I'd like to conclude my talk, and I'd be happy to take any questions.
Great. We'll have the next speaker set up while we're waiting for questions. If you have a question, please approach the closest mic. If not, I have a question for you. So I imagine that as you're training your generative model on this data set of images to audio or video to audio, there's not a whole lot of robot data in there. So how do you address the distribution mismatch between your training set and then runtime inference policies?
Yeah, that's a good question. I think in practice, having a large-scale kind of generative pre-training really helps to this end. So we actually train on kind of all the audio that's available on the internet, and then we fine-tune on a very specific set of pouring kind of in the wild pouring videos. Specifically to the point that there's not enough robot data, I think we're lucky enough with this specific task that the audio dynamics actually sound very similar. And I think this is in general true, like most of the times, ignoring kind of the in the background robot noise, the audio dynamics of tasks as they're performed by robots are pretty similar to how humans would perform the equivalent tasks.
Okay, I think we have another question by the microphone. Is that right?
Thanks for the presentation and the work, great work. So my question is about the, have you tested whether or not like the policy is paying more attention to say the audio versus the vision? For example, if you are providing it misleading audio, or if you remove audio at all, would the performance be hurt? Because it says, for example, focused more on the audio and started to ignore vision with time because it was an easier signal to follow. These kind of insights I'm curious about. Thank you.
Yeah, so we do have ablations that remove audio, so the vision-only performance is worse than the multimodal performance. You can't actually entirely remove vision because you do need vision to actually navigate to the cup. So I didn't show any of the early parts in the interest of time, but you do need to grasp the cup and move it over to the appropriate receiving container. Yeah.
Great, thank you very much. All right, next up we have the presenter for real to render to real. Perfect, take us away.
Hi, my name is Justin Yu. I'd like to acknowledge my collaborators and our sponsors. We're from UC Berkeley and the Toyota Research Institute. So, are we close to having enough robot data? My advisor Ken Goldberg made a video that I think puts things into context really nicely. So here are some of the hours of teleoperated data from Google's OXE and the Pi0 training dataset. And LLMs, on the other hand, have scaled on vast oceans of data straight from the internet. And this conversion metric was proposed by Kevin Black from Physical Intelligence, where the amount of data used to train contemporary large vision language models is on the order of 100,000 years. That's the predicament we're faced with today. Meaning it will take a human that long to read or view it. But the data we need to train robots is a combination of video inputs with robot motion commands, and that data does not exist on the internet. So where do we get our robot data from? One way is, of course, teleop, where a human expert performs a task for the robot and repeats this over and over again. Really quite tedious. And another source is YouTube videos. NVIDIA Cosmos, for example, ingests this video data and tries to generate novel robot data by learning a world model. But it turns out it's pretty hard to generate 3D consistent information, and in particular, robot actions, when learning from only 2D videos. And then there's simulation. The promise of simulation is to decouple data generation from human effort and hardware. So if we just figure out how to train robots in a really good video game, maybe we can do away with the need for real data. And there's a lot of great work coming out of, for example, David Scaramouze's lab showing that simulation is indeed a powerful tool. We can train these aerial racing drones entirely in simulation and then transfer what they learned into the real world. And we see a similar story pan out for even locomotion and agile whole body control. But where is the same story for manipulation? Collision dynamics in particular is still very hard to simulate. And even simple geometry sometimes flies all over the place. So how can we scale simulation? I'm going to propose that we don't need to consider all tasks at once. Maybe we just incrementally get there. And of all the manipulation tasks, many are actually quasi-static, meaning they primarily depend on position and not on forces. And many of these tasks are also short horizon, and this turns out to be a large subset of manipulation tasks. And now let's consider simulation. Here's a GUI showing a state-of-the-art simulator for robots, and there are many sliders and tabs you can see on the side, and in particular one deals with physics. And in the middle you have this really nice rendering of a robot performing some task. And up to now I've talked about simulation as if it were a single concept, but it's actually made up of many, many complex parts, one of which is rendering, which is the subset of simulation that makes things look real and doesn't care about perfect collision or exact forces. And it turns out that rendering is all that is needed for quasi-static manipulation. And that is precisely why we are called real to render to real. And recent work has shown creative ways to scale up robot data sets. Some take teleoperated data and port the trajectory and assets into simulation, and others use augmented reality or in-paint robot embodiments into human hand demonstrations. And many other works are thinking along the same lines to scale data sets. And this one on the left was presented just yesterday for the workshops, and it uses a VR headset for tracking and augmenting data sets with human hand demos. And on the one on the right uses Gaussian splatting and trajectory optimization to generate new collision-free paths and realistic novel views. And so here's our pipeline. First, we get our real objects ready for rendering. And you don't need a real robot for this. You just pull out your phone and you start scanning. And then from this scan, we generate a 3D Gaussian splat and segment them using group anything with radiance fields. And then we take a second video of a human demonstrating this task. And with these two together, we can track the object motion using a technique called 4D differentiable part modeling, which was first introduced in the paper Robot See, Robot Do. And then we find the optimal grasp axis for the robot by meshifying our geometry and sampling for antipodal grasp axes. And we choose the highest scoring grasp based on human hand pose estimation. And now for the rendering part. Remember, we only use the position elements and we ignore the dynamics. So using this track and grasp that we just computed, we then figure out what the join angles need to be. And then render from different camera views. And of course, a massive benefit of having this render is domain randomization. And along the same lines, we can also interpolate our trajectories. And you can think of this like bending and twisting your original trajectory a bit to turn one into many. We can render all of this in parallel and on different embodiments and use this data to train our models. For our experiments, we trained vanilla diffusion policy from scratch, and fine-tune pi0 fast. So what happens when we test these models out in real? This is showing a fine-tuned pi0 fast policy using exclusively rendered demonstrations. And rendering can also be done on a different embodiment, in this case, the Franca Panda. And we even tried the same method on more tasks. These are all deliberately chosen to highlight the diverse quasi-static manipulation scenarios that you will find in the real world. And we find that with a single GPU, we can render 1,000 demonstrations in a little just over half an hour. And the models that it trains matches the performance of that trained on teleoperated data collected in 1.5 hours. That is 3 times as long. And so just as a thought experiment, imagine scaling the number of GPUs you have versus scaling human teleoperators and robots. And so getting into some of the limitations of this work and for future work, it should go without saying by now that our method has no dynamics. But for more dynamic tasks, that simply won't hold. And we retarget the human hand to parallel jaw grippers, where there's still an embodiment gap issue. But parallel jaw grippers are not the only embodiments out there. And finally, while our rendering produces visually realistic data, there is still a visual gap between our synthetic scenes and the real world. So making this gap even smaller than we have here is a very exciting prospect. Maybe, for now, for the class of models that we train today, looking as close as possible to the matrix is enough to get us a decent part of the way there. And with that, I'd like to thank you. It's been a pleasure. Please visit our website where you'll find more videos and release code. And thank you, and I'll take any questions.
Great. We'll take questions. Next speaker, please set up. So I have one for you. So considering tasks that could be quasi-static, such as like maybe taking a rubber band and putting it across 2 pegs or something, how would you think about sort of trying to address that problem with your formulation? Where that maybe is a bit more of a consideration towards forces and it's not just sort of very visual geometric.
Right, so I can imagine a framework that I don't think these 2 ideas are at odds with each other, like including trajectories from real demonstrations and like physics computation engines. I can imagine a framework that combines the best of both worlds.
Cool, great, thank you. Other questions? Great, thank you. All right, our next speaker is going to present their work on steering your diffusion policy.
Hi, everyone. My name is Andrew Wagenmaker. I'm a postdoc at UC Berkeley. This is joint work with some great collaborators, Mitsuhiku, Yunchu, Sahong, Walid, Anusha, Abhishek, and Sergey. So the question we want to understand in this paper is how can we go from a diffusion policy that behaves like this, that is, doing reasonable things, but not actually solving the task in the way that we want, to a diffusion policy that behaves like this, that actually solves the task that we want it to solve, and it solves it effectively and efficiently. And furthermore, how can we do this with simply online training and real-world deployments? So to answer this question, we're going to take a step back and just think about what a diffusion policy actually is. So let's say you're given some demonstration data set, and I train a diffusion policy using standard BC on this data set. Now, what I've learned in this diffusion policy is essentially a mapping that takes some random noise and feeds it through the diffusion policy, which then transforms that into some action that is something like a demonstrator action. So at some high level, we can think about a diffusion policy as simply a mapping that transforms random noise to demonstrator actions. Now, in standard diffusion policy deployment, what do? Well, typically, I just sample noise from a standard Gaussian. I feed that through my diffusion policy. It gives me an action. I play that action on my robot, and it does something. Maybe good, maybe bad. Maybe in the next deployment, I sample some other noise. I feed it through my diffusion policy, get another action that produces another sort of behavior on my robot. Now, if we think about standard diffusion policy deployment, the story sort of ends here. I just sample Gaussian noise. It produces whatever noise it produces. It gives me some action. I play that. But this is kind of missing something that could be potentially very useful here, which is that some noise might be mapped to better actions than other noise. And so if I just sample from a standard Gaussian, I don't sort of exploit this fact. But if we can instead restrict our noise so we only sample the good noise, then we can perhaps improve the policy significantly. And that's the basic idea behind the approach we're proposing, which we call DSRL, diffusion steering via reinforcement learning. So instead of sampling noise from a standard Gaussian, I'll sample noise from some policy that I'm learning. Okay, so I sample noise, it produces an action through my diffusion policy. I observe what happens when I play that action, and then I update this noise policy via RL training. Maybe I sample some other noise, I get another action, and now this maybe does a better behavior, and I update my noise policy again through RL training. So what I've effectively done here is I've transformed the action space of my problem, at least from the perspective of the RL agent, from being the original action space to being simply the noise space of the diffusion policy. Now, when I run RL over this noise space policy, what I get is a policy that in the end sort of locks in to what the right action is, the action that sort of will accomplish the task in the way I want. So what is this bias? Well, a few things. For one, it enables efficient and expressive improvement of diffusion policies, and I'll demonstrate this in a bit. For another, it doesn't require fine-tuning the diffusion policy's weights at all. The only thing I'm training here is this noise space policy pi-w, and typically we just instantiate this as a small MLP. Furthermore, it avoids issues like backpropagation through time, which has been a challenge that people have encountered when they're trying to apply RL to diffusion policies. Finally, while you can instantiate this with almost actually any RL algorithm, we propose a sort of instantiation in particular that allows you to learn both from online and offline data. So you can improve your diffusion policy by learning the steering policy either in online rollouts or sort of from some offline data you have. Okay, so I just want to show you some results on what this gets us. So we'll just first look at some benchmark sim results. So on RoboMimic, which is sort of online RL, or doing online fine-tuning, we get state-of-the-art performance for fine-tuning diffusion policies. But also on OGBench, which is an offline RL benchmark, we can actually match the state-of-the-art using sort of this offline version of diffusion steering. So we have this unified algorithm that does sort of offline and online learning efficiently. But I think what is more exciting than this is sort of the real-world results we get. So what I'm showing here is sort of some videos of diffusion policy that we trained, and this is before DSRL performance. Okay, and so we're applying this really across scales. On the left, we have a diffusion policy we trained on 10 human demonstrations. In the middle is a diffusion policy trained on the bridge data set, so it's something like 60K demonstrations. And on the right is OpenVLA, or Pi0, sorry, which is a sort of state-of-the-art VLA model. We can apply DSRL to all of these, and we can significantly improve the performance of all of them. In general, we see something like you can take a policy that gets like less than 30% performance, you can boost this to greater than 90% performance, and depending on the setting and the task, this can take anywhere from 30 minutes to an hour and a half of online training. So really across diffusion policies, from VLAs to single task diffusion policies, you can apply this to efficiently improve your policy in the real world. Okay, so just to close, I want to sort of give you some sense of like what DSRL training looks like and maybe why this is learning efficiently. So I'm going to just show you a full DSRL training run. So on the left is rollouts from the initial diffusion policy. The task here is just to pick up the mushroom and put it on the cloth. And so we see this policy is doing reasonable things, but it succeeds less than half the time. Now on the right is DSRL training. So I'm starting from scratch, I'm just showing you the full run. And what we see, I guess, just initially is that the actions that are being played here are very reasonable in some sense. They look like actions that a human demonstrator might produce. And the reason for that is even though I'm running RL, right now I'm training this noise space policy, the diffusion policy has learned to map any noise to sort of a demonstrator-like action. So that when I'm doing this RL training, rather than getting some sort of random-like behavior, I'm getting very structured, coherent, human-like behavior. And in fact, if we plot the trajectories that are produced here and compare these to what you get if you were to run standard RL, you get something very different. We're getting these highly structured trajectories that are enabling very efficient learning, very focused online data collection. And we compare this to sort of standard RL training trajectories like this, you get this much more diverse, random sort of behavior. Okay, and so we see actually that already we're about 20 trajectories in, 20 episodes in, but already we're seeing some noticeable improvement of the diffusion policy. And in fact, if we played this out, for the next like 15 trajectories, it's going to succeed every time. And so by exploiting sort of exploiting this mapping that the diffusion policy has learned from any noise to reasonable actions, we can achieve highly sample efficient RL in real world deployments really across diffusion policy settings. Yeah, that's what I have. Happy to take any questions.
Great, we have time for questions? Yes, please.
So I was wondering if you'd talk a little bit about how you parameterize a change in the Gaussian. Because one thing that I'm kind of curious about is, IID Gaussian draw in high dimensions looks like basically close to a draw from the hypersphere, right? And so if you change that, you get out of the domain where the diffusion model works well, I would imagine, but it seems like you got around that.
Yeah, so how we actually do this in practice is you just clip it. Like we basically parameterize this like a noise action space as just a box. So we just clip it somewhere not too far from the origin at like say 1.5 or something. But your point about it being like a hypersphere is actually a good point. The sort of like more correct way to do this, which we did try and it also works, is rather than enforcing a hard constraint, you enforce some sort of like L2 constraint on the actions such that you're like encourage them to be close to the origin. And then that encourages it to sample something like from a hypersphere.
Thanks.
Please.
Thank you for the great talk. It seems that there's an implicit assumption that the correct action is indeed in the support set of the action generation distribution. Can you comment on what happens if the correct action is like completely missed by the multimodal action distribution?
Yeah, so what we find in practice is that as long as your diffusion policy gets like greater than 0% success, it almost always works. Like you can almost always get it up to like close to 100% success. So I think in practice, what you're saying is certainly correct. Like if you just don't have an action in support, you won't be able to play that action. But in practice, it seems to actually not be as much of an issue as you might expect.
Thank you.
Yeah, please.
Yeah, interesting work. Yeah, I guess related to that, so the way you were visualizing the results is that you might lock onto certain modes of the data distribution rather than others. So do you find that you're losing the ability to capture the full multimodal nature of the data distribution?
So in some sense, I guess so the diffusion policy itself, we don't fine tune. So in particular, like the diffusion policy still maintains all the multimodality you want. Now, the learned policy you get, you sort of do lock onto a single mode, but I would argue that's actually the desired behavior because you want to sort of maybe lock in on like the right mode or the successful mode. And so in sort of these RL settings where when you're trying to maximize a single reward function, like that is sort of what you kind of want to do. But the multimodality still exists in the diffusion policy.
Thanks.
Great. I don't see any other questions. Thank you. Next up, we have the presenter for streaming flow policy. Take us away.
Hi everyone, I'm Sid, and I'm presenting streaming flow policy, simplifying diffusion and flow matching policies by treating action trajectories as flow trajectories. And this is work with some amazing co-authors, Sunshine, Shaolin, Nick, Leslie, and Tomas. So let's begin. So we all know that like diffusion policy and flow matching policy have revolutionized imitation learning for robotics. And the way they work is that they take a history of sensor observations as input and output a multimodal distribution over action trajectories. They define a diffusion process in trajectory space. So they start by sampling noise from the standard Gaussian, and they perform a diffusion or flow process to gradually denoise this trajectory. Importantly, all intermediate action trajectories are thrown away, and the robot must wait for the diffusion or flow process to finish before executing any actions. So can we simplify this framework and maybe make the policy faster? So in this work, we propose a flow matching algorithm in the space of single actions rather than the space of action trajectories. So we first sample a narrow Gaussian centered on the most recently executed action and define a flow process that treats the action trajectory as the flow trajectory. The execution time of the action trajectory is now the same as the flow progression time. This allows actions to be streamed to the robot during the flow process. And so the robot can asynchronously execute the action chunk while it is being generated. And this can reduce latency in the policy. But how do we construct such a streaming flow policy? The idea is to learn a velocity field that takes as input a history of observations, a time between 0 and 1, and an action. and it outputs the time derivative of the action trajectory. We first sample an action at t equals 0 from a narrow Gaussian that's centered at the most recently executed action, and then we integrate the velocity field to produce an action trajectory. And this sequential integration is what allows us to stream actions during the flow process. But how do we learn this velocity field? The answer is flow matching. Here's a toy example of a data set with just 2 demonstrations in blue and red. And the x-axis contains one-dimensional actions, and the y-axis shows execution time, which is also in this case equal to the flow progression time. So given a trajectory sampled from the training set, we analytically construct a flow around this trajectory. And this constructed flow has 2 components. The first is the initial distribution at t equals 0, which we define to be a narrow Gaussian centered at the first action in the demonstration. And the second is we construct a velocity field. At any a comma t, the velocity has 2 components. The first is the time derivative of the action trajectory, which basically moves us along the trajectory. The second is a stabilizing term that guides us back towards the trajectory. And such stabilization is known to reduce distribution shift and improve imitation learning guarantees. So at any given time t, the marginal distribution induced by this flow also happens to be a narrow Gaussian centered at the trajectory. So how do we train this velocity field? We sample a demonstration trajectory one at a time from the training set. We sample time between 0 and 1, and we sample an action from the flow that's constructed around this trajectory. And we just minimize the L2 loss between the predicted velocity and the constructed velocity. And this is called the conditional flow matching loss. And after minimizing this loss, we obtain this velocity field. And these are trajectories sampled from the learned velocity field. The flow matching loss guarantees that at every time t, the marginal distributions over actions matches the training data. And so the main takeaway is that this method is able to represent multimodal trajectory distributions while also generating actions in a streaming fashion. So here are some results on the push-T benchmark dataset, where our method performs comparably to diffusion policy in terms of performance, but it can be significantly faster. And just like diffusion policy, streaming flow policy can sample multimodal behaviors that are present in the training set. And we perform experiments on other benchmark data sets like RoboMimic, where we kind of obtain the same conclusions. So here's our method in action with a real robot arm picking up an apple while trying to avoid clutter. Streaming flow policy tends to be smoother, faster, and more reactive than diffusion policy. Here's another task, trying to rotate a block to a goal orientation, where streaming flow policy just tends to be much faster. So the question you might be asking is there a price that you have to pay for being able to both represent multimodal trajectories and also able to stream actions? And the price that you have to pay is that you can only guarantee to match the marginal action distributions at each time step, but not the joint distribution. So here's an example of 2 demonstrations that intersect in the middle. And here's the learned streaming flow policy. And the samples from the policy looks like those 3s that you see on the bottom right, even though the demonstrations kind of look like those S's. And that's because streaming flow policy can mix and match pieces from one demonstration with pieces from another demonstration. And this kind of compositionality can be an issue in certain tasks and applications, but it can only compose these trajectories so long as it matches the marginal action distributions at each time step. That is guaranteed. And this type of compositionality, I would argue, is usually valid for most manipulation tasks that are reasonably slow and quasi-static. But my main message is that the original flow matching framework is so flexible that we can be very creative about how we apply it to action sequences. For example, this is another variant of streaming flow policy, where instead of adding noise to the initial action, we can decouple it into a separate variable that is responsible for all the stochasticity in the policy and is sampled from normal 0, 1. And the game is, as long as you can construct a conditional flow where the actions kind of closely follow the demonstration, the flow matching theorem ensures that you will learn the right multimodal distribution while also being able to stream actions. So streaming flow policy opens up a huge design space, and I think we have only scratched the surface. And on that note, thank you all for listening. If you're interested, please visit us at the poster session this afternoon, and I'm happy to take questions.
Great, thank you. Questions?
Yeah, a quick question.
Yeah.
It does look like the final model you have ends up being like basically an autoregressive model in velocity action space. Is that fair? And is this just that you're using a sampling method instead of just a closed form likelihood-based method to?
Right, so it is an autorecursive policy, which is why you're able to kind of stream these actions. But it kind of combines this framework of flow matching that also kind of makes sure that you are learning multimodal trajectory distributions while being autoregressive. The big lesson from diffusion policy is that imitation learning data is inherently multimodal. And if you are not careful about the kind of models you use to learn this data, it can kind of end up averaging trajectories. And so this is a framework that is both autoregressive, but also handles this multimodality.
Yep, I think we have another question back there, yeah? Yeah.
I think, first, thank you for the nice talk. And I think my question is kind of similar to the previous question. It feels like to me that you are learning a one-step action, which can be interpreted as a delta action or the velocity field. But if my understanding is correct, that you don't use the action chunking. Is it correct or not?
Yeah, so that's a good question. It kind of feels like it's a one-step policy, the delta actions, but it's actually the entire chunk that we generate sequentially. That is an action chunk in the sense that it's not running closed loop. So you're taking observations at the initial time step, but you're using the same observations throughout the chunk generation. So that's what makes it an action chunking policy. And we know that being able to generate these kind of action chunks in an open loop fashion and run it is kind of an important part of kind of diffusion flow matching policy. Okay. So it's kind of somewhat feels like in between, but I would squarely put it as an action chunking policy.
I may need to look at it more carefully, yeah. Okay.
Yeah, great, thank you.
Thank you.
Next up, we have the presenters for SAIL. Take us away.
Thank you. Hello, everyone. My name is Nadun Ranawakara-Chige.
And my name is Zhenyang Chen.
And we are proud to present SAIL, Faster Than Demonstration Execution of Imitation Learning Policies. Okay, so recent advances in imitation learning have enabled robots to perform many challenging and impressive tasks. However, when we look closer at these cool demos, there is still one thing that is not quite satisfying. Many of these videos are sped up, perhaps even 8 times, and this doesn't work in the real world or for industry where we want robots to be fast and efficient. So, can we execute visual motor policies faster than demonstrations? To answer this question, we propose SAIL, or Speed Adaptation for Imitation Learning, a full-stack robot learning framework. On the left, we have a human teleoperating a robot to train a policy via imitation learning. During deployment, such policies will at best match the same speed as the demonstrator. SAIL, however, goes beyond this and is able to perform the task at twice or even 3 times the speed of the demo. Additionally, SAIL reacts much faster to perturbations in the environment and is also able to recover quickly from failures, resulting in greater efficiency. Now, is speeding up as simple as executing the robot control commands at a higher frequency? To understand why this is not the case, let's do a quick review of the visual motor policy pipeline at deployment. At the bottom, we have a robot that acts in an environment to complete a task. To generate actions for the robot to execute, we have cameras that capture the state of the environment with some sensing delay and pass this data to a model, which after another delay for inference, generates a trajectory of actions that are sent to the robot controller to track. And the cycle continues. During execution, each of these components can introduce distribution shift, and this problem is more severe when speeding up, leading to policy failures. The first source of distribution shift is latency. This latency comes from observation and inference delays. If we naively speed up execution, the robot will pause due to these delays, resulting in jerky movements that can cause distribution shift. One way to address this is through asynchronous execution, where we start inference while the previous trajectory is being executed. However, when speeding up, the execution time of our trajectory decreases, making the robot run out of actions. Next, with multimodal policies, the model may switch between strategies during receding horizon execution, causing divergent predictions. Here, we have an initial trajectory generated by a model, and we start tracking this. During execution, at the next time step, we take a new observation and run inference again, while continuing execution of the initial trajectory. However, the second predicted trajectory diverges from the first one at the time of inference, which causes unstable movements when we switch over to this new prediction, and we can see this effect in this video. Another key issue is the change of in the robot controller's dynamics at higher speeds. For demonstrations, we typically use a low-gain compliant controller, which makes teleoperation easier and smooths out noise. The commands given by the teleoperator are here denoted as commanded poses. Due to the low-gain controller, the robot doesn't reach these poses exactly, but maintains some tracking error as shown by the blue line. Now, when you run the policy at the same speed as the demonstration, this isn't an issue and you're able to maintain the same motion profile. However, when you start speeding up, the low-gain controller can no longer track with high enough fidelity, resulting in a different motion profile, and we can see this effect in this video. Since each of these components are tightly coupled, this distribution shift can compound, causing more frequent and severe failures when you speed up the execution of your policy.
To address these challenges, we propose speed adaptation for imitation learning, CEL. CEL is designed based on both policy level and systems level consideration. On the policy level, we adopt diffusion policy as our base policy and propose error adaptive guidance to generate smoother reference trajectory. EAG encourages consistency by conditioning the prediction of next action sequence on the tail of previously planned action sequence using classifier-free guidance. It mitigates the divergence and encourages temporal smoothness between predictions. However, when larger tracking error occurs between reference action and the robot state, naively applying CFG might hurt the performance. To this end, we propose EAG and dynamically adjust guidance weight and disable the guidance when tracking is inaccurate. With EAG, we are able to generate smoother reference trajectory for the robot to check. Executing all parts of a manipulation task at maximum speed can compromise the success. For example, speeding up during interaction that require precise motion like grasping or alignment could be harmful. Adaptive speed modulation automatically identifies different motion stages and dynamically adjusts the speed up factor based on the real-time context. This allows the robot to speed up and slow down as needed. With modulated action trajectory and speed modulation, we design action scheduling module to enable asynchronous execution according to the action timestamp and minimize the effect of system latency. Then, to mitigate the controller behavior shift, we train the policy with rich pose and check it with high-gain controller instead of the default compliant low-gain controller. These design choices can give us less tracking error and high speed. With all these components, CEL mitigates distribution shift across a whole control loop and enable faster than demonstration execution. We evaluate our main throughput in our main experiment, which reflects the numbers of successful rollouts in unit time. While the baseline achieved no significant improvement when speeding up execution, Cell achieved up to 3 times higher throughput when speeding up, which indicates its potential in real-world scenarios, especially like production environment, where efficiency matters a lot. We conduct extensive experiments in real world on challenging tasks, for example, like carb stacking. And also, it can perform tasks, accelerate tasks involving articulate objects, for example, closing the door for the oven. Moreover, it manipulates a soft object and achieves 2 times speed up like close folding. And we are able to handle and accelerate the dynamic bimanual task. In the future, we aim to apply Cell to more capable industrial robots and further unleash the potential of imitation learning in the real world. With that, we would like to thank all of our co-authors, and please visit our website for more details. We are happy to take any question here and the poster session. Thank you so much.
Great, thank you. Time for questions. So I have a question for you guys. I can imagine for kinematic tasks where like speeding up or slowing down might not create that much distribution mismatch, but if I have physical interactions where force transmission is kind of an issue here. Now, if I do go faster, if I do go slower, then you do actually create a distribution shift that your model hasn't seen before. So when the forces matter, how do you imagine kind of growing sail into those kinds of regimes?
Right. Yeah, thank you for the question. So yeah, that's definitely a valid concern and perhaps one of our limitations. But with the development of better and more high fidelity robot controllers, we believe that we could perhaps address that, as well as collecting more on-policy data during rollouts to deal with the changes in dynamics when you speed up.
Yeah, I think what I was trying to hint at is, so if I'm pushing something, I might apply less force in the demonstrations than I would during execution if I run sail. If I run sail, then now I apply a much larger force, and that might materially impact the task itself. So how do I think about reformulating sail to take into consideration variations in dynamics that I did not see in my training set?
Right, so part of that is with the, part of the solution is that we use our reached poses, so we don't want to push too far into objects, perhaps, when you speed up, right? So instead of using the actual commanded poses from the teleoperator, which may cause us to transmit more force than we wanted to, we're able to more closely match the distribution states during the demos by using the reach poses instead.
Great, thank you.
Yeah. Also, I think another thing about that is I think what you want to mention is more like the unknown object dynamics that we want to solve. So actually that would be our extension in the future work. Yeah, because in that part we also need to estimate some different things, for example, the dynamics on the fly, so we can incorporate that to the policy better. But here we focus more on the kinematics part and then to accelerate the execution during the runtime. Yeah, thanks so much.
Great, thank you. All right, next up we have the presenter for versatile local manipulation. The floor is yours.
Is it showing? Is it showing?
Maybe guys can go. We're right on schedule. Thank you. How's it going? Yeah, nice to see you.
Good to see you.
Yeah. Don't worry, he'll figure it out. He's smart.
Still doesn't work.
right, we're going to do a little shuffle. Can I have the author of XSIM come up, and then we're going to revisit versatile locomotion once we resolve the technical issues. We're just going to flip these two around, okay? This should be good. All right, next up we have the presenters for XSIM. Let's hope you have more luck. Huzzah! Congratulations, this is good.
Okay. Hi, everyone. I'm Kushal.
And I'm Pratwish.
And today we'll present XSIM, cross-embodiment learning via real to sim to real. Teleoperation is the dominant method to train robots today. But does it actually scale? The good thing is that it provides us real-world robot action data. But as seen in these videos, oftentimes this data collection is time-consuming and difficult to collect. On the other hand, human videos are abundant, cheap, and easy to collect, making data collection much more scalable. However, there's a catch. They lack robot actions required to actually train robot policies. A common solution is to just take human hand motion as input to your retargeting network and output robot actions. But this assumes that humans move like robots. Without this assumption, the robot often struggles to imitate the retargeted human actions. For example, the human's grasping motion here is not kinematically possible for the robot to achieve. In this task, the human picks up the mug with a frontal grasp, whereas the robot finds it more comfortable to pick up the mug with a top-down grasp. Even when performing the same task, robots often require different hand actions than humans. Still, it is possible for the robot to move the mug through the same trajectory as the human, resulting in the same object motion across both embodiments.
So the key inside of our work is instead to learn robot actions that match object motion rather than hand actions. So towards this goal, we propose XSIM, a real-to-sim-to-real approach to learn from human videos. First, our real-to-sim pipeline tracks object motion from the human video. Then we learn robot actions via RL using object-centric rewards. Finally, our sim-to-real pipeline deploys image-based policies in the real world. So our real-to-sim pipeline has two major components. First, we construct a digital twin of the real world in simulation using Gaussian splatting. Then we track object poses from the human demonstration using foundation pose. So within the simulator, the robot learns to complete the task via RL. We use an object-centric reward function that encourages the robot policy to match object motion from the human video. However, the RL policy is actually trained with privileged state information. So to transfer to the real world, we roll out the RL policy to collect varied RGB demonstrations. And finally, we can use this to distill into an image-based diffusion policy. But can a policy trained only in simulation transfer to the real world? Well, for simple pick-and-place tasks, we actually find that the transfer to the real world is highly successful, as shown in this example. But we find that on more challenging tasks, there's actually a pretty large gap between sim and real performance. The policy has slight imprecisions in the real world, leading to misaligned insertions in this example. So to investigate this mismatch, we replay the same actions across both simulation and the real world. While the environment states are matched when you do this, we actually find that the simulation and real world induce different image embeddings, as shown on this TSNE plot. And we propose a simple solution to close this gap. We choose to minimize the distance between image embeddings corresponding to the same environment states across sim and real. After this alignment procedure, the image embeddings corresponding to the same exact environment states are now much closer, as shown in the updated plot, and we find that minimizing the visual sim to real gap helps reduce the performance mismatch across domains. So while the policy struggled to place this mug into the holder earlier, we see improved performance after this alignment. And quantitatively, there's a pretty significant increase in task success rate.
Next, we move on to the experimental evaluation of our work. First, let's go back to hand retargeting and see how XM fares against it. While directly retargeting the frontal grass motion here is not kinematically feasible for the robot, XM overcomes this issue. It learns robot-feasible strategies that match object motion from the human video instead of the hand motion. Quantitatively, we find that hand retargeting is not bad for the simpler tasks in our setup, but starts to completely break down as the tasks get more and more complex. XM improves task performance across the board, especially on the harder tasks, where learning strategies different from the human is critical. We see further improvements by doing our alignment procedure, which kind of makes the image embeddings across simulation and real more aligned. We went through all this effort to learn robot policies from human videos, but the key question still remains. How does this XM measure up against plain old robot teleoperation? First, let's look at the collected demonstrations themselves. We see that human videos are much easier and faster to collect, allowing scalable data collection. This allows XM to match behavior cloning task success rate while reducing data collection time by 10x compared to teleoperation. Still, XM has its limitations compared to teleoperation. It assumes match physics between sim and real, is limited to rigid object manipulation, and requires human effort to scan the environment. We are actively working on these limitations in future work. To summarize, we propose XM, a method to learn from human videos via real to sim to real. Thank you for listening to our presentation. You can access all our code and our real to sim assets using this QR code. We would be happy to take any questions from the audience now.
Great job. Thank you. We have time for questions. Amazing. You did such a fantastic job. Good. Great. So a quick note that we're going to do demo speed up next, and then we're going to go back to the previous presentation we couldn't pull up. Hopefully it'll work next time. All right. Can I have the author of demo speed up, please? Thank you.
Hi, I'm Zhenrong from Tsinghua Embody AI Lab, and I'm glad to present Demo Speed Up, Accelerating Visual Model Policies via Entropy-Guided Demonstration Acceleration. We have seen tremendous progress for robotic manipulation policies in the past 2 or 3 years. By manual, dexterous hands, and humanoids, new fancy demos coming up almost every day. Despite the progress, it is also a fact that the execution speed of most learning-based policies is still far from satisfying. As a result, for visually pleasing smooth motions, many demo videos are accelerated by 5x or even 8x. Otherwise, they will just look like slow motions. However, to make robots work like humans, we believe fast human speed execution is very important, just like the previous presented cell. We provide 2 concrete examples here. The first is when we want the robot to work in the factory, it has to keep up with the pace of the assembly line to maximize productivity. The second is when we want the robot to work in time-sensitive scenarios. For example, to defuse the threat of a time bomb, the robot has to execute quickly enough to complete a task. But different from cell, we lay emphasis on the data side. We assume in this work that slow demonstrations are the primary cause for slow execution of behavior cloning policies. So a natural question will be, can we train us humans to become more skillful data collectors so that we can produce faster demonstrations? Unfortunately, under the current development of hardware, we believe the answer is no. Empirically, we observe that even skillful data collectors with over 100 hours of experience could not teleoperate the robot arms as fluently as using their own arms or hands. The major obstacle to achieving faster motions in both VR and kinematics teaching teleoperation are the lack of full directional, non-occluded view of the 3D thing, as well as the absence of tactile feedback to confirm the contact status between the robot and the manipulated objects. So, the major challenge is, can we train fast visual model policies from slow demonstrations? Our solution is to accelerate the source demonstrations. But how? Our key insight here is to note that not all the frames in a demonstration trajectory are as equally important for a task success. For example, if we want to pick up pen, the last inch motion has to be very precise and therefore should not be touched. By contrast, how to approach the pen is quite casual because there are multiple valid paths and either way is okay. Since those casual sections won't immediately determine task successes or failures, they can be more safely accelerated. Note that both casual and precise are very vague concepts. We can, of course, ask the teleoperator to label these sections, but this kind of labeling are quite subjective and also time and effort consuming. So we wonder, can we label the casual and precise sections in a more objective and automatic manner? Our solution is to introduce the concept of action entropy, which measures how uncertain a policy trained from the source dataset will take a specific action. According to this definition, frames with lower action entropy call for more persistent policy behaviors, which indicate the demands for higher precision. By contrast, frames with lower action entropy indicate there are multiple possible ways in the dataset, which correspond to more casual sections. Now, we have 2 remaining questions: how to calculate action entropy and how to accelerate the source demonstration using the estimated action entropy. For action entropy calculation, we take the following 3 steps. So step 1, we train a proxy policy on the original speed source demonstration. The proxy policy can be any policy based on generative model, such as popular ACT or diffusion policy. Note that the proxy policy is not used for actual deployment, but only used for the purpose of entropy estimation. Step 2, for each frame in the source dataset, we generate multiple action samples given the previous observations using the proxy policy. Due to the randomness of generated policies, the generated samples should be different from each other. Step 3, we assume these generated samples follow a Gaussian distribution and perform a Gaussian kernel density estimation on the action samples to calculate the probability function and the action entropy value. Given the entropy estimation, now we are ready for demonstration acceleration. For entropy-guided acceleration, we take the following 4 steps. Step 1, we perform some regular entropy pre-processing, mainly to exclude outliers and perform temporal smoothing. Step 2, we do density-based clustering, dividing source trajectory into alternating high entropy casual segments and low entropy precise segments. Step 3, we accelerate the source demonstration via piecewise downsampling. That is, we downsample the casual segments by n times, thus making it run faster by n times. For the precise segments, we just keep them in their original speed. Step 4, if we naively downsample the source trajectory, we will severely hurt the diversity of the visited states and therefore hurt the policy performance. As a remedy, we copy the casual segments by n times and perform downsampling in a non-overlapping manner to ensure the diversity of visited states can be maintained after downsampling. We do simulated experiments on the Aloha and Beijing benchmarks covering bimanual, mobile, and long horizon manipulation tasks with high precision requirements. We adopt 2 different kinds of generative policies, VAE-based ACT and diffusion-based diffusion policy for all the experiments. We compare demo speedup with 2 baselines, the policies trained on the original speed source dataset and the policy trained on the naively accelerated dataset through downsampling by 2 times. The results show that the naively accelerated baseline could speed up the policy execution, but at the cost of degraded success rates. By contrast, demo speedup could accelerate by an even higher rate while maintaining and even slightly boosting the task completion success rate. We attribute the improved success rate to the policy's reduced decision horizon, a beneficial side effect caused by downsampling. In the real world, we designed 5 challenging bimanual manipulation tasks and find demo speedup once again reduced the execution speed by approximately 2 times, while also boosting the task completion success rates in many tasks. If you're interested, don't forget to visit our website, demospeedup.github.io. Thanks for your attention.
Jens.
Or not versus doing it proportional to the distribution.
Can you say it again? Sorry, your mic was off in the first.
So the question is, why is it binary, either casual or not, versus scaling it with the distribution?
You mean how to distinguish casual and precise segments?
No, I mean, rather than saying you speed up the casual segments by 4 times, you could say depending on how broad the distribution is, the broader is, the more you speed it up.
Oh, okay. So, to downsample the casual segments will definitely change the distribution of the source demonstration. But since we will train a new accelerated policy using the accelerated demonstration, so we found that this kind of distribution shift will not affect the final performance of the accelerated policy.
Okay, thanks.
Yes, thank you.
2 more questions, one in the middle and one to the left. Again. Oh, can you try? Is it working? It's not on?
Thanks, Nima. I'm curious. I really like this entropy model. And have you been thinking about other places this could be used? For example, to selectively get more demonstrations or recovery behaviors right around those high entropy zones?
You mean by use the entropy model for to achieve better recovery capability?
Exactly.
Okay. We have not tried that, but yeah, I think so. From my intuition, if we still have the classification of casual and precise segments, I think when the policy gets stuck into some failures, it should recover to a casual segment status rather than a precise status. So yeah, maybe it will be an indicator, and we will maybe look into that later. Thank you.
I think this one is on, actually. So. Yeah, so I was wondering if you could help me understand a little why you had to go all the way to kind of the entropy estimation rather than using a simpler proxy like variance.
Yeah, so actually we take multiple samples from the proxy policy, and we use these discrete samples to we have an assumption that these samples follow a Gaussian distribution, and we use these we estimate the probability function of the Gaussian distribution and then calculate the entropy. So so we do this because we take discrete samples from the proxy policy, and you cannot very easily calculate the variance from multiple discrete samples. So we need a continuous probability function so that we can calculate the entropy.
Thanks.
Great. Thank you.
Yeah, thank you.
All right, last but not least, versatile local manipulation. Take us away.
Thank you. Good morning. My name is Quan Fang, and I'm presenting versatile local manipulation through flexible interlimb coordination. So this work started with a simple question out of our curiosity. Can robot interact with objects using not only arms, but also legs? Robots, especially quadrupeds, have begun to explore this space. They can pick up objects with mounted arms, or sometimes repurpose legs for certain interactions. But these approaches are often limited due to limited fixed limb roles, static limb coordination, and task-specific designs. As humans, we effortlessly coordinate multiple limbs to interact with the world, balancing, stabilizing, manipulating, all in unison. This rich interlimb coordination allows us to perform complex tasks across diverse settings. In this work, we aim to strategically coordinate the arms and legs of a quadruped robot to unlock new capabilities, behaviors that are not possible with the arm alone. Examples include manipulating objects with both an arm and a leg while walking, or performing multi-limb coordination while standing, and using legs to assist or accelerate complex multi-step tasks. Imagine this simple task of transporting a large yoga ball to the other side of the room. This task might seem straightforward, but for a quadruped robot, it involves far more than walking and grasping with a single arm. Given the assigned roles of limbs and their target trajectories, we would like the robot to jointly control the arm and the legs to achieve the task goal. The key challenge during this process is how to precisely perform manipulation with the arm and the selected leg while maintaining stable locomotion with the remaining limbs. To address this, we focus on 3 core aims: flexible coordination strategies, dynamic limb assignments, and versatile task specifications. To enable such capabilities, we present RELIC, reinforcement learning for interlimb coordination. RELIC bridges target-driven manipulation objectives with locomotion stability and the dynamic assignments of limb functions. At the core of RELIC is a limb assignment mask, a binary vector that specifies which limbs act as manipulators and which act as supporting legs. The task specification comes in the form of target trajectories of the manipulators and the body, serving as conditioning signals for the RELIC controller. Given the mask, the targets, and the current robot state, the RELIC controller outputs joint commands as low-level actions. However, directly optimizing a single model to produce suitable actions jointly for manipulation and locomotion is highly challenging. Naive joint optimization often fails to produce coordinated, robust behaviors. To tackle this grand challenge, our approach generates actions through the interplay of 2 dedicated controller modules. This includes a model-based module that prioritizes task success, and an RL module that learns to maintain stable gates in accordance with the manipulation motion. The modules interact through the two modules interact through the whole body robot state and the assignment mask, yielding coordinated local manipulation actions that are both robust and adaptive. Leveraging Relic's advanced interlimb coordination capabilities, the robot can perform diverse and complex local manipulation tasks from 3 types of user commands. Direct trajectories allow the user to specify target motions via teleoperation. Contact points ask the user to select key points on the RGBD visual observations and then convert it into target trajectories. Lastly, Relic can take free-form language instructions and employ a vision language model to compute the target motions. We trained the Relic controller in simulation with domain randomization. To learn stable local manipulation for real-world deployment, we adopt 2 complementary techniques. Motor calibration adapts torque limits from real-world rollouts, and gate regularization stabilizes locomotion through contact time patterns. And the varying settings, our Relic controller precisely follow target trajectories while maintaining stable local motion. Ablation studies also demonstrate the importance of the key design factors. Without them, controllers suffer from large tracking errors or complete task failures. Moreover, Relic supports seamless transitions across gate patterns. Here, red indicates manipulation, purple indicates ground contact, and gray represents lifted leg at locomotion. During task execution, the robot can smoothly lift or place any leg to assist manipulation at any time without pausing or disrupting the overall motion. We evaluated Relic on 12 diverse local manipulation tasks across the 3 task types. First, for mobile interlimb coordination, the robot is able to pick up a large object such as a yoga ball or large cardboard box and move it to a target location across the room. For the stationary interlimb coordination task, the robot can perform tasks such as tire pumping or interacting with large or small trash bins or a deck box. In this task, the robot needs to use a leg to press the button of the trash bin or use the leg to lift up the lid of the deck box. We also have tasks that enable the robot to assist or accelerate multi-step tasks with legs. For example, the robot might go to a shopping mall and use the leg to lift up the cart and then use the arm to retrieve objects, or use a leg to either drag an object with it or kick away the obstacles that blocks the way. Diverse assignment patterns are employed and supported by Relic to achieve the success. In each task, the robot dynamically assigns the limbs for coordinated manipulation, separate manipulation, and locomotion based on the task needs. Across the 12 tasks, Relic achieves high success rates in most of them, outperforming the end-to-end and MPC baselines. These results demonstrate exceptional robustness and versatility of Relic. For more results and videos, please come to our poster and website. Thank you, and I'd be happy to take questions.
Great, we have time for questions. Yes, please.
Very nice work. Thank you for the introduction. So I was wondering, maybe I missed that when you are solving with different tasks. How are you dealing with the masks or the planning patterns? How to generate those things?
Yeah, great question. So I mentioned that we have 3 different task interfaces. So for direct targets and contact points, so the user would directly specify which arm or legs are going to be used as the manipulator. While for the language interface, we will employ the VLM to decide which limbs are going to be used for manipulation and which legs are going to be the remaining supporting legs. Thank you.
Great. All right, thank you, Kwan.
Thank you.
All right, with that, we come to the end of our first session. Thank you, everybody, for listening. Thank you for our great speakers. You can find the posters outside. That concludes us. Next up is an oral spotlight that will be introduced by one of our awesome, awesome local chairs. Thank you to everyone.
Thank you. Thank you very much. Good job. Hello, everyone. My name is Seongnok Choi, one of the local chair. It's time to enjoy spotlight session. So the presenter of spotlight also is now over there. So they are sorted by paper number. And then this is paper number. And then every presentation will be 1 minute, very short, right? So it is very similar to YouTube Shorts. So please move your finger when you enjoy spotlight session. So are you ready? Not ready. So I think that this is the first time for spotlight session, so nobody know about how to do that. So I think that, okay, if there is a sign, then we can start. I think that after this session, we will have coffee break, right? And then in morning session, there is no special coffee break, but afternoon session, afternoon coffee break, there will be exhibition on the first floor, and then there is a barista. So you can enjoy professional coffee made by barista. So I hope you enjoy the coffee at the time. Ready? Yep, it's okay. So if there is if there is any absent, then we just enjoy the video only. So let's start. Let's enjoy spotlight session together, okay? Okay, come forward. No first, yeah. First guy is not absent. So if you see that also in the conference, please blame that. Hey, you missed the spotlight session, and I will tell you your advisor. So let's enjoy video. Wow, boot is very, very strange, right? It is only 1 minute, but don't feel guilty because we will have very long session for poster session at the end of today, right? So please visit the post session and then please blame him. Hey, why don't you miss spotlight session? Wow, cute. Yeah, maybe he talking about something. We didn't hear, but it's okay. Okay. Let's enjoy second video. Wow. Yeah, I didn't expect it.
Okay, this is our work, and our work can navigate to any goal from any instruction in every environment. Yeah, and I think the video is changed. So yeah, so as you can see, it's a real scene in the real world. And our framework is to, we give the human instructions and the current drone frame to the VRM, and we transform the output to action commands to the drone fly iteratively. Yeah, and our key contributions is to transform the 3D navigation into 2D prediction. So the latency will be lower and the efficiency is very good. Yeah, that's all. Thank you.
Thank you. Thank you. Yeah, second person is also absent. So let's see the video. And then if you don't like it, just do this. Wow. Imagine he make movie. Wow. Wow, great.
Hi, everybody. Is it playing?
Collecting robot teleoperation data is too boring. Instead,
The audio is not supposed to be there.
Yeah, this is the first time, as you know, so please understand us.
Okay, so robot teleoperation data sits at the top of the data quality pyramid, but collecting it is often too slow, expensive, and hard to scale. So instead, we propose collecting an egocentric human data set that is efficient to collect, diverse across tasks and environments, and bridges the gap between humans and robots. We use a human-centric representation, which encodes actions using wrists and fingertip key points. This format is embodiment agnostic and can be applied to any bimanual robot. Trained on both human and robot data, the policy predicts future actions as key points, which can be further retargeted to control any bimanual robot. Co-training with as few as 10 robot demonstrations alongside diverse human demonstrations improves policy generalization to new backgrounds, spatial arrangements, and object appearances. It also enables few-shot transfer across different robot embodiments, highlighting the benefits of leveraging large-scale human data sets. Thank you.
Okay.
Hello everyone, so I'm Nguyen from Aalto University, just presenting the extracting visual plans from the unlabeled videos. So the motivation is that currently for visual planning recently, the generative model and large language VLM models still have many hallucination and slow for real-time inference, and also need manual labeling or prompts to make it really work. And our motivation is just simply using a lightweighted visual foundation model to extract symbolic representation from the video and construct a planning domain. Idea is converting the videos into the object-centric features and finding the stable state and grounding it with a symbolic state using the visual foundation models. And in the middle, you can see this is the planned, visualized symbolic plans, and on the right are the robotic just following the visual plans to accomplish very long horizon complex tasks. So our model is, well, better than many generative visual planning models and able to do the real-time inference. And our poster number is 67, so welcome to check it out. And thank you.
Hi everyone, my name is Xiaheng, and I'm happy to present our work called Slack. So we tell people that we we want to do real-world reinforcement learning on mobile manipulators. And this is what people tell us. Are you crazy? That will take forever. And you're probably going to break your robot during training. Okay, so what they're really telling us is that real-world reinforcement learning can be very, very sample inefficient, and as a result, it will take a very long time. And in the meantime, it can bring really serious safety concerns, so you might break your robot while training your policies. But we did it anyways. In fact, within only an hour, our method makes our robot capable of learning this super contact-rich task that requires visual motor whole body motion. And the best part is that the entire pipeline does not require a single demonstration. If you want to know more about our work, please come to our poster session. Thank you.
Hello, I'm De Qian from UCLA. I'm glad to introduce our work on latent adaptive planner for dynamic manipulations. So the intuition is, can we train the robot to learn like human-like behaviors from like the retreat? In this way, we produce this latent space modeling that we can do variational replanning in 30 Hertz and the motion generation in 100 Hertz. So basically, we realize the idea of the planning and the inference and try to do everything in the latent space. So this will give us even better position control and torque controls. So in the beginning, we used kinetic point estimation from the videos, and also we try to estimate torque using the inverse dynamics. So these are several demos for the across different robot platforms in the different robots in our labs. So that's pretty much. If you are interested, feel free to come to our posters to discuss this. Thank you so much.
Hi, my name is Seung-Eun Roh. We present SDEX, unsupervised skill discovery as exploration for learning agile locomotion. We want robot to jump and regard this problem as an exploration problem. This is why existing work rely on either one of these. We try to learn this behavior with none of these. We leverage unsupervised RL, which aims to learn diverse skills, maximally diverse skills. We just add the diversity reward with the task reward, and it learns a diverse solution to solve one task. And there's an adaptive module for Lambda. We train Lambda along with the policy. We use the bi-level optimization framework. During training, it tries out diverse behavior to jump over the gap, and after the training, it collapses to one nice skill that solves the task. And the learned skills are transformed well to the real robot. Please visit poster session 58. Thank you.
It's necessary for mobile robots to safely navigate in various human-shared environments. And our key insight is that the prediction uncertainty can signal distribution shifts by reflecting like prediction errors and the misalignments between the expected and the ground truth dynamics. And our work focuses on quantifying uncertainty and leveraging it effectively to reduce collision rates. So our approach shows much better safety constraints or safety performance in human cross. And our methods also show robustness to out-of-distribution scenarios, including velocity variations, behavior changes, as well as group dynamics. We deployed our policy on a real robot, and it safely navigates even when facing adversarial behaviors, such as humans running towards the robot. Yeah, thank you very much.
Hello everyone, I'm Yizheng Zhang from Tencent Robotics X. I'd like to introduce our Agent World. This is a simulation platform for scene construction and mobile manipulation. The video seems does not contain. Does the video? Oh.
I'm sorry. We are naked. I'm sorry.
Oh, sorry. Maybe I put the wrong video. Oh, yeah, this is a video. Yeah, sorry. Yeah, I'd like to introduce our contribution. Oh. Oops. This is our procedure scene construction. We provide a pipeline to automatically create a lot of diversity scene. And this is our imitation learning and RL result. We use the RL to control the legs and the imitation algorithm to control the arms. And we combine them together to make a mobile manipulation task. And we also do the sim to real transfer. This is a very simple task to make a pick place. Yeah, I think that's quite okay. Yeah, thank you.
Let's move on.
Hi, I'm Jen from Oxford. I present D-Cubed. Oh. Trajectory optimization can find high-performing action sequences by minimizing cost function without expert demonstration or policy learning. While often effective for rigid object manipulation tasks, solving dexterously deformable manipulation tasks remain challenging due to the large site space or numerous contact or limited guidance from the cost function. To overcome this, we propose D-Cubed. D-Cubed requires only task-agnostic play datasets to train the latent diffusion model as action sampler. To optimize trajectory, we propose gradient-free guided sampling, which integrates cross-entropy method into the robust diffusion process. At each time step, latent diffusion model sample multiple action sequences evaluated in simulation, and we keep the only best trajectory for further denoising. With a single model, D-Cube solves complex and diverse manipulation tasks. For further detail, please come to our poster session. Thank you.
Hi everyone, I'm Yun Chu. I'm happy to share our work, ATK. We always want our robot to only train in a fixed setup and then learn and be generalized to different visual variations or robust to disturbances. However, the policy learned in that way are super fragile. Then the question is choose the right representation to be robust to visual variations and easy to be focused on the important things. In this work, we select using key point as the representation to filter out irrelevant information which leads to environment to visual shift. With our method, we can do key point filtering and key point-based policy learning simultaneously. In our experiment, we show that ATK enables policy robust to different background change, random lights, and disruptors in both sim-to-real and imitation learning setup. For more questions, please stop by our poster section today and visit our website. Thank you.
We present Learn From What We Have. This work was completed at Robotics Institute at Carnegie Mellon University. There are natural ambiguities in many manipulation tasks like opening doors and lifting uneven objects. These tasks require robots to interact with objects and learn from the outcomes. Motivated by that, we propose HAF, a history-aware verifier that reasons about past interactions. Coupled with a generator, we theoretically prove that using a verifier to select action with the best predicted reward achieves better expected reward than sampling just one action. This motivates our generator verifier framework to disambiguate online. We use an unconditional generator that aims to be expressive and generate diverse actions, and a history-aware verifier to evaluate action proposals based on past interactions. We conduct experiments in real-world and simulation environments. We found HAF consistently outperforms generator-only method.
Okay. Hi, I'm Sander, and I'm presenting from Space to Time. Imagine a drone flying through a well-mapped city environment where wind varies across space. Not accounting for these spatial variations risks crashing the drone. Current approaches learn a value function offline, but assume they know the disturbance variations, an unrealistic assumption. Our core innovation is realizing that we can treat spatially varying disturbances as temporal variations along a trajectory, for which we can effectively learn a value function. We can then use estimates of the disturbances and its rate of change to create this value function, and as such, space-to-time assures that we can retain safety in spatially unknown varying environments. We showcase our method in both sim and in hardware, where we outperform baselines which either are very conservative or crash. Come visit us at poster 11 in the main conference hall. Bye.
Hello, I'm Won Jong Lee, presenting on behalf of Jung-kyung Kim. Recent vision-based foundation models have enabled generalizable robot navigation with minimal fine-tuning. However, fine-tuning challenges remain unclear regarding data, train time, and performance in new scenarios. So even with fine-tuning, the models encounter frequent collisions due to lack of spatial understanding in new environments. We present CARE, a plug-and-play module enhancing the safety without additional sensors or fine-tuning. CARE estimates repulsive forces to adjust trajectories, avoiding obstacles missed by visual features. CARE improved collision avoidance without compromising original navigation performance. For more information, please visit our poster session. Thank you.
Hello, my name is Jan Węgrzynowski, and today I will present our work beyond constant parameters, hyperprediction models, and HyperMPC. The performance of any model predictive controller is fundamentally tied to quality of the dynamics model. In the real world, due to unmodeled states, is the video playing? In the real world, due to unmodeled states, model miss phenomena like elasticity, fluid dynamics, or backlash. These effects typically cannot be accurately captured based only on current observation. Our idea: encode unmodeled dynamics into time-varying parameters of the dynamics model. This is possible thanks to proposed hyperprediction model, which, based on the recent observation history and planned control actions, predicts a trajectory of time-varying model parameters for the entire MPC horizon. This allows MPC to anticipate unmodeled dynamics while keeping the solve time unchanged. Our approach outperforms state-of-the-art methods on challenging systems, including real-world F1 10th car and drone with rope-suspended payload. Thank you very much.
Okay. Learning to precisely control end effector during locomotion is challenging due to the conflicting goals of locomotion and manipulation. In this work, we present a multi-critic architecture which allows to combine multiple tasks together with task-specific critics. Further, we present a novel twist-based end effector tracking policy which is commanded using the twist required to track a trajectory. With this, we can show very smooth end effector tracking performance at various velocities. Further, we also achieve very low tracking errors compared to post-based architectures over a large workspace. In comparison to a single critic architecture, our approach is better in tracking and balancing multiple critics together. To learn more about our work, please visit us during the poster sessions.
The speaker is missing.
Yeah.
We introduce behavioral robots,
features are absent.
streamlining real-world whole body manipulation for everyday household activities. We identified 3 whole body control capabilities for robots to perform everyday household tasks. First, they must have an extensive end-effector reachability. Second, they need to perform bimanual coordination. Third, they need to navigate stably and accurately. Behavior Robot Suite enables robots without these capabilities through 2 key contributions. First, Joylo, a Nintendo Joy-Con-based low-cost whole-body teleoperation interface for efficient whole-body data collection. Second, Whole-Body Weimar, a novel learning algorithm to model coordinate whole-body actions. To learn more information, come to our poster session. Thank you.
Hello, I'm Abdulaziz, and I'm presenting merging and disentangling views in visual reinforcement learning for robotic manipulation. In typical reinforcement learning pipelines, researchers train and deploy a visual manipulation policy on a single camera view. Yet, due to the world's 3D nature, training on multiple camera views can create better representations for Q-learning, and in turn train more sample-efficient policies. However, these multi-view policies can be burdensome to deploy and can be sensitive to failing cameras. To mitigate these issues, we introduce a merge and disentanglement algorithm. The video is freezing.
Yeah, I'm sorry. Yeah, everything is a series of mistakes. We made many mistakes at the beginning, but we are better and better, right? So when you visit afternoon spotlight session, then you can enjoy better video, I think. Because our staff is now do reinforcement learning, right? Better and better and better. I'm sorry about that.
We introduce a merge and disentanglement algorithm named MAD. In MAD, we merge multi-view inputs to increase training sample efficiency, while simultaneously disentangling views by augmenting multi-view features with single-view feature inputs. This creates lightweight policies that are robust in deployment. We demonstrate the efficiency of our algorithm on 20 visual RL tasks from MetaWorld and Maniskill. Thank you. Please come by our poster 86 for more.
Hi, I'm Yajwan, here to talk about LucidXR. So, learning-based methods in robotics today are very data hungry, and collecting real-world data requires lots of robots, lots of props, and lots of Airbnbs. So it would be great if we could turn data in VR into real-world robot policies. And LucidXR is a stepping stone towards that. We moved the Majoko simulator into the web browser so that it runs on-device on the Vision Pro. This allows us to build manipulation scenes in VR and collect demonstrations with 0 additional latency. We put our data through an image generation pipeline and amplify it by warping trajectory key points and object positions, turning tens of demos into hundreds. We've shown this data working on complex task and simulation using 3D-GS-based eval environments and on the real robot. Come see us at Poster 40 and see some live demos on the Vision Pro, and check out our website at lucidxr.github.io. Thank you.
Hi, we are Sungjae and Daniel, and we'll present Imagine, Verify, Execute, or IVE. What drives a child to explore a room filled with toys? Throughout exploration, we learn about the world dynamics, guided by our own goals or intrinsic motivations. So how can we make a robot explore like a human? VLMs can reason about what objects are, where they are, and what might happen next, things that traditional RL struggles with. But VLM can just rely on their imagination. Humans actually do more. We discover new scenes and try to understand the dynamics. We often verbalize goals similar to a child telling what they plan to build with the blocks. The processes are actually supported by semantic understanding, memory, and action. Then can we design a robot agents that do the same so that the robot can move tangram pieces around, create new shapes, and make a title of them by itself? Come to poster number 49 to find out. Thank you.
Hi, my name is Justin, and should robots have eyeballs?
Well, that's what we study in this work, where we build an eyeball, which you can see at the center, pair it with an arm, and use it to do large workspace manipulation. So here, even though nothing is visible, the eye learns to first search for the towel and then for the bucket to carry out the task. And what's really cool about this is that all of the eye behavior you see here is never supervised. So all of the tracking of the object and searching for towels is emergent purely from RL, driven by the need to act. And without supervising it, we see surprisingly human-like gaze emerge. So here, when I free drive the arm, you can see that when the arm is up, the eye learns to look for the towel, and when it's down, it looks for the bucket. To do this, we jointly train the hand and the eye together. We use reinforcement learning for the eye and behavior cloning for the hand. So in this way, the eye learns to look to make the BC policy do well. We train in 360 videos, come to our poster to learn how, and check out our website for more, including code and data. 감사합니다.
Wow, great.
Hi, good morning everyone. I'm Naman. I'm presenting my joint work with Jayesh and Siddharth on learning symbolic abstractions. Humans excel at learning from small demonstrations in simple tasks to solving tasks that are much complex. In this work, we present our approach that takes unannotated and unsegmented trajectories and then learns a symbolic model that is predicates actions and samplers that can be used with TAMP and then solve much complex tasks that are unseen completely in the test task. So on the left, here are our 5 test settings, 3 of the simulations and 2 with real robot, where the robot is using much simpler demonstration to solve much complex tasks. And on the right, what we are seeing is our experimental evaluation with one of the hand-coded Oracle abstractions, and then one of their approach, which uses foundation models for solving problems. For more information, please come to poster 54. Thank you.
Hi there. We are presenting constraint-preserving data generation for visuomotor policy generalization. Data collection is time-consuming, so given a single demo, how can we use it as a seed to generate more demos with diverse object geometries and poses? So we present CPGen, a method that starts from an expert demonstration annotated with key points and then generates thousands of new demonstrations with novel geometries and poses, and then zero-shot deploys sim to real, this learned policy. Data generation works in 2 phases. We start from an expert demo that we segment in free space segments, skill segments, then we annotate it with actor key points to represent constraints, and then we take a new observation, adapt the skill segment accordingly to preserve the constraints, and then use motion planning to connect the adapted constraints. And using CPGen, we generate thousands of demonstrations and transfer trained policies zero-shot to the real world. So if you want to know more also how this relates to related work that was also presented here at Corl, come to poster 29. Thank you.
Hello everyone, my name is Yang and I'm presenting H-Drone, benchmark adaptive teaming in multi-drone pursuit. I'm sorry. I'm so sorry. But I think I have submitted the video. So I'm done.
Yeah, just before copyright. You can. Well, I'm really sorry. It's end of today's spotlight session, and then it's time to enjoy coffee. And then at the post session, you can enjoy everything again, in-depth discussion and Q&A. So please enjoy Corl and Seoul and coffee together. Thank you.
뭐야? 이 아니었어요. 저기서 조종하는 거. 그거 좀 봐.
go ask.
Sure. Yeah.
That was very. I should make you do this. These things.
Oh yeah.
Yeah, now discuss what kind of beauty spotlightization. So obviously
Yeah, I guess I need to show. Oh, wait. There's another one that's something is going into this.
Check, check, check.
All right. Gosh. Oh man, why does it always do that? Sorry.
Yeah, it's okay.
Yeah, it's yeah, I need to test this out. I don't know why it's doing this. Okay. Okay, wow, this is perfect. Okay, so I can see this.
네, 괜찮아요. 짧아. 됐어요? 네. Hello, everyone. Hello. Yeah, it's our time to start the opening session. So can you please get seated? Hello, everyone. So good to see everyone. Welcome to Corl 2025 in Seoul, Korea. Before we begin, first of all, I apologize for slight difficulties with our spotlight session. It will not happen again. Okay, welcome to Seoul once more. I hope you are enjoying Seoul. As you might be aware, this is the 9th Corl. The very first one was in Mountain View in 2017, and now we are having this in Seoul 2025. I need to mention that this, as you are realizing, this is the biggest Corl ever. The size of Corl is more than twice of what it used to be a year ago. We have close to 2,500 in-person participants. Even if we just count the main conference attendees right now, it is close to 2,100. In yesterday's workshop, we had close to 1,500 attendees. So as you can see, there was an explosion. Before we go into the details, I hope you are having fun in the giant maze below this convention center. If you have not tried yet, please do. It's quite fun. One more thing before we go into the details, how things are organized in this venue. We are in COEX, the very best convention center in Seoul. We are occupying an entire wing, from the first floor to the third floor. At the moment, you are in the auditorium, which is on the third floor, where the main oral sessions will be. On the second floor, there will be additional rooms, ballrooms, for the overflows. On the first floor, there will be posters and exhibitions, as well as main coffee and snacks. The grand ballroom at the moment is closed, so that the exhibitors can actually prepare their exhibition. But we'll start to open this after lunch today. So have fun in this wing. Okay, we have a good organizing team. The general chairs include me, myself, as well as Abhinav. Unfortunately, Abhinav was unable to join the conference, but rest assured, you are in good hands. The program chairs include Joseph, Shuran, and Haewon. And as mentioned, we have truly amazing organizing committee, including Kitana, Hyemin, Seongnok, Byungok, Jinhyuk, Younghoon, Rerel, Tingnan, Daehyung, and Sehun, serving as open review, local registration, workshop, demo, and publication chairs. We also have Jonghyun, Aditya, Bernadette, Wenhao, Kiin, Kwan, Jinghwan, serving as sponsorship chairs, inclusion, finance, volunteer, virtual experience, and web chairs. We also thank the leadership of Global Learning Foundation. Okay, there is one peculiar thing about the conference this year. That is that we are co-locating with Humanoids 2025. Humanoids 2025 will happen from September 30th to October 2nd. And as you are realizing, September 30th is the overlap day. We have 2 joint keynotes, as well as 1 special panel session. So I hope you enjoy this overlap day as well. Now, I'll hand over to Shuran so she can cover a bit more about the program details.
Okay, hello everyone. I'm Shuran. I'm going to give you a quick overview about the program. We have a very exciting program for the next few days. So here is the program overview, and also on your badge, actually we have printed out the program for you, so that you can always check on the badge about what's the time now and which session you should go to. And then a few things to highlight. So first of all, we are still a single-track conference. I don't know how long we can keep this, but we know people like it, and we try very hard to keep this conference single track. So that means that everything will happen in this room, like all the orals and spotlight session will happen in this room. So you don't need to find another room except the overflow scenarios. And then we have 6 oral session, 6 spotlight session, and 3 poster session. And the one thing I want to highlight is that even during the break, we have something going on, which is the demos. So feel free to go to see the demos during the breaks. It'll keep you very busy. And then as Michael mentioned last day, we have joint keynotes and panels with the Humanoid Conference. And I think that's very exciting. Okay, and then, yes, talking about keynotes, we have a very amazing line of speakers lined up for our keynotes session and also earlier career session. And then we have a very diverse, people are coming from a very diverse background, both in industry and academic. So I think this is really the highlight for the conference. Make sure that you make time to attend those amazing keynotes. And then here's a little bit of updates about the paper this year. So I think one of the biggest change that we did this year is that for the required limitation session, we actually no longer limit the page limit. So it's no longer count towards the 8 pages. So you can actually write as long as you want for your limitation session. And then what we found is that this long limitation session really is helpful for reviewers to understand the proposed method and also their assumptions and the limitations. And also, I think this extended limitation session helps to lay the ground for future works. So I think it's a very nice practice that maybe we can carry over for the future. And then as you expected, we have the largest number of submissions this year, but we managed to keep relatively similar acceptance rates with a little bit lower acceptance rate. So in the end, we accepted 42 oral papers and then 221 poster papers. And then for the review process, we also did a few experiments, something new this year. So first is that we have the reciprocal reviewer requirements, meaning that if you're author for a paper, you are required to register as a reviewer as well. Whether you are actually assigned paper to review, that's based on your expertise and also maybe experience in the past, but we always require authors to register as a reviewer. And then I think the biggest experiment that we did this year is that we limit the rebuttal format. So back then we have this free format rebuttal and a relatively longer rebuttal process, but this year we actually limit the whole rebuttal need to be fit into 1 page. So this is actually, we designed it to first fit into our very short time frame for review process, but also this is an attempt to try to reduce the burden and also the stress for both the authors and the reviewers, because we found that sometimes the reviewer actually need to read such a long rebuttals that's almost like reviewing another paper. So we did this experiment, but we don't know how you feel about this particular change. So let us know whether you like it or hate it. Let us know, so we can decide whether we want to keep the same format or change it back. And then overall, because of the new requirements for reviewers, we actually get a very big pool of reviewers this year. And we also have 86 ACs that did a lot of hard work on making the decisions of which paper to accept. And then we have a very short review period this year. We only have 36 days. And because all the hard work from all the ACs and reviewers, we're actually able to get a large number of reviews in time before the rebuttal period starts. So finally, I really want to thank all our ACs and the reviewers for your hard work for making this Corl conference possible. And I think you are really the important part of this conference. Thank you.
Hi everyone, I'm Kirtana. I served as the Open Review Chair this year. You'd known me as the person who would write the very threatening emails about desk rejection and stuff. All right, I'm here to introduce the humanoid learning special panel. So, like Michael introduced, this year something special about Corl is that humanoids and Corl is co-located. This is to acknowledge the increasing significance of humanoids in robot learning and learning in humanoids. Traditionally, the two communities had been separate, but this year we are bringing them together to explore ideas and synergies in the middle. To this end, on the shared day, we would have an interesting panel discussion with a lot of esteemed members and leaders in the industry who are working on humanoids. We are blessed to be joined by Kanishka from Google DeepMind, Jonathan from Agility, Jung Ho from Rainbow Robotics, Huazhe from Galaxia Dynamics, Scott Reed from NVIDIA, and He Zhang from Tencent Robotics. This panel will be moderated by myself and Michael. Something tells me this is going to be very interesting and fun. So if you're here on the 30th, please make it. It's on 11:30 in this room. Next, I would be handing off to Youngwon to introduce the demo and workshops.
Hi everyone, I'm Youngwon Lee, workshop chair, together with Little Pinto. This year we got amazing workshop tutorial proposals. We got 40 amazing proposals. It was very hard to choose 17 workshops for this year. We already did all these workshops yesterday. We hope you enjoyed those workshops. I truly appreciate all the workshop organizers and attendants and local organizers who help us doing a great workshop this year. We will have demo for next 3 days. We got 13 accepted demos, including 11 research demos and 2 sponsored demos. The demos will be held around 1:30 p.m. to 4:30 p.m. on the first floor. So yeah, please enjoy, and I will hand over to the next speaker.
Hello everyone, this is Hyemin, one of the local chairs with the Seongnok, and we will introduce about the local tips and venue information in this slide. And for the first of all information can be found out in our website. And if you go our website, click on the attending, and behind the attending there would be many things, including the venue information and the local tips. Here we provide the QR code here, but you can also see this QR code in the next slide, so I will move to the next slide, okay? And also this QR code information can be found out in the web page. So going to the venue information here, and yesterday we had a workshop on the southern part of the COEX. But from today, we would have the things in the northern part, which is denoted with the red dots here. The first floor name is Grand Ballroom, and second floor is the ASEM, and third floor is the auditorium. And here we have the oral and spotlight session. And if this place is full of people, we are sending the people to the overflow rooms, which is on the second floor and the third floor and the fourth floor, on the last day on the fourth floor, I mean. And for the posters and exhibitions, it's on the it's on the first floor, and it is from the 1 p.m. today, okay? So moving on, more details. So about the third floor and the overflow rooms. So here is the main thing happening, and if it's fully booked, so we have several overflow rooms. So first thing, let's go on to the right side, which is the ASEM here, which is known as ASEM. So room 201, 2, 3, including here, and on the 206, and on the 210 here. And if these are fully booked, and if it is full of people, you can move to this meeting room, which is on the left and right side of the auditorium. Okay? And one more thing is that for the case many people coming to the last day where the session is held with the humanoid, we prepared another meeting room on the fourth floor, which is the meeting room 3 and 4. So it is only available at the 30th of the September. Okay? And moving on to the next slide. Posters and exhibition and demos. It is color-coded here. So poster is the purple thing, it's on here and here. Here is the entrance, and at the front of the entrance there are posters, and alongside with the exhibition we have also the posters. And exhibitions are here, and these parts are for the copy. We have also the baristas here today, and the demos are happening in this section. Okay? And note that this is since today afternoon 1 p.m. And for the lunch, we provide the lunch every day from the 12:30 to 1:30. And pick-up and eating place is a little bit different. So if you want to pick up your lunch, you need to go to the auditorium lobby, which is the 3rd floor. So lobby, if you go outside of this room, there would be the lunch pick-up place. And it can be also be picked up in the overflow room in here. Room 201 to 203, 206, and inside. Inside the room, we are giving the lunch. And where to eat is a little bit different. So please eat inside the auditorium and the lobby and inside every overflow rooms. And yeah, so enjoy your lunch inside the rooms with the desk and chairs. And note that, so if you see the badge, so you will have a coupon for the lunch for the, so inside here we have the lunch coupon for the last day. So lunch coupon is for last day because we are mixed with the people attending the humanoid conference. So for the last day, please use the lunch coupon, but except for the last day, you don't have to use the lunch coupon, okay? And about the welcome reception, which is today dinner, please come to the auditorium lobby. So it's on the 1st floor, 2nd floor, and 3rd floor here. All the places are having a welcome reception, and you can enjoy the award-winning local wine and beautiful scenery of the Bongwonsa Temple. Okay, and then moving on. And the banquet is held in another place, which is the Harmony Ballroom in the Westin Seoul Parnas Hotel. It is next to the COEX. So we are in the 3rd floor of this place. So if you go to the 1st floor, there would be Grand Ballroom Lobby, and you can follow the direction. There would be many panels directing to the Westin Seoul Parnas Hotel. So if you move to these hotels, this floor, and you would see the banquet. And for the case when the banquet is also the full of people, we also have an overflow, which is on the Grand Ballroom Lobby 1st floor in the COEX. And we also prepare the K-pop performance, and if you want to enjoy that, please come to the banquet. And last thing is about the tour near the COEX, and as it is well known, it is very big giant maze, but there's also the funny things inside the COEX, like Permadang Library, Aquarium, and the Media Square. And next to this place, there's a Bongwonsa Temple, and also the Gundam base for the people who loves the robotics, okay? I mean, Gundam is also the robot, right? And last thing is about the tour. We are on the southern part of the Seoul, which is COEX. We are there, okay? We are here. But except for that, there are also many playful things inside the Seoul. So from my perspective, from the Han River, the southern part of the Han River is more like very city things. But in the northern side of the Seoul, there are many traditional and heritages in here, like a palace and museums and so on. Okay, this is all about the local things, and let me pass it to the next presenter. Thank you.
Hello, everyone. I'm Byung-ok. Here are some registration statistics for our conference. There were a lot of things with registration process this year. So when we started planning, we didn't expect Corl to be this big. So in 2023, our initial attendance estimate was 1,500, and we booked the venue based on this. So, but the actual number of registered attendees is nearly 2,500. So we apologize for the registration difficulties. Let's move on to some numbers about our attendees. Looking at attendees' background, about 52% are students, 32% comes from industry, and remaining part is from academia. So by country, Korea is number one, and followed by United States and China. Korea has shown to strong interest in robot learning. And when we look at attendees by company, Google takes the top spot, and followed by NVIDIA, then Amazon, and proudly in fourth place, Etri, where I'm working. How about universities? So one is first number one is Seoul National University, and second is KAIST, and third is Postech. Now I'd like to hand it over to Jinhyuk to continue.
Yeah. Oh, I'm Jinhyuk, another registration chair, and I'll briefly explain the registration process. As quickly exceeded our initial expectation, the entire process became more complex and noisy. Here is the timeline. At the July 10th, we began the early bird registration, and it was ended at August 8th. But after the end of the early bird period, we paused registration because the number of registrations already reached our initial expectation. So at the time we paused, and next we issued priority registrations for essential participants and some contributors. At this, we tried to minimize the number of priorities. After handling priorities and slightly expanding the capacities, we reopened 250 slots to the public, but they sold out within 15 minutes. And from the August 25th, we opened a wait list and released the registration code sequentially by the wait list order. After reaching our prepared capacity, we closed the entire registration process at September 22nd. And in this complex situation, we had to apply more strict policies than usual to preserve the fairness. And here is the brief overview of our policies. And our goal was to maximize the public registrations and preserve fairness. And priority was limited to very essential roles for the conference, and some exceptions were approved for only unavoidable cases. Also, we strictly announced in prior for every event. And the waitlist operated on a first come and first served basis. But even with these measures, we recognized that some were dissatisfied, but I'm sorry for the complexity and inconvenience. Thanks.
Okay, it's me again. We have a huge amount of sponsorship this year. This is almost like 3 times the size compared to Corl 2024. And we have 4 diamond sponsors, 7 patron sponsors, 29 standard sponsors, and 7 live sponsors. And I really thank all of them. Without their support, yes, the conference cannot run. Okay, we also have more than 50 volunteers helping us for the conference. If you want to find them, look for the white conference t-shirts. Our regular conference t-shirts will be in black, but the volunteers will be wearing white. So they are all around you. Please try to find them if you need any help. Final thing to mention, everything is being live streamed on YouTube. Just go to YouTube, search Corl 2025, and you will be able to find the live stream, including what's happening right now. That is pretty much everything. And before I conclude, I would like to invite all our organizing committee here, who actually were very essential for organizing this conference. Please come to the stage. Yeah, really, without our amazing organizing team members, this could not have happened. So I really appreciate them, and let us thank our organizers once more. All right, that is everything. I hope you really enjoy Corl 2025 in Seoul, Korea. And yes, one more thing I didn't forget. Here is our Corl Foundation President, Ken Goldberg, and he has some messages to you.
Thank you, Michael. Let's have a big round for Michael Rue here. He deserves it. He has been working on this for several years. Literally thousands of emails have gone around, and he has attended every single detail with amazing care and technical skill. I also very quickly want to acknowledge someone else, Aude Biard, who had the idea to have these two conferences co-located. Yes. Aude had this vision a couple years ago, and that has worked out extremely well so far, so I'm really impressed by that. I also want to mention our other officers in the board that keeps the continuity for Corl since it was founded in 2017, and it's been a pleasure to work with the treasurer, Jay Tan, and our wonderful secretary, Jens Kober. They have each worked countless hours, many emails, and Jay in particular has been dealing with all kinds of wire transfers. It's super complicated, but they both deserve our applause. So thank you guys for that. And someone who really deserves an immense amount of appreciation is my predecessor, and who has been doing a fantastic job, still continues to advise us. We basically bother him almost every week with some kind of question. But Vincent Van Hoek, thank you very much for everything you do. He created this, and he continues to be a really guiding light. And so I just want to say, now we have to start thinking about year N+3. So we want you to start, if you're interested in hosting or helping organize this conference, we'll be back in Asia, Oceania in 2028. So this is a good time to start thinking about it. We're actually revising the process for bidding for these, to host. So think about it now. And I think it's the worst kept secret of all where it's going to be next year. So I think it's safe to reveal. It's going to be in Austin, Texas. So Yuka and Peter Stone and a number of their colleagues are going to be hosting us next year. So you'll be hearing about that later. But anyway, thank you all for being here. Thank you guys for organizing this wonderful thing and having us in such a fantastic location. 감사합니다.
All right, thank you, Ken. Thank you all once more. This is pretty much it, and I really hope you enjoy the conference. Thank you.
All right, everyone, let's get started. Our first keynote session. So my name is Haeon Park. I will be chairing this session. It's a great honor to introduce Professor Sang-baek Kim at MIT. He earned his PhD from Stanford and moves to Harvard for his postdoctoral work. And he joins MIT. Since then, he has been a professor of mechanical engineering at MIT and director of biomimetic robotics lab. And very recently, he decided to move to Meta. And then I'm really looking forward to what interesting work he will perform in Meta. And he's mostly famous for his seminal work on legged robots, including MIT Cheetah series and MIT Humanoid. And his new electric motor design truly revolutionized the field of legged robotics. As you can see now, the legged robot can now run and jump and dance and even backflipping. And he open sourced his technology, and then he really fueled the real commercialization of legged robotics. And not only that, he is among the first who introduced model predictive control on the legged robot. And this enabled truly agile and dynamic legged locomotion on the quadruped robot and humanoid robot. Recently, he started working on dexterous manipulation using his new electric motor design and then model predictive control. And then I really want to learn about that in his talk today. So, are you ready, Sang-baek?
I hope so.
Okay. Okay, so with that, let's welcome Professor Sang-baek Kim. A round of applause.
Thank you so much, and thank you for inviting me. It's such a wonderful conference. It happened to be very, very big. I expect actually about 200 people when I came. And I didn't even expect this many venue. Slide is working? Oh, okay, awesome. So yeah, because I heard that I have to cut short my talk, so I will just jump into the topic. You don't need to even talk about why we're interested in physical intelligence. Actually, I've been talking about this concept and this word since 2015. My actually tenure talk was about physical intelligence. Okay, all right, so hopefully that works. And I will just really fly by my previous work and then go to the more interesting topic. I believe everybody's interested in manipulation nowadays. Something is not very stable. Is it the connection is not stable or? Try again or? Okay, let's try again. See if this works. I don't know why it's a little unstable. All right, hope that stays like this. Okay, let's go. So, I don't want to emphasize here in this community because, our life was influenced by this IT technology heavily, last 2-3 decades. And even me, I can feel this like screen time is increasing even nowadays. But that's where all the industry and all the monies are focused. But you can't ignore importance of this really physical services, and you guys can agree Because if you really think about all these like virtual services, actually not, there's a lot more importance in the physical. If you just imagine some social media disappear one day compared to like a garbage collector cannot work anymore, or policeman doesn't work anymore, or fireman cannot work anymore. It's just a fundamentally different story if your food delivery doesn't work. So we really need to think about this more seriously for the future. And as some of you already know, all these conventional robotics technology is actually sitting in the industry, even nowadays, except like a vacuum cleaner, a few examples. Most of the robots are still stuck in this very controlled environment because the paradigm they've been following is very much very rigid, very accurate position controlling with a very heavy industry. So my first like a 10-year career at MIT is about how can we shift our design paradigm from this grounded application, everything is expected, we know everything about the environment, and precision position control solve all the problems. Where when it comes to mobile application, none of these applied, and then we have a completely different set of design requirement for hardware. So I actually focus on hardware for first 10 years, really focus on force-controlled machine that can actually do running. I'm not sure if you can realize when you watch a leg robot walking and running, the contact time on the ground is actually very, very small. In our case, when Professor Hewan Park working on cheetah, the contact time of the cheetah was about 80 milliseconds, 80 milliseconds. If you cannot have a control bandwidth high enough, basically you lose a chance to control the ground action force. So I will just quickly show you my previous work, mostly focused on quadruped. And you might be able to see Professor Park right behind the screen. And we achieved like 6 meters per second at animals level achievement. This is like 2014. And then we did the steeplechase, like we apply a few different algorithms. All of them are physics-based algorithm, and then we can actually achieve this in 2014. And then we moved to a little bit more omni-purpose machine. The previous robot cannot actually turn very well. So we made a more modern design. At the time, we were only a few of them doing this. And we did some teleoperation as well, using this very different type of actuator that can be more force controlled and then more impulse. And then MIT Mini Cheetah, it became kind of popular because the design was kind of open sourced in many ways. And then you can see the impact of this fantastic platform. And this all, I still believe that this controller was the most advanced balance controller ever seen. And it's actually full nonlinear dynamics MPC running on a computer. And we did some vision. Probably the vision is like the least things we did. Well, I have a very little expertise in vision. So, but when it comes to leg locomotion, once balance is done, like you have to really focus on vision. So, sort of inevitable. We built a bunch of them, including collaboration with Naval Labs. We actually give it out to the other academic institutions. So we've been about to actually collaborate and organize some workshop, and then COVID happened, so we couldn't do much. Anyway, the focus is actually the developing actuator using the motor and the electric motors more proprioceptive way. Is if you look up proprioception, it's kind of even hard to pronounce, but it's more like your feeling is own instead of having another sensor outside. The opposite word is actually extroception, which is actually your sensing in the skins and then feedback through it. But how your muscle works is actually more like this. Your skins are actually not force sensor. Your skins are just like vibration sensor. Your muscles are all doing all this force control. And then pretty much that apply that idea in the electric motor world. This is the fantastic example of less is more. We have a less sensor, so less the force sensing, and then actually you achieve a higher bandwidth and more robust force control. And this will be very awkward equation in this community, but this is actually how we define backdropability. Everybody still uses this term, but there's no proper definition. So if you want to know a little bit more about what's true meaning of backdropability, please look at impact mitigation factor, and then look at our papers. And that's how you define proper backdropability. Is an impact mitigation factor is a normalized relative inertia of your operation space inertia compared to the worst case whole inertia. That's how we actually define it. And you can see some impact. I just put together some chronicle chart with a bunch of robots. And when I first started MIT, pretty much Boston Dynamics hydraulic machines were dominating. All companies like China and Korea, they're copying Boston Dynamics. Hydraulic is the way to go, electric motors too weak, and so on. After we show off our capability of MIT robots, this Cambrian explosion happened. So now you can see most of the Chinese robots, not all, pretty much follow our tradition. The people call it QDD, but actually proprioceptive actuation is a proper term because it has a meaning on it. And Boston Dynamics, my students actually go there and then terminate the hydraulic program, and they're all following our direction, including Unitree. So you can see quite an impact. And then recently I kind of looked it up, and I realized companies who are producing this still use terms like MIT power or MIT-driven actuator. I don't know what that means, but they're still using these terms, and I don't control the MIT logo or copyright, so please talk to MIT administration. Yeah, that's not my work. We can talk about this forever, but I want to just talk about model-based versus RL, which is actually a very interesting topic in the locomotion. That's where I can really talk about detail. But you can step back and then you can think about these examples as a good example of kind of tension between data-driven versus more like a rule-driven. I know you guys are using these tools for this, and people are using it. Just you really think about why you're using that tool for that application. Really, please step back and think about it. And then the reason why we're using data-driven for certain things, because it actually can work without having assumption, without really relying on accurate model. Whereas a model-based, like rule-driven, model has to be accurate. As long as your inside assumption actually works really well. The problem is once you step out of assumption, you basically have no guarantee whatsoever. But same thing you can say in the data-driven. If you are out of distribution, now you are pretty much out of there's no control over it. So if you really think about these two animals, if you think about MPC, this is a world of MPC that is inside an assumption. Imagine this circle is an assumption space, and then MPC is completely general there. There's no hole. Maybe there's some constraint cause a hole, but as long as you're inside an assumption, you have a no hole. But the problem is the assumption space is so tight, so you can't actually do many things. And if you have multiple of these, it's very clunky to connect these. That's like RLs or like behavior cloning, you can stretch way more. You can do more things really easily. And it looks like you can cover more space. But you forget about that. There's actually empty between these branches. And then we actually don't know how to fill these branches anymore. Not really. So if you think about these very complementary tools, actually you might be able to achieve something much more advanced, much more general by combining these two. If I really think about step back, like if you think about any plumber who work on your house, just guarantee none of the plumber will have to work on things they worked on before. There's not a single case of plumbing job is exactly the same as what they've done before. So you have to have some stretch of logical reasoning to fill those gaps. Bottom line is, best engineer always mix the knowledge and experience and with the reasoning. I don't know what the ratio is. We can't even quantify how to do this. We have to think about this completely two different set paradigm to really solve the problem in the way we want it, not just to show off certain things. So I just want to say that for leg locomotion case, where is reinforcement learning is MPC, but you can think about this for many, many other areas. And this is going to be sort of the main message I want to deliver today. I want to show you some of the work. This is actually reinforcement learning, but the model is inside and guiding, so you actually make it stepping a lot more reliable. And then inverted pendulum model have a proper reasoning, physical reasoning. And this is purely MPC. There's no data collection whatsoever. It's all rule-based. And then it's actually covering quite a bit of larger space. All the things you see here is this behavior. There's one policy. Because it's an MPC, because it's a model-based, it can cover the whole space with a very little hole. Of course, sometimes there's collision avoidance, there's the constraint comes in, cause some issues. But in order to do all these with the reinforcement learning, you have to create many different policies, and then you don't know how to stitch them very well. It's a cost function problem. Cost function tuning is a really, really big issue. Another good example, which is probably not as relevant as, I'm not sure anybody working on ping pong project. If you really think about ping pong, what tool we have to use? I know Google's and other company using like just data-driven, collecting tons of data. This is actually the best project to use MPC. There is very little uncertainty in the model. We need to collect some data to really accurately predict the recessive coefficient. But you can, and this is actually requires such a high precision. If you're holding rocket like this and translate forward, it's not an issue, but we actually need to swing it. And to achieve this like a top spin, down spin, and then high speed. And this is MPC really, really shine. And then I can show you, we can achieve like a human level, at least like beyond human level, use this model base. This project is only going on 2 years with the 2 students, by the way. And then now we finally, David is the lead MPC controller here, and then we finally create a gantry. This is not full-blown MPC, but you can see now we can probably cover entire space. We can compete with a human. The message is we have to really think about what kind of tool you're going to use and why you're using it. And then if you have a problem, oh, that's very nasty, it's hard to model, yeah, of course you go the data-driven. If you have a very clear model like a ping pong, why bother collecting data trying to solve the problem? And then you're never going to really collect enough data to cover all the spaces. Let's move on to the main topic of manipulation. I'm very new to manipulation, by the way, and then I'm not actually a learning person, so I hope you guys can some insight, but I'm going to talk very high level, so hopefully you can get some insight out of it. I actually have a 1-hour lecture on this. You don't know what you're doing, and cognitive bias toward AI and so on. But I want to show you, make it very short by showing one video. This is one video I just pick up apple or pear. I still don't remember what it is. Pick up fruits, and then I was kind of curious, like what my hand is doing when I'm doing it. So I asked my student, like, can you take a video, slow motion? But I'm not going to look at it. I'm just going to pick it up. A lot of videos are boring, but this was one of the most interesting I want to show you. Did you see anything? So let me show you, because you probably couldn't see anything, so I want to show you slowly. First of all, you just slap the hand and just glide happen. Your fingers are so compliant. Humans are not very too cautious about sliding hand pretty quickly. And then you can notice that 2 fingers, 2 apples, 2 fruits are in contact with my finger. If you have any optimization experience or algorithm person, you're going to write some heuristic or experience, even data-driven, even stochastically. Highest fruit is easy to pick, right? Even kids will know it. Like anybody will say, okay, I'm going to just cost function, like the highest one, I'll pick it. Apparently, my hand is much dumber and pushed the best apple out, and then ended up making contact with more fruits. And even at this point, if you have any reasonable algorithm, go to the left a little bit and pick up the top one, right? I was very disappointed to see this video. It actually chose the worst possible choice among all the fruits that I made in contact. I was like devastated. Wow, my arm is so dumb. Maybe I shouldn't say I'm dumb because I don't know what's going on. I don't remember any of this action. And then, okay, so you make your contact on 3 fingers. Oops. I'll show you one more time. And then, it's actually interestingly, my hand felt that that's not secure enough. So dig deeper, and then make a really secure contact, and then bring it out, finally. So I was like, wow, that's really dumb. But, if you watch the video again, that was 0.7 second. During the 0.7 second, it made a contact, make a decision, push out, as I happened to push out the apples, empty-handed. You have the fruits contact, and then you make decision, and then you assess the quality of the grasp, and then dig down, and then finish the game. If I do this 1,000 times, I'm pretty sure I am successful 100,000 times. And you're gonna find the video like at least like 10, 20 times probably, maybe more. I have absolutely no idea how to write this kind of algorithm, even though each step sounds really dumb. The point is, like, it's not about optimization, it's about good enough solution. If you know any about biology, evolution, you probably understand what I'm trying to say. We need to figure out how to create robustness by the architecture, not by just finding the maximum optimal solution or precision in any layer. We have to really achieve the robustness through the architecture. So let's talk about architecture. Many of you are doing this and then here, probably inspired by LLM, and then we know that LLM is relatively high level abstraction. Everybody agree? Like if you think about an abstraction level, planning where to go is high level, but like moving, walking toward the airport is low level, right? And then probably the VLM is trying to get a little bit more concrete and then collecting more refined data. And then now a bunch of people are working on VLM and VLA actually here to really create an action with the more collecting data. And then I realized a lot of people start using physical intelligence on this level. My definition of physical intelligence wasn't that. I've been talking about this since 2015, where even language model wasn't there. And then my definition of physical intelligence is actually below that level, where actual physical interaction happens, where physics is really dominant. And this is where actually real dimension explode. If you just think about last mile problem or last 10-meter problem, anybody familiar with the distribution, delivery, network management, operational optimization? When it comes to think about you're the Amazon, you're organizing delivery. What dimension you're dealing with when you're dealing with the last mile, last 10 meter? How about last a meter? When you open grab the door handle, open the door, hold the box, and you have to push inside the box, or you have to push a button, open the garage door. Last meter, if you get close to the physics, your dimension explode. As long as you're inside a car, you will do two-dimensional space. And then as you get close to the final last millimeter or last centimeter, your dimension explodes. Just think about how much data you have to collect to solve this problem. So, what do you mean by Sangbi? What do you mean by physical intelligence? I don't know, we're still trying. So my proposal is like, why don't we just try to come up with a way to represent that lower level intelligence and then see if we can help. So our attempt 3-4 years ago was, why don't we use some reactive layer? Because that's where all these dimensions explode. We need to have some feedback algorithm to solve problem. And I'll show you some of the example. This is actually really common in human world, and you guys are probably not familiar. If you pick up something in an object, nobody crushes that object. We always feel just enough, and then when you pick it up, and if you feel weight, and then you properly squeeze more. And that's happening every single time you pick up. You just watch out next time, what your hand is doing. You don't know what you're doing. We explicitly create that so to make sure contact force is within the friction cone. So you can see when you pull down, you can see the robot fingers actually squeezing more to secure the contact. And you can see the same thing when you're grabbing a bottle, empty bottle, and then you pour water. You can see the squeezing force goes up, so you can make sure you're inside a friction cone. These things happen just all the time, and I can guarantee you can get this information looking at the YouTube video. This is a very limited application, but it's actually very interesting. I mean, pretty sure we can expand it to more realistic. That's what happened. We want to be anti-polar if you have 2 fingers, and then that reaction literally happened in 100 millisecond because our sensors are very fast. You can do this kind of stuff. You can see that. That's real time. And if you see slow motion, it's actually a lot slower, a lot faster. That's a slow motion. So that's what happened if you slow motion. And if you combine, I don't want to, there's a lot of the details I'm missing, but basically we use a YOLO to recognize your object and then just vector. There's not much planning. Actually, there's no planning. And then you achieve basically relatively fast grasping. I know the problem is relatively simple compared to what everybody's doing. But this it was very interesting to see the effect of the reflex allows to be a lot less accurate on the positioning hand, and you still achieve the relatively high performance. That's the 1x, by the way. So you can think about a lot of interesting local, low-level feedback algorithm that's called a virtual magnet. This is proprioceptive finger. I've been working on proprioceptive actuator for leg robot and humanoid. That's a finger, has no sensor on it. So proprioceptively can feel that the actuator actually can feel that light touch, and then you can react upon. And you can also think about non-contact sensor like a proximity sensor to really dodging the collision. But actually, the whole point is not avoiding collision. So the whole point is actually wrapping around the object without really worrying about sliding or friction and contact and so on. It's just still thinking, these could be a representation of the lowest level action so that we can actually don't need to collect all this crazy amount of data to solve nitty-gritty data explosive space. And if you really think about it, LLM is amazing. LLM really seems like it generalizes everything. What is token there? Language token. Who created that language token? Google created? Or a bunch of data collection created? Human created. We call this table, we call this mic, and everybody agree on it. And then it has its meaning of embedded meaning on it. And what is that equivalent in a space, in the action space? We have a verb, human has a verb. Can you grab that? And what does that mean? The grab can create like a 2,000 PhD and it still cannot finish that grab. We don't have enough resolution of the action space that really represent the action token. We can actually deal with it, which is not quite the same as the language space. Okay, so in Sangbe, you talked about a lot of contact and grasping. How about actually reaching? We actually, Dr. Lee actually worked on this MPC, sort of MPC, but it's more like a rule-based and then velocity field-based control. One of the problem of the conventional robotics, a lot of trajectory optimization and your execution is done by some kind of controller as time-based. So if you are crashing something, if something happened, you will just plow through, follow the trajectory. It's not going to work in the real world. So this actually is based on velocity trajectory, velocity field. If something happens, it still doesn't. It's basically time invariant. It's almost like a vector field that kind of guide where you want to go, including collision avoidance. Those are all included, and then you can actually achieve things. So I want to show some of those action. This is actually what's the reasoning inside. How we achieve this such a fast solving is that we separate like global search, global planning in the only end effector, and then solving more complex like a joint controller in the locally. So there's going to be some chance where it's going to stuck in the local minima, but I hope VLA, VLM kind of high level prior will solve that problem. So this is a setup. I'll show you some of the video. This is all 1x, there's no sped up here, and then robot is basically chasing down, and then disturbance, rejection, all these included, we can still do it. There's a zero teleoperation data collection here. Is it as general as some of the VLM? No, there's a lot of things are contrived and then only, but just think about how much you can do if you actually follow the rule of the world we can actually imagine and you can create out of intuition or even physics. Another example, we created some obstacle. And Dr. Lee is like moving the object around, and then these things, without colliding the obstacle, it can be done with just like a few lines of code. And then while get this disturbance rejection happening and so on. And another example is a time invariant. That's why it's okay to push, and then it doesn't really plow through trying to follow the predetermined schedule of the trajectory optimization as conventional robotics approach. Like a moving object, for example. And then think about the speed and then the reliability. I mean, something happened. We can actually take a look at why is it failing. Is it a perception space failing? Most of the failure here actually is all perception because we only have a one-point cloud camera. We probably need to go onto the RGB with a much more advanced perception stack. But my lab is very small. We couldn't do this yet, but we plan to do it. And then finally, he actually include some of those reflex. So it's a little bit hard to see what reflex is going on. Dr. Lee actually figured out how to find the antipodal stable aggressive posture independent from geometry. No matter what geometry you throw it there, as long as your point cloud measure the 3D shape properly, you will find the antipodal relatively quickly. So you have to see the slow motion, not the sped up video. The gripper is not very good, so we're going to move on to next level gripper. And then we're only working on antipodal. We're going to try to we can expand this idea actually to multi-contact way too. And this is also have that initially is not very good pulse, but it's actually evolved toward the direction is more antipodal, more stable, aggressive. These are actually all happening in the low level in the reflex layer. and geometry reasoning based on geometry you see from the camera. There's still a limitation. This is a proof of concept, but you can see how these can actually complement all these data-driven level where we can have a global planning is reasonable, but you lose all this detailed information. You can ground those using physics, the rules we know, and then using all these QP solvers and then all the conventional technology where you can actually debug. That's actually very important words. So I just want to throw a few thoughts I've been thinking about for a while, last 5-6 years, and I want you to just think about this. LLM, why don't you just copy human trajectory to solve end-to-end? I think a lot of people told me, actually, literally last six months or a year. I just want you to think about the closest example is actually self-driving, very dangerous. It's a physical machine, everything. But car, if you think about a car as a robot, car has only 2 degrees freedom. And then what kind of object does it deal with? A road, which is flat object. Your vector field is pretty much constant. And then you don't make a contact break contact there. You're always on the ground unless you have something really funky in your car. And Tesla has about 8 million cars and then sending data to the Tesla without paying them. I don't get paid when I'm sending my teleoperation data every day. And guess where they are? I was very impressed, actually. The FS is very impressed, probably because of 8 million teleoperator, 8 million robot, and sending data for several years. Yet, cannot even handle local information because it's end-to-end. You can also think about conditioning that large model so that you can figure out that cross-section, right turn is only right turn only, that kind of information. But just think about how many cross-section has to be conditioned to train that end-to-end to properly behavior. And Boston Street here, there, you have to be on the left lane or right lane and so on. And when it comes to manipulation, your dimension explode. Your degree of freedom at least is 8 to 9 for one arm. Entire humanoid is easily 50. And then your object dealing with compared to the flat ground is nearly infinite. What kind of task you have to do with the manipulation? Probably hundreds of different tasks, maybe tens of different tasks. Car task is one thing, just moving from A to B. You just think about the complexity level difference and how many robot teleoperator pair do we have compared to 8 million Tesla car with the 8 million users. Just think about how much data do we need to achieve the Tesla level. Tesla FSD is pretty good. I've been using it every day. Not quite there yet, right? People talk about bitter lesson. Sangbe, we've been there again and again and again. We don't want to be there again. I'm pretty sure half of you at least are sitting here because of that bitter lesson. I just want you to think about what is the difference between virtual intelligence to physical intelligence. I'm not saying one thing or another. I just want you to think about it. How do we collect the data? Virtual intelligence is already in the web. Of course, we have to label them. You have to send the data, can collect those. But pretty much a lot of them were already in the internet. We had to collect data, building a robot. We had to collect, hiring people, teach them how to use it, fixing the robot. And so yes, great, like Peter Lesson article include a bunch of success rate. None of them are autonomously independent, by the way. There's not a single larger data-driven machine learning agency running completely independent like a human. That's fine, because this is just a system, AI tool. Is that okay for robotics? It's a robot, but I need to be there all the time. That's never going to be the case. Maybe taxi, the Waymo, you need to watch over several vehicles. Maybe that's still okay, but in robot, that's not really the case. And uncertainty, the most important difference is uncertainty in action space. Like even car, actually, action is actually quite certain. If you have a trajectory, 99.99% of the time, that car is going to be able to physically follow the trajectory. In manipulation, that is not the case. Every millisecond, there's uncertainty. You cannot measure everything. You might not even be able to achieve that. It requires feedback. You can't just collect a bunch of successful data and then expect to be just amazing. I will ask you this question. Just please think about it. If you collect 1 million people's walking data for 1 million hours, that's a lot of data. Walking, I'm not even talking about soccer, playing basketball. Do you think we can train a humanoid to walk? What do you think? If you think you can, raise your hand, please, right now. Million people walking million hours in flat ground. I'm not even talking about mountain climbing, just flat ground. How many people you think you can train humanoid robot, good one, not bad one, to train in the walk in the flat ground? How many people? I'm surprised. I expect like 90% raise their hand. How many people know you can? I can guarantee I don't know the answer, but I would say, of course, why not? But one thing I can tell you is like what happened if I shove that robot, kind of funky way, 45 degree from the back to front by twisting. Like if I shove certain way, I know what happened. 100% I can guarantee it's going to fall, where none of you is going to fall that way. Why? Out of that million people's million hours training data, how many of them got shoved? Probably 5, maybe 10. Basically, you only have a successful trajectory data. You don't have a recovery. You don't have a nasty failure data if you are just using expert data from human. You can show that robot, if that robot walk on the flat train, everybody look at you, wow, that robot walks. We're done with the locomotion. Because you can tell the difference until you get shoved. Just think about that in manipulation space. Just think about that. Don't read the line at the bottom if you're a student. Oscar Wilde said this. He doesn't know robotics, I can guarantee you. He died way before. He said that the imagination imitate. But it's a critical spirit that creates. Creation is not just imagination or imitating. Imitation is not true learning. And somebody might say, do we need to learn? Do we need to really understand? Your LLM might say the same thing. I don't truly understand, but I at least pretend to be truly, that I'm better than you. If I ask LLM, what is confidence? Can you describe what that means? It will describe better than anybody I know in life. But does it really understand what it feels like in a confidence when you hit the ball when you're playing tennis? Bang, I just hit the winner. That's the confidence. Do you think the LLM actually can feel what I feel? Why? Why we need to understand? We can cover all the spaces. We're going to have a hole there. Data cannot cover the entire space. I'm not saying one thing is model-based or approach or another. I just want you to, if you have two different approaches to really reach 100%, I want you to really think about which trajectory you're going to take. That blue curve looks just like any of this data training, ML training curve. You know, everybody probably familiar at this point, right? Which trajectory you want to be? I just want you to think about it. Composable, interpretable, testable, debuggable is an essential key item to really reach 100%. I didn't say it. Professor Greg Hager said it in 2024, I think, ICRA. He says another thing, edge case is actually the general case. We really need to achieve this to really handle our societal need. We're aging population and so on. And I think how you guys think, these people, proper thinking direction is going to determine whether we're going to achieve this or not.
Sangbe? Sorry to
That's the
interrupt.
last
Yes.
slide, yeah.
Okay.
There was a HDMI issue at the beginning. So anyway, so by the way, somebody took it. That's why we had a problem. This is the last slide, and thanks for all the sponsors, and then I'm ready to take questions. Thank you.
So due to the time limit, we will only have one question. So I think everyone wants to have a lunch now, I think. So let's conclude our first keynote session. Yeah, let's thank to Sangye.
Thank you. Thank you very much.
to deploy into the real world. I'm Kashyap, and I'd like to show you some recent progress our team has made to address this with a new evaluation technique called reliable evaluation.
腾讯 Robotics X 和福田实验室基于过往多年在机器人领域积累的技术能力，广泛结合产业端需求，发布了规划大模型、多模态感知模型、感知行动联合大模型。各个模型之间通过多模态感知、规划、记忆等模块的协同工作，转化为机器人的具体行动。规划大模型作为机器人的大脑，具备自我认知能力，通过与人类自由沟通、拆解任务、调用工具、查询知识库和在执行中的自我反思，最终完成长程复杂任务，并可为特定领域提供角色问答服务。欢迎参观腾讯机器人实验室。
来，我们握个手吧。
当然，很高兴认识你。多模态感知模型可实时整合环境感知数据，构建语义丰富、空间关系精确的3维层级地图。
你们俩去站在前面2个企鹅雕塑中间，我给你们拍个合影。
支持自然语言输入输出，实现多场景下的高效信息检索，助力机器人精准完成任务规划与环境交互。感知行动联合大模型结合快慢系统思考与时空物理感知，有效赋能灵巧手、夹爪等多种末端执行器在复杂场景下对多样物体的操作能力。同时，针对人形机器人训练得到的模型，可实时感知机器人本体信息、环境地形信息，并做出及时响应，控制各关节协调运动，进而控制机器人灵活移动、灵敏运动。目前 Hyros 已经适配过双足、轮式人形、4足、机械臂等多构型本体，操作支持夹爪、灵巧手等多种末端执行器，与多家机器人企业在工业、汽车、家电等多行业进行场景落地实践。未来期待与更多机器人企业联手，共同推动机器人行业发展，共建人机共存、共创共赢的未来。
Omron Cynic X quickly captures signs of change in the world and the social issues that arise from them, designs the near future, and aims to create innovative technologies necessary for solving those issues. In particular, we are focusing on research into the evolution of AI agents with physical bodies and 5 senses. We aim to create a society where these AI agents enhance human autonomy and independence, enabling people to enjoy creative activities.
Can you believe it's been 20 years of robots?
People.
Innovation.
Collaboration.
Challenges.
Leading. Growing.
Conversation.
Expanding.
Serving.
Vision.
Research.
Participation.
Recognition.
Pioneering.
In the race to build truly intelligent and general-purpose robots for all applications, one element stands above all. It's data. Max Insights delivers large-scale, high-quality and cross-embodiment datasets for embodied intelligence and general-purpose robots. Using precision motion capture, we capture human data and retarget it across different robot embodiments. Our high-quality data is collected from real-world environments, including not only bedrooms, living rooms, kitchens, garages, and laundry rooms, but also warehouses, restaurants, and other everyday settings. We offer data collected using the same robotic arm across different scenes, as well as data collected using different robotic arms in the same scene. If you're building robots and want better models through better data, it starts here. Embodied intelligence starts with Max Insights.
bathroom. What are you doing here? Wait, come here, come here, come here, come here, come here, come here.
What are we hitting? Chest, legs, back?
I think I'm doing back today.
I spent the last decade of my life working on building humanoid robots like Neo.
Oh, here it comes.
Oh my gosh. I can't even go. I'm gonna take some robots into the jungle.
Vinny, what do you have to say?
I'm tired. New problem.
Oh my god, he's squatting.
Redwood. Oh my god. Okay. So I'm not a rapper. I'm a magician.
No way, really? This is great. Wow. Not good enough.
Yeah, that's a moment like I feel like, hey, we can do it.
Fan, what are we doing?
We're about to go to TED.
We're living in Vancouver.
It's about creating a future where we actually have time to focus on what matters to us as humans.
Okay. Hi everyone. Welcome to the Diamond Sponsor Talks. My name is Aditya. I'm a sponsorship chair. And
my name is Jonghyun Choi from Seoul National University, another sponsorship chair.
all right. So first of all, we want to thank all our wonderful sponsors for their support for Corl. Today we have two speakers. First, we have Kanishka Rao from Google DeepMind. Kanishka is a research director at Google. He's worked on several things, including speech recognition, imitation learning, and recently robot foundation models for control. The floor is yours. Yeah.
All right. Thanks, everyone. As I said, I'm Kanishka, and I'm going to talk today about general purpose robots with Gemini in the physical world, and I'm presenting on behalf of the Gemini robotics team. All right, so we've seen some really remarkable signs of general intelligence from frontier models. Just 11 days ago, Gemini achieved the gold medal at the International Collegiate Programming Contest World Finals. And a few months earlier, Genie 3 was released, and it was a new frontier in world models. So really remarkable general intelligence. And on the robotic side of things, we've seen some really impressive physical dexterity. Things that we didn't think were possible a couple of years ago, now we're seeing the robots do. So how do we bring these two things together? Really general intelligence and very physical, high dexterity? Well, we don't know, right? So this is, I think this is one of the fundamental questions that robot learning has to solve. And at our Gemini robotics team, we tackle this problem from two viewpoints. We are looking at frontier models like VLMs, like Gemini, and we're making them more embodied, making them more spatially intelligent. And on the other side, we're taking robot models like VLAs, and we're trying to make them more general. And maybe the answer to this generalized dexterity question is somewhere in the middle of this picture. So we're still studying this problem. And we've been studying this problem for a better part of the last decade, but in this talk, I'll focus just on the last 6 months of work. Earlier in March, we released the first VLA based on Gemini Robotics, and then a few months later, we released an on-device version of that. And just a few days ago, we introduced Gemini Robotics 1.5. So when we first talked about Gemini Robotics earlier in March, we focused on 3 capabilities. This model has to be interactive. An intelligent robot model is. It can perceive its environment and react to the changing conditions. It should be general, and we showed that this model could kind of leverage Gemini's word understanding to do things it hasn't been trained to do, like slam dunk a basketball. And it's very dexterous. It can do complicated dexterous tasks. So this is our first kind of look into Gemini-based VLA. And then a few months later, we introduced an on-device version of this, and we showed that with it's slightly less general than the Gemini robotics model, but it's a much smaller model, so it's great to see that it has these same properties. And with a few tens to hundreds of demonstrations, you can fine-tune it for a specific task. And we opened this up, the model and the SDK, to our trusted testers. I'm really excited to announce that, a few days ago, we introduced Gemini Robotics 1.5. And in this version, we introduced a couple of new models. We have our Gemini Robotics 1.5 ER model. ER stands for Embodied Reasoning. This is a VLM. It understands the physical world. It is spatially intelligent. And it's a VLM that's kind of designed and optimized for robotics use cases. And then we also introduced Gemini Robotics 1.5. This is our VLA, and I'll talk more about this as well. And we brought these two together in a agentic system, and these two work really well together to solve really long horizon and complex tasks. All right, let's first talk about the embodied reasoning model, 1.5. So this model is state-of-the-art for spatial understanding, and on the left I'm showing a plot which includes 15 external spatial understanding benchmarks. And the right-hand side, you can see the kinds of capabilities that it has. It has object segmentation, it has pointing, trajectory prediction, progress estimation, success detection, all the things that you would need for a robotics task. I would like to highlight one specific task here. We added pointing as a capability to this model, and one really cool thing that we saw was it was able to generalize this capability in a much more general way by interleaving reasoning and pointing. We call this complex pointing, and this is an example here. We said the waterfall example is a plot a trajectory of 8 points. that shows the way the water falls. And the model was able to point to like, okay, this is where the water starts flowing, and this is the midpoint, and then it hits a pool, and it creates a pool. So this is a very, is a remarkable kind of, generalization of the pointing capability where it can reason about what those points mean and kind of expand it. So this is a hallmark of a frontier model where it can take a capability and really kind of, scale it and generalize it. So if we can get dexterous manipulation to, scale and generalize the way this pointing capability does, we'll be a lot closer to this dream of dexterous generalization. So this model, the Gemini Robotics ER 1.5, is available for you all to try today. So here's a link, and go try it out yourself. All right, let's talk about the VLA. So Gemini Robotics 1.5 is our most capable robot action model as of today. So here I'm just showing a plot of the different progress scores on a variety of tasks. And so in distribution, as well as in our generalization benchmarks, it does much better than previous models. And specifically for action and task generalization, it really gives us some nice performance boosts. So we're pretty excited about this model. Let's talk about some of the breakthroughs that went into the VLA. So we do this thing called motion transfer with this model. At a high level, it encourages the model to think about its motions and understands the physical impact of what it does. And one really cool consequence of this is that we found that this model can work across different embodiments. With our previous 1.0 model, we had required to fine-tune these models for specific embodiments. With this 1.5 model, with motion transfer now, we are seeing that a single checkpoint can control all these different robots quite well. And this includes a diversity of robots, including, a bi-arm parallel jaw and, even a humanoid with multi-fingers. So we're pretty excited about this ability to now control a variety of robots. The second really impressive thing that we were all very excited to see was this ability of this model to zero-shot skills. So here on the top left, maybe you can focus on that one first. We showed one of the robots, the bi-arm Franca, how to unplug a cable from a computer. And the Aloha robot, which has never done this unplugging task, is able to do it zero-shot. So this notion of like getting the VLA to understand what its motion means and how it interacts with the physical world is really, we can see it in action here where it can understand this motion and transfer it across embodiments. And we're really excited about this capability as well. So here are some numbers. This is showing a progress score on the top and success on the bottom. So these are very difficult tasks. These are like zero-shot tasks, so all the numbers are low. We're asking the robot to do something it's never seen before. But to highlight here, the orange bars are basically asking the robot to do it zero-shot with just its own data. And then the dark orange bar is when we throw in all the robot data in together. This is similar to what we've done in previous works like RTX, which is a bit like a naive mixing of data. And then with the blue, this is with motion transfer now, and you can see you get a pretty big improvement with this technique. All right, let's talk about a second breakthrough with this VLA. We also introduced this VLA as a thinking VLA. Here the VLA outputs thoughts and actions interleaved, and so this is trained to do this end-to-end. And this basically means that it has to explicitly reason about its physical actions. And there's two kinds of thoughts that it has. One about the next immediate step that it has to do, and also about the physical motions of its own body. So these thoughts, as you can see on the left, is just an illustration. You can see this thought scrolling as it's doing the task here. It's very cool to see this in person because you can, it's very interpretable. You can read the thoughts of the robot and see why it's doing the things that it's doing. It's also steerable because you can have an oracle, basically provide these thoughts, and it makes them more general. So overall, we're pretty excited about this as well. Let's dive into one example to just see what's happening under the hood. So here, the task the robot has is to put the objects in this white bin. And on the top left, you can see the thought process that it has. It says the next step is to pick up the yellow tennis ball with your left hand. So it has kind of decided that that's the next thing I should do. And it looks at the objects and it picked the yellow tennis ball. And then it saw its left hand is close by, so maybe I'll use my left hand. And then it decides to pick it up. And then the cool thing here is that after it's picked it up, you can see that the next step changes to put the tennis ball. So there's an implicit success detection happening here where it understands where it's at and then moves to the next step. And here you can also see its more detailed motion description thoughts. So these are the full thoughts of the robot. I won't read them all because they're all verbose. And then at the very bottom, you also see error recovery happening. If you kind of drop the object, it sees that it's dropped it and then can replan and go pick it up again. And we also showed in a variety of medium horizon benchmarks that this thinking concept really helps the VLA become more general. And in the previous talk, Sangbei talked about how imitation, without understanding is not really learning, and I tend to agree with that. So with both of these breakthroughs, with emotion transfer and thinking, we're in that spirit of trying to, endow the VLA with capabilities where it has to think about what its actions mean and understand its motions in an embodiment agnostic way. So these are all kind of, trying to get the model to, be more general than just imitation. All right, so then we bring both of these together in our agentic system. This is a high-level overview where the ER model is user-facing and can take speech and text and images, and then has all these different robot capabilities that help it orchestrate the VLA. And then the VLA is the one that controls the robot and does all the tasks, and it has its own thinking trace. So this whole thing kind of comes together, and the ER model can also make digital tool calls if it has to solve the task. So it's a really neat agentic system that comes together. Here are just some more numbers. So the blue plots are basically the VLA-only thinking. So this is a much more long horizon task. So you do need that two VLM and VLA together to solve the task, and that's the dark green bars. I especially like the comparison with the light green bars because that is just Gemini 2.5 Flash, and you can see that's not as good as our Gemini Robotics ER model in terms of orchestrating the VLA. So there's a really nice message of our robotic-specific VLM pairs really well with our robotic-specific VLA. So these two work quite well together. We also really care about safety, and we have a holistic approach to physical and semantic safety. With this release, we also announced the Asimov 2.0 benchmark, and we also showed that this ER 1.5 model is safer than our previous model. And again, we showed that thinking can improve this safety reasoning. All right, so I breezed through a lot of stuff. There's way more technical details on our blog post and our technical report, so I really encourage you all to go read that. And we have a booth. Come see Gemini in person, and we have the Aloha and the Biome Franca, so please come see those. And then, yeah, just want to give a quick shout out to the team, and I see a lot of them here. So please come, talk to us. There's a huge team effort, so thank you.
Thanks, Kanishka, for the talk. Do you have any questions? Maybe one? Or? Okay, if not, please thank Kanishka, and we'll have our next speaker. Yeah.
All right, so our next esteemed diamond sponsor is from BitRobot, right? And Michael Cho, the co-founder of the company, will give a talk about their recent approach for robotics regime and some learning schemes. So please welcome Michael Cho for their talk.
Usually I use HDMI. Just not use
Yeah, please give a round of applause.
Oops. Okay. All right. Hey guys, sorry. My name is Michael Cho. Super excited to share with you guys today about this project called BitRobot. Quick one about myself. So I'm not a researcher, although I've always been fascinated by research. And in case I look a little bit familiar, perhaps some of you have seen this podcast that I co-host together with Chris Paxton. Shout out to Chris. On a weekly basis, both of us interview researchers like yourself whenever we come across a cool robotics paper. And I must say, Chris and I have learned a lot. It's been a real privilege to talk to many of you. But today, the thing I really want to talk to you today is about BitRobot Network, which in my opinion is a really ambitious attempt to crowdsource what I call the world's open robotics lab. And I'm just going to put this up front. I think that crypto will drastically accelerate embodied AI research. Now, before 90% of you want to rush out the door, like stay here. Hear me out for the next 15 minutes. So the way I'll try to convince you is just to talk through what we've been doing the last few years, what we're doing now, and how would this whole project actually work. So anyway, this is me 3 years ago in New Zealand at the Corl, much smaller event back then and a very different time before ChatGPT. So the reason why I went there was I started hacking on this like Earth rover, like kind of like a small sidewalk robot. And these days, we actually did, these are the two models, a small one and a bigger one, and we really think of it as toys, and indeed we sell them for a couple $100s. And because these things come with 4G, so that what allows us to do is to build this kind of like a real-world robotic game. It's kind of like a Pokemon Go. So you drive around a robot and then you collect like virtual items on the map. And because these are really affordable, right? So we managed to deploy around the world, and these days people are buying it and it's popping out all over the map. We went viral multiple times on social media, YouTube and all that. And at the beginning, my hunch was that perhaps the data collected could be useful. And so I started Googling around 3 years ago, found this paper, shout out to Jusha. Jules asked me to go to New Zealand to meet him, and that's where I went. And that's the first time I've heard in my life this phrase called teleoperation. But I guess on hindsight, I realized the game that we've been building is basically that. It's basically remote teleop. So that really encouraged us first to, I guess, open source this data set. So we did this last year. It's about 2,000 hours of real-world driving data collected right across many cities. And that then led on to this competition called Earth Rover Challenge. We did it in IROS last year and then ICRA again this year. The basic idea is we pit the human gamers, right, to take on the same game as AIs, like models developed by researchers like yourself. And unlike most like competition you found in these conferences, like the robots are not at the venue, the robots are out there, right, in Singapore and Kenya and all that. And you can almost think of it like evals in the wild. And also a quick shout out to the other co-organizers. Like I said, I'm not a researcher, so without them, there's no way this competition could have happened. So in case you're wondering, the AI sucks, at least compared to a human for now. But what pleased me the most personally is that I'm starting to see like research that's being done because of this effort. So here's a survey paper capturing some of the learnings. Here's a paper that used the data set and also used the robot fleet to actually test out their policies in the real world. And I'll say since then we've moved on, to other type of like research collabs. So just to give you some sense, we did some remote teleop for manipulation now in simulation. We also started working with SIG Robotics and Factor. I don't know whether you guys know the QA and Acceler robot. So we do actually have a booth at the conference. So later on, if you go to the booth, you'll be able to basically remotely control from here in Korea a bunch of Kiwi and Acceler robot and also Earth rovers to play some robotic game around the world. Also a shout out to the guys at Virtuals. We started helping them with the iOS app that do ecocentric video data collection. World model, so this one, our contribution there was we provided compute. So 16 H100s we give to them to do this. And then also a shout out to the guys, Pranav and Kyle from Robo Arena. This is probably my favorite project the last few months. So here we basically, our main contribution there is we help out with the real world evals. I think they have a very neat way of doing pairwise model comparison in the real world, and I think this is very much needed in the space. So very happy to contribute there, and I'll encourage anyone with a Droid setup to also contribute. Yeah, so also a few announcements about some of our own open sourcing efforts. So the first one is a bigger data set, so called Berkeley Photobot 7K. As the name suggests, so this is in partnership with the lab from UC Berkeley. Shout out to Catherine Glossop if you're still around. She spent a lot of effort basically to started from 10,000 hours to bring it down to 7,000 hours of real-world driving data. And the other thing that I'm super excited about, yeah, so this is the robot. We are open sourcing the entire hardware. So we're working with the team, SIG Robotics, that did the Kiwi, but also with the labs from NYU, George Mason University, and NUS. And when I say fully open source, I meant everything. I meant the electronics, PCB design, embedded software, 3D, printer file and whatnot. And also a shout out to the guys from Hugging Face. So we are working closely with them to make sure that both the hardware and the data set are fully compatible with the robot platform. Another one I'm super excited to share with you guys today is RoboCap. Yeah, so this guy over here. So we've been working on it the last 2 months. Something like this. So it's basically an egocentric video data collection kind of device. Because of the form factor, right, we get away with basically way higher, like I guess, weight budget. And also because we have a big surface area, so there's no overheating, which effectively means that we can basically collect data like, for more than 10 hours, basically. And our guys have been wearing this to play badminton and whatnot whole day, no problem. So this thing have 256 gigabyte on board. Yeah, not the lightest, but it's all right to wear it the whole day. And it will be fully open source. All the electronics and everything will be open source. But if you do want to get one today, you go to robocat.io, put in a discount. Definitely get it because it's definitely below BOM. But we really want to basically get people to start using it and give us feedback and maybe contribute to this effort as well. Yeah, and also a shout out to a bunch of universities that we've been collaborating with. What I want to say though is like I said, I'm not a researcher, right? So I don't do any actual research ourselves. What we try to do though is to do the stuff that researchers wanted done but shouldn't spend time doing. And this Earth Rover Challenge to me is a very classic example of the kind of stuff that I feel that my team should do. And I personally have always been very inspired by the DARPA Challenge of the O and ARC Prize as well, for those of you who know. And so we've been thinking about how to make this Earth Rover Challenge more impactful. And so very happy to announce the Earth Rover Grand Challenge today. And the way to make it more impactful is just to make it, the navigation way longer, right? So Berkeley to Stanford, for those of you who don't know, this is about 40 miles. All the way from Berkeley to Stanford. So literally driving this small little bugger. Oh, and of course we went viral on Reddit. People are starting to follow it around. But yeah, so this is a footage. So we basically have a team of really dedicated human gamers, most of them from the Philippines, I think. Basically remotely controlling this little toy and going from Berkeley to Stanford. And the reason why we try to do that was basically to kind of stretch the limit of what is human benchmark. Well, what can a human do with just a tiny robot and with only the front camera and back camera? And yeah, we managed to do it. Turns out it took 33 hours, 35 minutes, and 34 seconds. Oakland is definitely, a rough spot. But we managed to get past it. But the idea is that we want to do it a lot more regularly, and we try to coincide with robotic conferences wherever possible. But the idea is we want to do it more regularly, so we can take regular snapshots of the improvement of the embodied AI. We start with scene environment, and then before we move on to other cities, right? But the idea is ultra marathon style, 40, 50 milers. But then what we want to do is to put a big grand prize, $1 million, for the team of AI researchers that can basically convincingly beat the human benchmark. So that's the first one. Why stop there? Let's do origami 2. So very happy to announce this next one. So here, very fortunate to have a bunch of hardware manufacturers coming up. In fact, later on at our booth, you also see this exact demo. So Tesolo will be having this set up there. You can see how they try to do this. But we are even more excited to be able to do this together with the Nippon Origami Association. So basically, they are the world experts for origami, right? In fact, these couple of days, we have a grandmaster of origami who flew all the way from Japan to Seoul. And you'll be able to see the demo, right? Basically, the human expert right next to what we can do with robots today. So the general idea is the same, quarterly, and have basically embodied AI try to take on humans and put a big grand prize, $1 million. This is the last one, IKEA assembly. Same idea, start with something simple and then move on to all types of IKEA furniture. And then have human expert versus embodied AI do regularly and then put $1 million. So this is actually part of a bigger Big Robot Grand Challenge Fund that we are announcing today. So obviously we have announced 3. So we're definitely up for a proposal for any moonshot outcomes that you guys have in your mind that you think could be cool. Would be cool to have human benchmarks and then we take regular snapshots. Now, how does this all work? How do I get the funding? How do we get the H100s? How do we get the tens of thousands of teleoperation hours? And so this is where crypto comes in. Yeah. Let me show you some tokens, okay? So, in my view, I think crypto incentives is probably the best invention since, let's say, the limited liability company, right? For us human beings to collaborate. And it is a way to do massive crowdsourcing of resources globally. So if you look at something like Bitcoin, right? Bitcoin itself as a project has never raised a dime. And yet, every year, I think it consumes something like 0.5% of the global electricity bill. Just think about that, right? So in fact, if you look at other crypto projects that are successful, by and large, in my view, they take on various forms of this concept of crowdsourcing. So for me, when I think about embodied AI research and what you guys do in this room, I think of it like a mahjong game. For those of you who play mahjong, it's a game that you must play with exactly 4 players, not one less, not one more. So obviously you need data, you need compute, and you need people like yourself, right? Who are really the tastemakers that take the data and take the compute and do something cool. But because this is physical AI, ultimately we need to test them in the real world and in fact maybe do in-context learning, in-continual learning and all that. Which means you need a big fleet of robots, probably a lot of humans in the loop to press a kill switch, perhaps, and a lot of real estate. So I guess for me, this conference is about like solving research problems, but I think someone should also take a serious crack at solving the incentivization problems, right? How do we incentivize the guy, the gamer sitting in the Philippines, have times on their hand and ask him to contribute teleoperation hours, and yet reward him, like compensate him fairly for his efforts. So this is basically Big Robot Network, right? And the way we structure this is a network of subnets. Subnet, just think of it like every subnet as an open research mission, right? So for example, the Cyber Robot game we have, right? So what do we have in this subnet? We have gamers or teleoperators. We have people who own the robots. We have the people who deploy the robots. Now 3 roles can be played by a single dude, but it can also be 3 different people. But what you get in the end is a data set, right? With the Earth Rover Grand Challenge, you need researchers, you need perhaps a lot of compute if you're doing VLA, you need robot owners, you need deployers. But at the end of the day, you get a series of policies that are well tested and evaluated in real world settings. And so I would say this idea can be really scaled to any kind of robotic embodiments or any kind of research area. And you can think of maybe another way to think about Big Robot is like a giant grant writing machine. Although I do want to just say that crypto is not magic money, right? But to me, crypto is a fair share in exchange of contributions. So this is probably, in my view, the most important slide. So I think of crypto as facilitating leap of faith at scale, right? So if all of us in this room believe that for there to be a huge outcome in embodied AI, we need all these things, right? The only thing is we don't know when, and we don't know the exact path to get there. But guess what? Like this kind of setup is perfect for crypto because this is like a big call to action to the general public and say, hey, we need help. We need a lot of robots. We need real estate, blah, blah, blah. We need compute. Can you just contribute? And in exchange, we'll give you a token, obviously not transformer token, crypto token. Even though the path there is uncertain, but because the outcome is so significant, today the token price will not be 0. Which means that today we already can get the resources we need. And so I don't have time to gloss over a lot of details. There's a white paper and blog post, but I would say fundamentally what we're trying to solve at the Big Robot Network is first, how do we gather resources at scale and then turn around and give it to you guys basically. And in my view, if this is done well, this can be done at about $1 to 10 billion US dollar. I say these numbers not out of thin air because there are crypto projects that are successful that are trading around this kind of range. $1 to 10 billion sounds like a lot, but I don't think it's enough. So the second question is also how do we make sure that the resources that we gather is allocated properly? And so to me, the whole Big Robot Network will have many subnets. It's like, the whole network will have many shots on goals. And over time, the network needs to adapt itself to make sure that the resources are, channeled to hopefully the channels that can really move the most needles. And in the coming weeks, we have a lot of announcements coming out from other crypto projects or other robotic startups that have nothing to do with crypto, as well as other labs that are going to contribute to this network. So maybe final thing I want to say, instead of thinking crypto bros as purely like get rich quick kind of speculators, I would encourage you to think the opposite, to think of us kind of as your biggest fans. And I would say that maybe there are thousands of you here, but there are probably millions of us out there willing to contribute, right? Be it our time, be it our compute, be it our homes, be it like to buy a couple of robots that you want us to buy. And yeah, so get involved, propose or co-organize some grand challenges with us. And also in your research, if there's stuff that you think you need resources to scale, do come chat with us. If you want to get even more involved, come and help us govern like how to allocate these resources among the subnets. And of course, like get a cap and come to our demo booth and try out the demos. I know it's a weird talk, but thanks for having me.
Thank you very much. All right, that concludes the first Diamond Talks, and we have another Diamond Talk tomorrow. So stay tuned and see you tomorrow. And thank you very much.
Okay. All right, so we're going to switch to the second oral session. My name is Stanfei. I will be chairing this session, and the topic is perception. Okay. We have the speaker of our first talk, One View, Many Worlds here, and let's welcome him.
Hello everyone, I'm an intern of Beijing Academy of Artificial Intelligence. I'm going to introduce our work about one view, many words, single image to 3D object meets generative domain randomization for one-shot 60-pose estimation. Before introducing our paper, imagine robots in the real world facing endless new objects, like an unknown toy or a toy or a household item. Current VLA methods handle broad tasks like folding or cleaning well, but struggle with perception. For fine manipulation, we still need accurate 60-pose estimation to operate. But get it is tough. Pre-scanned 3D models are rarely available. Multi-view capture is impractical, and single-view reconstructions suffer from scale ambiguity. Consequently, reliable one-shot 60-pose estimation from a single image had long been deemed nearly impossible. Thus, we introduced one-pose VRGene, a novel approach for one-shot 60-pose estimation for unseen objects without requiring 3D models. Our method leverages single-view 3D generation for both of training and inference, and introduces a coarse-to-fine alignment strategy to simultaneously recover the object's metric scale and 60 pose using multi-view feature matching and refinement iteratively. To enhance robustness, we employ text-guided generative domain randomization to create diverse synthetic training data, effectively bridge the gap between generated models and real objects. Our pipeline works like this. We have a RGBD anchor image, IA, and a query image, IQ. Our goal is to find the relative rigid transformation that aligns the object's pose from anchor image to query image. Since our 3D models are scale normalized, we also estimate a scaling factor based on the anchor image to recover real-world size. Appearance can vary significantly between anchor and query images. To handle this, we focus on robust geometry features and reliable correspondences, ensuring accurate pose estimation across diverse and challenging scenarios. From a single RGBD image, first, we segment the anchor image to isolate the object. Then, we estimate a surface normal map using a pre-trained model. This map, combined with cropped image, guided our modified high-3D gene to generate high-fidelity textured 3D mesh. The resulting object-centric model is geometrically accurate and preserves fine details, forming the basis for alignment and real-world scaling. To ground our model in real world, the coarse-to-fine alignment module jointly estimates the object's metric scale and 60 pose from an anchor image. In the core stage, we render the object from multiple spherical viewpoints using camera intrinsics. Superpoint extracts features from both the renderings and a reference image. Then, superglue matches them. The rendering with the most matches is selected. Matched 2D points are left to 3D using depth and transformed into object normalized and camera coordinates. We then apply the PNP algorithm to estimate an initial 60 pose, though it lacks correct scale. To recover scale, we align the normalized 3D object points with their camera space counterparts, assuming they differ only by a global scale factor. We solve for this scale via least squares optimization. This gives a good initial pose and size. However, to improve accuracy, we refine both in the fan stage iteratively. Starting from the coarse estimate, we use a foundation pose-based network to predict small pose corrections. After each update, we re-estimate the scale using the same feature matching and optimization method as in the coarse stage. This loop, updating pose, then refining scale, repeating until the convergence or maximum iterations. The final output is a 3D object pose with accurate 60 alignment and real-world scale relative to the anchor image. Once we have the refined metric scale model, we can estimate the object's pose in new query images. Then, we compute the relative transformation using two absolute poses. Finally, to bridge the domain gap between generated models and real-world images, we introduce a task-guided generative augmentation strategy. We use Trellis, a task-guided 3D model, to generate diverse variations of an object from a single input, preserving its core shape, but varying textures and styles. We render these in blend proc with different veils, lighting, and occlusions to create a rich synthetic dataset. This trains our pose network to be more robust, especially for rare long-tail objects, and better handle texture changes and partial visibility. We evaluate our method without the proposed fine-tuning to ensure fairness. On 3 public datasets, a sharp increase can be seen in the table. We evaluate our method into real-world robotic tasks using 15 objects, 30 trails each. The first task was pick and place with X-hand from Roboterra, challenging due to heavy occlusion during grasp. The second was Dura manipulation involving picking, handover, and place phases with dynamic occlusions and object instability. Our method achieved a 17.3 success rate, outperforming SRT3D and DPAC, providing robust in complex occluded scenarios. Thanks all.
Okay, we have a question over there.
Thank you for your nice talk. And I'm wondering about how did you get the normal maps when you generated the 3D mesh, and why did you use the normal maps to guide the generation of the model?
During model generation, we use stable normal turbo as the normal map predictor. We use surface normals to get the 3D model generation because in certain viewpoints, partial information may be missing, and the normal map contain rich surface geometry cues that can achieve more accurate and robust 3D reconstruction in the following 60 pose estimation.
Thank you. Thank you very much.
Okay. Is there more question? Sorry, if there's anybody standing before the microphone and I don't see you, just wave. Okay.
Okay, thank you for sharing. Right. And I want to ask the benefits of using the loop to do the pose match, and how did you choose the initial pose?
Since the generated models model is based on the anchor image. Certain features of the model will closely align with the real object. Therefore, in the pose refinement and cost refinement step, only small pose adjustments are required. For the course alignment, we use 30 linear viewpoints, which represents a trade-off between speed and subsequent accuracy. Additionally, by incorporating fine alignment, leveraging existing models, we can achieve more accurate pose animation, therefore obtaining more precise correspondence for subsequent scale alignment.
Thank you.
Thanks.
All right, let's thank our speaker again. Can the next talk speaker come up? Okay. Awesome. All right, we have the speaker of FetchBot, and take it away.
Okay. Hi everyone, I'm Wei Heng Liu.
Hi, I'm Yushan Wan.
Today we are very glad to stand here to share our work, FetchBot, the generalizable artifact chain in CAS scenes via the short interview. So what is object fetching? Can you imagine one day when robots help store staff pick items from the shelves, assist chefs by trimming balls from kitchen cabinets, and hand us items from tabletops or drawers? Actually, all of these operations involve object fetching, which comprises three stages: reaching, grasping, and retrieval, with safety enforced throughout. In this paper, we achieve this by developing a fetching system that can generalize to diverse objects, scene layouts, and environments, whether the target is on shelf, on table, or in drawer. However, there are many challenges to achieve this. The first is a constrained workspace caused by obstacles and panels, which makes safe path planning difficult for the policy. In addition, these obstacles and panels introduce severe occlusion. It hinders the understanding of the scene and may cause important cues to be missed. And finally is scene diversity across object categories, scene layouts, and materials. This makes generalization very difficult. So how do we solve this? A natural first idea is motion planning, but it requires prior knowledge of object and the environment, which is very hard to get in the real world. Besides, motion planning usually assumes that a clean free path exists, but in many chaotic scenes, no such clean free path is available, and the best we can do is to minimize disturbance to the surrounding items. In recent years, learning-based methods have emerged as a feasible path to generalizable skill acquisition. But this raises another question. Data is hungry. Where does data come from? Compared to real-world data, synthetic data is more cost-effective, easier to scale, and safer to collect, but seem to get processes. Therefore, in this work, we propose FetchBot to address these all challenges. Our pipeline has two main components. The first is the generation of synthetic data, and the second is the distribution of a 3D variant policy that is symmetry-friendly. Let me first introduce the data generation first. Diverse synthetic data starts with diverse simulation scenes. We develop Univox a voxel-based scene generator that enables fast, scalable synthesis of diverse scenes. And in total, we generated 1 million chaotic scenes spanning shelf, tabletop, drawer, and storage rack environments. With the scenes ready, we need to collect demonstrations. We use reinforcement learning to do this. The policy takes full scene observations and low states as inputs. To represent the chaotic scenes efficiently, we model each object with key points. We then use a hierarchical scene encoder. A local network aggregates per-object features, and a global network captures the whole scene context. And our rewards fall into 3 categories. First, a task reward then drives the policy to successfully fetch a target. Second, a penalty for environmental impact during fetching, making behavior safer. Third, behavior constraints that ensure safe arming execution. After getting this policy, we use it to calculate 500K trajectories as demonstration, and this is the final performance of our policy in simulation.
Okay, I will continue to introduce our pipeline. So now we have a massive dataset of expert demonstrations. The critical next step is to distill this knowledge from our state-based IR policy into a purely version-based student policy. However, to do this successfully, we must overcome two fundamental challenges. The first one is symmetrical gap, and the second one is heavy occlusion. First, let's focus on the symmetrical challenge. I'd like to ask a question. Can a version policy trained on simulated RGB images transfer zero shot to reality? As you might expect, the answer is no. This approach is often not feasible without any significant adaptation. There is a huge domain gap. And especially for the texture gap, this is mainly caused by major difference in lightning, materials, and the shadows between simulation and reality. So our solution is to bypass the texture problem entirely. We use estimated depths as a unified intermediate representation, mapping both sim and real RGB images into a shared, purely geometric space. This dramatically narrows the symmetrical gap and serves as a cornerstone for achieving zero-shot transfer. Okay? However, estimated depth only solves the facial consistency problem. For character scenes, this reveals a more critical challenge. How do we handle heavy occlusion? As you can see, a depth map only shows the visible surface, offering no information about the occluded regions. Relying on such incomplete information is not only dangerous, but also makes it difficult for the policy to learn a correlation avoidance policy. Okay? Therefore, a natural idea emerges. We need to predict the occluded regions, because without that, the policy is difficult to generate safe and reliable actions. To address this, our solution is to introduce occupancy reconstruction as an auxiliary task to learn a more powerful 3D representation. As shown on the left, our shared version encoder generates a rich 3D feature, and which is then sent to two heads. The occupancy head reconstructs the local scene around the end effector. The purpose of this auxiliary task is to force the encoder to learn 3D spatial reasoning, resulting in a high-quality visual representation. And the action head then uses this powerful occupancy-trained representation to predict actions. As you can see on the right, with this occupancy prediction task, we can reconstruct occluded regions. Okay, here is the more real-world reconstruction results. Our method is highly effective. In simulation, its performance nearly reaches the upper bound of an Oracle policy that uses previous information. And in the real world, the estimated depth and occupancy allows our policy to achieve excellent performance, and this is zero shot. Okay, here are some demonstrations in the real world. Please notice that even with these unseen objects, including transparent and reflective ones, our policy can still generate correlation avoidance trajectories. Furthermore, our policy is robust to real-time dynamic obstacles. Here is a scenario that policy never encountered during its training in simulation, but it's worked very well. Okay, here are some takeaway messages from our work. First, more diverse and large datasets yield better performance. And second, foundation models are a powerful tool for sim2real. By using them to create a unified intermediate representation, we can effectively mitigate the domain gap. And finally, the auxiliary tasks that enforce 3D spatial reasoning, like occupancy prediction, directly improve the policy's ability to generate more better actions. Okay, that's all. Thank you.
Thank you. Can we have the presenter for next paper come up and while we take questions? Is there any question. I don't see anybody. Maybe I'm wrong. Okay, I have a question. So, it seems like you assume that a collision-free path exists for your task, correct? Yeah. Like you don't, for example, for settings where you need to move the object in front of the object to retrieve, those situations don't exist. Is that correct? And if so, how do you, I guess, extend your work to solve that problem?
Because we have assumption, and in our tasks, and there may be no collision-free path exists. Therefore, right now, what we need to do is to minimize the disturbance to the surrounding items. Just like we have, just like you said now, if there is one obstacle in front of the target, and we cannot directly reach the target and grasp the target and retrieve it. And in such cases, we don't have such cases in our task. What we want to have is that we have grasped the target, and what we need to do is to extract the target out and minimize the disturbance to surrounding items at the same time.
Got it. Thank you. Can we have the slides come up? Great. All right. We have the presenter of Savor.
Hi, everyone. I'm Rishabh, presenting this paper on behalf of my lab mate, Janshin Wu. I'm excited to introduce Savor, skill affordance learning from visual haptic perception for robot-assisted bite acquisition. Feeding is a key activity of daily living for people with mobility limitations. However, bite acquisition when feeding is challenging due to the complex interactions between utensils and foods with diverse physical properties. Besides the diverse food physical properties, utensil-food interactions are further complicated by the temporal variability of food properties. For example, chicken nuggets are soft enough to skewer with a plastic fork when they are warm, but after a few minutes, as they cool, they firm up, and the same skill no longer really works. Existing state-of-the-art approaches rely on category-based methods, which still fall short. For example, they choose skewering for all fruits and vegetables, regardless of the food's actual physical properties. Our key research question here is, how can robots reliably pick up food? Our key insight is that by understanding skill affordances, basically how suitable a skill is, like skewering or scooping, for a given utensil food interaction, the robot can enhance bite acquisition success across a wide range of foods. In our formulation, skill affordances arise from the combination of tool affordances, what a utensil can do, and food affordances, what the food allows. Tool affordances are learned through offline calibration, while food affordances are characterized by physical properties, which are initially estimated through common sense reasoning using a visually conditioned language model, and then dynamically refined during interaction through online visual haptic perception using SavorNet. SavorNet is a neural net that predicts physical food properties, softness, moisture, and viscosity from visual haptic perception. The goal of tool calibration is to provide the robot with contextual knowledge of the utensil's affordances. Prior to deployment, we perform offline calibration where different utensils interact with a variety of foods to evaluate their functional capabilities. We collect skill execution data on diverse food items annotated with food type, physical properties, and execution outcomes. And these affordances are represented in natural language and later used as input to the VLM-based planner GPT skill. During deployment, we initialize a food property estimate using only visual input. Given an RGB image, we prompt a VLM GPT property to estimate the physical properties of the food. Shape and size are represented as categorical descriptors in natural language, like bite size or round, and other properties are scalar values from 1 to 5, similar to a 5-point Likert scale. For example, a softness score of 1 would indicate very hard, while a score of 5 would indicate very soft. This estimate is then passed to the planner to select an appropriate manipulation skill. If the selected skill succeeds, we move on to the next food item. If it fails, we continue with subsequent attempts. In subsequent attempts, SaverNet takes online visual haptic perception and predicts food properties. If the confidence in the prediction exceeds the threshold, we define the food property estimate, and then GPT skill replans based on the updated state. If the new skill succeeds, we proceed to the next item. Otherwise, we continue attempting the task using the latest observations. Let's walk through an example here. Before deployment, we conduct tool calibration for 2 different utensils, plastic fork and metal fork. Now, let's begin deployment with the plastic fork as the example. Imagine eating chicken nuggets. From visual cues, the robot assumes the nuggets are soft enough to skewer, so it selects the skewering skill. And at first, it works perfectly fine. But as the nuggets cool, they firm up while still appearing the same visually. In subsequent attempts, it obviously fails, and visual haptic feedback detects this change. SaverNet then processes the online visual haptic signal and updates the food property estimate. GPT skill replans based on the refined state, and the robot then switches to scooping and is successfully able to pick up the chicken nugget. This example highlights the importance of combining tool capabilities, visual estimation of food properties, and continuous refinement through visual haptic perception. We evaluate on 10 unique dishes and 20 single food items. To quantify performance, we define SR1 as the proportion of items acquired within the first attempt in a meal. Similarly, we define SR2 and SR3 as the success rates within 2 and 3 attempts, respectively. For the low-level skills, we use the skill library from previous work, including 6 different skills: skewer, scoop, twirl, dip, cut, and push. We first look at the impact of offline tool calibration and figure out why do we exactly need it. We decided to test with 2 utensils, a plastic fork and a metal fork. As you can see, calibration significantly improves success rates. Without calibration, the system often chooses the wrong skill. For example, it might try to skewer a firm steak with a plastic fork, which almost always fails. The robot tends to overuse skewering regardless of context, leading to frequent failures. With calibration, though, the robot matches skills to utensil capabilities, skewering with the metal fork, scooping with the plastic fork, making bite acquisition much more reliable. Next, we evaluate Saver against several baselines, including haptic and vision ablations, and Saver achieves the highest success rate among all the baselines. End-to-end baseline takes the same input as Saver with lower success rate. This highlights the advantage of explicitly estimating the physical properties. Among all methods, only Saver and its variant without calibration achieves significant improvement from SR1 to SR2. By inferring food properties from utensil-food interaction, the system learns to adapt its skill in subsequent attempt. Now let's take a closer look at the benefits of visual haptic perception. The vision-only variant performs the worst with 60% SR3. It struggled to capture the subtle differences in utensil-food interaction. For example, strawberries, watermelon, and carrots, they all look roughly similar in color, but their physical properties are very different. The vision-only model often overestimates softness for firm items like carrot, which leads to skill selection failure. The haptic-only variant does better, reaching about 75% SR3, but it still falls short. Haptic alone struggles when food shares similar force signatures, such as soft cheese and avocado, making them hard to distinguish by touch. In these cases, small changes in pose can also cause rapid force spikes, either from skewering through soft foods and directly hitting the plate, or from utensil deformation against firm items. Without visual context, these noisy, ambiguous haptic signals are difficult to interpret correctly. By integrating vision and haptics, Saver resolves these ambiguities. These results highlight the critical role of visual haptic perception in accurately estimating food affordances. We also evaluate Saver on 20 single food items, including 10 that were unseen during SaverNet training. Saver outperforms SOTA baseline on both seen and unseen items, highlighting its strong personalization. The key takeaway is that interaction-driven skill affordance enables generalizable and effective robot-assisted bite acquisition. Please come to our poster session and check out the website for more details. And thank you for listening.
Thank you. Would you like to take question or?
I'm happy.
Okay, sounds good. Is there any question? Again, I can't really see, so if you just shout. So I have a question. So can you continuously update the Saver net based on the mistakes it makes? Or is it more like every time you have to make the same mistake in order to correct it?
So SaverNet is trained using an offline data set of different trajectories with differing food properties over time. So once we train it on that offline data, we don't really update the weights of the network. But because we have trained it on diverse food properties varying over time, it can actually figure out if the softness or the moisture level has changed over time. And it is able to predict different scores depending on the attempts.
Got it, yeah. Thank you. Let's thank our speaker again.
Thank you.
All right, can we have the slide come up? Okay, we have our speaker of reactive in-air clothing manipulation. Take it away.
Hi everyone, my name is Megha Kapoor, and today I'll be presenting our work carried out together with Neha Sunil, Arnaud Samal, Edward Adelson, and Alberto Rodriguez. So most prior cloth manipulation works rely on task-specific pipelines, like flattening, folding, dressing, or hanging, and typically use incremental pick-and-place motions on a tabletop placed in relatively simple, non-occluded states, often with rectangular cloth. Learning-based methods have shown to be quite successful at specific tasks, but rely on simulation, where the sim-to-real gap remains a challenge. Behavior cloning methods have also shown promising results on clothing tasks, but at the cost of large volumes of teleoperation data that may not generalize well. Our approach addresses some of these challenges with the reactive framework that adapts folding and hanging strategies of shirts of varying geometries. So our key contributions are custom simulated shirts with parameterized variations for correspondences across different shirt geometries, confidence-aware pixel-wise dense correspondence for shirts both crumpled on a table and suspended in air, a visuotactile grasp affordance network to find good grasp regions, and finally, a combined system incorporating correspondence, affordance, and tactile sensing for reactive, task-agnostic in-air garment manipulation, which can dynamically change folding strategies based on its confidence estimates. Later on, we'll also use this to hang a shirt on a peg. So starting with our simulated cloth model, we train our networks in simulation with a custom parameterized dataset generated in Blender. We randomize cloth material and dynamic properties and add realistic shirt features such as U-necks and V-necks, short and long sleeves, different collar lengths and depths, variations in the shirt bodice dimensions, diverse sets of shirt colors and textures, stitches, seams, and hems which provide crucial context under occlusion, and most importantly, scalable meshes to ensure each vertex maps to consistent points without the need for an intermediate skeleton. Our simulated dataset includes 3,000 hanging and 1,500 on-table scenes. Prior works have focused only on determining correspondences for on-table configurations, and so while our work extends correspondences to hanging shirts and unifies it across both settings. These cases often involve heavy occlusions where even a human would struggle to identify the features, further demonstrating the need for having a low confidence option. Now, moving on to the dense correspondence network, here we have a deformed shirt and a canonical shirt, and we want to learn pixel-wise correspondences between them. During training, we query a pixel on the deformed shirt, and we're able to get the corresponding pixel match in simulation. These images are input into the network, and the output of the network is the dense descriptor for the shirt, where every pixel is mapped to a d-dimensional embedding, capturing some notion of the location of the pixel with respect to the canonical shirt in the descriptor space. Traditionally, in prior works, these networks are trained with contrastive loss, where the loss is structured to decrease the distance between matches and descriptors and push non-matches farther apart. We, however, use a distributional loss where we have a target distribution that is a multimodal Gaussian with modes at symmetric match points. We obtain the probability estimator by taking the soft max over negative distances in descriptor space. Then we train the model by minimizing the difference between the target distribution and the probability estimate as measured by the KL divergence. This is important because we can encode symmetries and have built-in confidence estimates, which is very helpful for in-air garment manipulation. The network can query points on deformed shirts to obtain correspondence heat maps with respect to the canonical as in training. Conversely, in the inverse direction, we can query from the canonical to the deformed shirt, which is the direction we use during robot task execution. The grasp affordance network is first trained in simulation on 3,600 images to find good grasp regions for a hanging shirt using only side grasp from the robot arm. A depth image of the suspended shirt is provided as the network input, and a heat map showing graspable regions is output, with the red region showing where the robot arm can grasp. In Sim, we explicitly check criteria and assign affordance labels based on the side reachability by the robot, if the gripper will collide with any part of the fabric during the grasp attempt, or if we are grasping 2 layers of fabric or less, or accidentally grabbing more than that. However, because shirts in real life have a wider range of material dynamics than we are able to capture in Sim, we see issues with the sim-to-real transfer. To address the sim-to-real gap, we fine-tune on the robot with a tactile classifier supervising grasp success. We collect over 8,000 grasp attempts for fine-tuning, using simulated affordance predictions to guide the grasp selection and the classifier to supervise the outcomes. Moving on to the combined system, our framework begins by grasping the shirt from the table using dense correspondence and tactile sensing to check success. A second grasp in air is chosen with both high correspondence and affordance, and the tactile classifier again verifies grasp success. Once 2 successful grasps are made, the robot tensions the shirt via shear feedback from the tactile sensors, then either folds or hangs the shirt on a peg. In order for the robot to find a good grasp point, it needs to check for confidence. Here, it's checking for correspondence confidence and grasp affordance. If these 2 are both high enough, we attempt the grasp and only move on to the next step if the tactile classifier confirms it's successful. Otherwise, the arm rotates the shirt and tries again. So here's an example of the robot attempting a single in-air grasp using the combined system, and you can see that we queried the end of the sleeve, and as the robot rotates, it becomes more confident that it is indeed a sleeve, and we also get into a position where the affordance becomes high enough, allowing the robot to attempt the grasp and the classifier to tell us that it was successful. When we put this example in the larger context of folding, the state machine starts by grasping a single key point from the table. It checks for correspondence being in the robot's workspace and that the tactile classifier confirmed a successful grasp. If successful, the next grasp in air can be attempted, and if it's successful again, it can tension and fold. If we can't find good grasp on the table, then we pick a random point, and our first grasp is in air. We allow our network to dynamically choose between different folding strategies depending on which grasp it's most confident in. Once 2 points are successfully grasped, the robot can tension and fold the shirt. If a good grasp is not found or the cloth slips, the system returns to a fallback option and starts over. So here's a full example of the system progressing through the folding state machine, where we show the tactile classifier after grasping from the table. We found that the combined system successfully folded the shirt in 6 out of 10 trials, with failure modes being attributed to correspondence failures, grasp of too much fabric, and grabbing diagonally across the shirt. Across the 30 total grasps attempted over the trials, 6 were empty grasps, all that were correctly caught by the tactile classifier, triggering recovery behavior. In addition to folding, we can also use the same correspondence and affordance for hanging, this time looking for a shoulder or collar point on the table and looking for the collar in air. Then we bring the shirt over to a peg, pull down, and let go. The hanging system was successful in 7 out of the 10 trials, with all the failures due to correspondence errors. Lastly, beyond the tasks we've shown, we can use our dense representation for other planning modalities, such as learning from human video demonstrations of folding. Here, tracked hand gestures provide query points that map to canonical shirt locations via the same correspondence network used before, demonstrating how confidence-aware representation can provide a generalizable layer for higher-level planning frameworks for garment manipulation. Please visit our project website to see more of the demos and folding strategies on the different shirts, and I'm happy to take any questions now.
Great. Right, I can see.
This is very interesting because, as you mentioned, behavior cloning and different VLA models often use shirt folding or something like that as a demo. My question would be, if you were to use one of the different features you've learned from this work or different sensor modalities to augment VLA models, what would it be, and how do you see this coming together?
I think in that case, I think the high resolution of the gel site tactile sensors really came in handy, and there's a lot of future work that can be put into how we can do things like even sensing how much cloth we're grasping or what aspect of the cloth, like if we're grasping a zipper or the edge. We kind of tried some of that and didn't have too much luck, but I think that's definitely something that we can augment into VLA models later on.
Great. Let's thank our speaker again. Okay. Next, we have the presenter for Screw Splat.
Great. Hello, everyone. I'm Seung-Young Kim. Today, I'm presenting our work, Screw Splat on end-to-end method for articulated object recognition. Although we may not always notice, articulated objects are common in our daily lives, and being able to manipulate them is a very important skill. So our goal in this paper is to recognize both the 3D geometry and the underlying kinetic structure of articulated objects so that we can manipulate them efficiently. Specifically, from multi-view observations in different joint angles, our goal is to infer their particular, Our goal is to infer their particular geometries, joint axes and types without such relying on any category-specific supervision. So there have been several approaches to recognizing articulated objects, and most of them build on neural rendering-based 3D reconstruction methods, such as NURF or Gaussian splatting, which don't require such supervision. However, a key drawback of these methods lies in their reliance on strong assumptions, such as a known number of articulated components or predefined joint types. On top of that, these methods usually involve multi-stage pipelines with intermediate steps like point cloud matching or part clustering. This makes the system more complex, and it can also introduce more potential points to failure. Some of these methods also rely on depth input, but depth image is often noisier than RGB images, especially for transparent or reflective surfaces, which makes these methods less robust in real-world settings. In this paper, we introduce Screw Splat, a simple end-to-end approach for articulated object recognition. Our method requires no prior knowledge of joint types or counts, avoids such complex intermediate steps, and operates solely on RGB observations. Our key idea is simple. We use Gaussian splatting to represent the geometry, and we extended it with a screw model that gives us a continuous parameterization of joint axis. Briefly, Gaussian splatting represents a scene or object with a set of 3D Gaussians. Each Gaussian is defined by its pose, scale, opacity, and surface color. And these Gaussians are then optimized by minimizing a rendering loss. And once they are optimized, we can use them as a 3D representation of the object. Beyond that, screw theory gives us a natural way to describe screw motion, covering both leverage joints like a hinge and prismatic joints like a sliding drawer. A screw axis S can be represented as a 6-dimensional vector, and with the right constraints, this screw representation can capture both leveled and prismatic joints as follows. So, given a screw axis S and a joint angle theta, we can simply express the motion of a coordinate T along the screw axis simply using the matrix exponential. I will skip the detailed formulation for now. And with these two components, our first intuition behind the screw splat was very simple. Just like we splat Gaussians, we splat random screws to discover the joint axis of the articulated objects. With these, however, that's not enough for now. First, we need to figure out which part each Gaussian belongs to. And second, we need to pick out the meaningful screws among the among the all splatted screws. To tackle these 2 points, we introduced 2 additional variables. The first one is a part probability for each 3D Gaussian, telling us which part it belongs to. And second is a confidence value for each screw, telling us whether that screw is meaningful or not. This is the first point to remember about screw splat. The next natural question is, given a joint angle that theta k, which is also an optimization variable, how do we use these screws and additional variables to render an RGB image? The key idea in screw splat RGB rendering is straightforward. We take the Gaussians from each partial Gaussian primitive hi and replicate them and then assign them either to the static part, static base, or to one of the movable parts. This is the second takeaway to keep in mind about screw splat. So each partial Gaussian, we replicate as many Gaussians as the number of screw primitives plus 1. That extra 1 corresponds to the static part. So for a Gaussian assigned to the static base, we modify its opacity by scaling with the probability that it belongs to the base. And for the movable part, the pose is modified by the screw motion for a given joint angle. The opacity is also modified by scaling with the probability that the Gaussian belongs to the screw J, and also further modulated by the probability that screw J is meaningful. So using this rendering approach, we can jointly optimize the partial Gaussians, screw primitives, and the joint angles by minimizing the same rendering loss used in the original Gaussian splitting across the observations captured from different joint angles. So that's not all exactly. So however, if we only rely on rendering loss, we empirically observe that the model sometimes predicts the duplicated same axis or the same part twice or more. And in other times, some meaningless screws can be picked. For example, a screw may still have non-zero confidence, even though no any Gaussian is assigned to that screw. These issues significantly interrupt the optimization process. To handle this issue, we introduce a parsimony loss. It effectively removes the duplicated screws and meaningless ones. And this is the third and the final key idea of screw splat. Then we jointly optimize the weighted sum of the losses. So with this concept, screw splat is successfully optimized to recover the object's partial geometry and kinematic structure. So here are some qualitative results. Screw splat is able to recognize not only for objects with a single leveled joint, but also with a prismatic joint and even more complex cases with multiple joints that mix leveled and prismatic joints. Building on screw splat, we developed a simple but effective algorithm for manipulating articulate objects. Here's how it works. Given the object's current appearance and a text description of the current state and a target test prompt, we use click to search for a proper joint angle. The joint angle is chosen so that the rendered appearance matches the target prompt. So here's an example video of articulated object manipulation. In the recognition step, the robot first collects multi-view RGB images while a human manually adjusts the object into different joint angles. Then screw splat is optimized with these images. And when the object configuration changes, we can quickly estimate its current joint angles with the optimized screw splat model and current observation. So finally, we use the text prompt to determine the target joint angles and then execute the corresponding robot manipulation. So there are many more interesting topics discussed in our paper, and we invite you to take a close look. So thank you for listening, and I hope to discuss more on the poster session.
Great. Any questions? I don't. So do you, I can ask a question if there's no. Do you make assumptions about like for the image you capture how open the joints are? Like, is there a? I guess it cannot be fully closed. For example, the oven door cannot be fully closed, right?
Do you mean that we use
the images that you capture, like the state of the object that you capture? It seems, for example, for the laptop, it's like half open.
So exactly for optimizing, we used 5 configurations from
5 configurations, okay.
Open to close. And
I see. And then how? What will be the minimum view that you need to do this?
Yeah, that does not matter. So we use the random views and. Do you mean the joint
like,
angles?
Yeah, minimum number of like configurations.
Minimum numbers. We exactly tested on the 2 configurations, and we empirically found that the square split is to get show the great performance, so not only for 2 configurations.
Got it. Yeah. Thanks. Let's thank our speaker again. Great. We have our final paper, clutter desk graphs. Take it away.
Okay, hi. I'm here to represent our team to introduce you the clutter desk grasp, a sim-to-real system for general dexterous grasping in clutter scene. So why should we focus on this? So let's start with why grasping. So as you can see from these 3 videos, grasping is everywhere in daily life and is one of the most fundamental human skills. And why clutter scenes? As you can see from these 2 images, it's very common in daily life, and daily life scenes are complex and cluttered. So why dexterous hand instead of parallel gripper? Because dexterous hand offers higher dexterity, it has bigger potential, and it could also perform more stable grasping, as a lot of tools and objects are designed to fit human hand morphology. It could also easily leverage human data for policy learning. Okay, so let's look back to dexterous grasping in clutter scene. What it looks like. So we asked someone to show us. So in this video I'm gonna show, we asked this person to grasp the target object, the banana, which is deeply beneath here, beneath the clutter. So apart from being able to grasp diverse object and the diverse clutter scene, the actual dexterous grasping in clutter scene also involves rich interaction, where the human needs to actively interact with the clutter scenes to retrieve the deeply buried objects, and it should also be closed loop. So PriWorks has approached these challenges from 2 directions. One is grasp pose prediction with motion planning, another one is imitation learning. But as you can see from the left, the video from AnyDex grasp, even though it's very impressive, but there's no interaction here. And then if you look at this video from Dex grasp BLA, it's limited to sparse clutter scene, and also as imitation learning, it requires a lot of data for very robust performance. Another line of work is very popular in dexterous grasping is reinforcement learning, but this latest work is still limited to single object grasping. So here we introduce our work, the clutter desk grasp, which is able to grasp any objects, any novel objects in any novel clutter scenes, and it will interact with the clutter scene if needed, and it's also closed loop control. So it's just like how human grasps. Okay, so here is our pipeline, and I will also follow the Here Student framework, where we first train a teacher policy in simulation. And there are 2 main challenges. One is how to learn this human-like grasping behavior in clutter scenes. So it should be rich interaction, and it should be also strategic. Also, how to ensure the safety of such policy for sim-to-real deployment. To begin with, we introduce a novel clutter scene representation called geometry and spatial representation, which computes the distance from target objects and non-target objects from to the finger link, and then the objective will be to minimize the distance from target and then maximize distance from clutter. And this kind of distance-based representation is very computationally efficient. However, even with such representation, learning dexterous grasping in clutter scene remains very challenging. Therefore, we introduce clutter density curriculum, where we train a general single object grasping first, and then we fine-tune such policy in clutter scene to develop a strategic grasping behavior. But such policy also shows these kind of aggressive behaviors. As you can see from this video on the left-hand side, where red indicates excessive contact force. Therefore, we also introduce a safety curriculum, which gradually tighten the force threshold for episode termination and penalty. And then after this curriculum, effectively temper these kind of aggressive behaviors while preserving these human-like strategies developed in earlier stages. Okay, so now we have a very general and safe policy, teacher policy, and we need to deploy it in real world. So we did a student point cloud policy distillation. And there are two challenges here. So one is how to sim to real world with single side view camera and heavy occlusion. The second one is how to allow policy to adapt strategies to different level of clutter densities. So to address this, we collect demos in multi-level clutter scenes, both sparse and dense, to capture these different strategies. And then here's a visualization of the point cloud. And with this kind of observation, together with joint state, we collect a lot of rollout and then train the 3D diffusion policy with such demonstration. And then this 3D diffusion policy could be zero-shot real-world deployed. And to evaluate our policy, we did a lot of experiment in simulation where we test our policy on over 1,000 normal clutter scenes and over 2,000 unseen objects. And as you can see here, it generalized well to unseen objects and unseen layout with very high success rate. And we also test our policy in real world on 41 unseen objects and 17 unseen clutter scenes, which contains 167 attempts, with average success rate around 83.9%. Okay, and let's take a closer look of these kind of adaptive human-like behaviors. So in these two videos, the target object is this green box and is placed at the same place. And then for single object grasping, it will perform this direct grasping. And then for clutter scenes, it will reach from the side and then clear the clutter first, and then grasp from the side. And then there's no like specific mode switch here. It's just occurring naturally. And also our policy could be used for continuous grasp and transport. And for complete videos, you could refer to our website. And then we also deploy clutter desk grasp on a new embodiment with Franca and Inspire. And we modify the process slightly, and then we reach better closed loop control, and then it could also recover from human perturbation. So as you can see, human push the robot arm away from the target. And then it's also much faster. So here the video is not accelerated. And you can also come to our poster for clutter desk grasp working in diverse daily life scenario where we just deploy. And then here's the takeaway. So real-world dexterous grasping in clutter scenes can be enabled with good scene representation, curricular learning with safety awareness, and 3D diffusion policy with pure simulation demonstration. But we also have our limitations. So we lack diverse grasp pattern for functional grasping, and then tiny objects could be challenging for current perception system as we only use single camera. Okay, so please come to our poster for more detailed discussion, and check our website for more videos. Thank you.
Great. Is there any question for our last speaker? Very cool work. So do you think this method generalizes well to higher degree freedom hands, like 22, or like basically higher degree freedom hands?
Sorry, you mean higher?
Higher degree of freedom hands.
A high degree of freedom of hand. Yes, we are currently exploring like with higher degree of freedom of hand, and I think it can because there's no design in the pipeline that limits it to low degree of freedom hand.
Okay, great, awesome. Is there no more question? Okay, I think that concludes the session, and hope to see you in half an hour.
Is there any author for spotlight session? Then please come forward and please be there, front left. We are now waiting for many authors, so please hurry. There is only 1 minute left, so if there are any presenter for spotlight session, then please come to the left side over there. Yeah, you can see that the authors, they have badge on his left arm. So we are improved. Okay, it's time to start second spotlight session today. And then I believe almost of you already watched our first spotlight session, right? So this is our second episode. So during several hours later, we are training. So please watch our result of training. So let's welcome the first speaker.
All right, good afternoon. So evaluation is one of the trickiest parts of any robot learning project, especially in autonomous driving. So today I'll be presenting some of the work from our team on better evaluation for autonomous vehicles. All right, so basically you need to trade off two things in current benchmarks, especially academic benchmarks when you can't deploy a real car. Either you have scalability and efficiency, which you get with open loop evaluation, or you have reliability and actual closed loop performance measurement when you evaluate in simulation. But getting them both together is hard. So we have a way to do this. If you're curious how, come visit our poster. It's number 80 right in the front. Thanks.
Okay, it's okay. Let's give one more big hand.
Hello. Hello, my name is Bernhard Jäger. Our work tackles the task of privileged motion planning and autonomous driving with reinforcement learning. Prior approaches in this field have used complex shaped reward functions, which we empirically observe do not scale to large mini-batch sizes with on-policy learning. Instead, we are proposing to reward agents with only a single reward term, which is route completion, and model all constraints via terminal states of the environment. We observed that the resulting policy is now able to scale to large mini-batch sizes, which enable us to train the policy with much more data than before. The remaining RL policy outperforms other learning-based approaches, such as diffusion policies and transformers, while being 10 times faster at inference time. Thank you.
So dear everyone, we are glad to present our work on torque-aware vision language action models. As shown in the figure, even a simple task like charge insertion can end with no contact failure or success. Each clearly reflected in the torque profiles of a 7-dwarf arm. Similar variations appear in many texts, motivating us to study how torque signals can be interpreted into value models. We first compare architecture designs for adding torque. The Dupre architecture achieved the best results, which we confirmed through HSIC analysis and noise experiments. Next, we examine torque history embeddings. The denoising one token design performed best, thanks to stronger input alignment and pattern completeness. Finally, we introduced future torque prediction as an auxiliary objective. It both focuses signals accurately and improves overall task performance. We validate our findings through quantitative comparisons, as well as cross-model and cross-embodiment experiments, showing consistent gains. Thanks.
Hi everyone, I'm Alex and I'm presenting generalist robot manipulation beyond action labeled data. So we all know robot foundation models need many robot demos. What if we could also use human demos for training? We present MotoVLA. MotoVLA learns a joint 3D action space between different robot embodiments and the human hand. And we do this via point clouds at the end effector. We extract point clouds from 2D videos by lifting 2D tracks to 3D using monocular depth estimators. And then we train a model to predict future point clouds in the first stage. In the second stage, we align the model to predict robot actions by training on a smaller action-labeled dataset. Here are some rollouts of tasks unseen during action alignment. So here's a human demo, and then here's a corresponding rollout of a robot. Thank you, and if you have any questions, please come to poster 30.
Yep, there is no author.
In this work, we propose a novel paradigm named CDP, which leverages causal diffusion to achieve robust autoregressive visual motor policy learning. When performing the task of grabbing the barrier in practice, the quality of observations is degraded by factors such as sensor noise, occlusions, and hardware limitations. In this case, the robot is unable to perform accurate manipulation. In this paper, we address historical action sequences to introduce temporally rich context as a supplement, which enables more robust policy generation. We systematically evaluate our CDP on a broad spectrum of manipulation tasks from RoboFactory, Adroit, DexArt and MetaWorld, covering gripper and dexterous hands, articulated and rigid objects, and single and multi-agent settings is shown in the table. The figure shows that the success rate of DP3 declines precipitously as noise grows, whereas our method maintains consistently high performance. We then present real-world task demonstrations produced by CDP. Consistent with the simulation results, these experiments achieve high success rates across all tasks even when the policy is trained on only 50 demonstrations.
Hi, I'm Siddhant, and I'll be presenting our work called Point Policy, where we learn robot policies directly from human videos without any robot demonstrations. Our method generalizes to novel object instances. Is robust to background distractors. You can see me, moving in the scene, changing the background. And is also robust to heavy scene variations, for example, heavy changes in lighting conditions. Yeah, we call this point policy, and we basically achieve zero-shot human-to-robot transfer using these key point-based representations. To know more about this, come find me at poster 17. Thank you.
Hello everyone, my name is Hao Yishong. Your bimanual arms might need a robot neck, and here's why. Your bimanual arms might need a robot neck, and here's why. Okay. Consider a task of retrieving an object inside a bag. You may first localize the bag, open the bag with one arm, and then pick inside to find the target object. Such a realistic setting often requires active camera moving, which motivates us to design a robot neck. In this work, we present vision in action. VIA is an active perception system that incorporates a 3D teleportation interface and a sextop active neck. VIA learns a range of active perceptual strategies directly from human demonstration, such as searching around for the target object, looking closer to focus on the task-relevant part, and bending down to find a better camera viewpoint. Please visit our website and come to our pro session at the first floor. Thank you.
Hello, my name is Aidan Curtis, and I'll be presenting our work on partially observable world model learning. So decision-making under partial observability is a central challenge in robotics and AI, and a partially observable decision-making process can provide a principled framework for reasoning about such problems. It consists of a transition function, reward function, observation model, and initial state distribution. Many recent works have explored generating code as models for different downstream policy extraction methods. Some examples include learning constraint graphs for constraint satisfaction, learning reward models for RL, or learning MDPs for planning. Our method basically constructs models for each of the 4 components of a POMDP, and since these are stochastic models, we need to represent them as probabilistic programs. So we make use of both online and offline data to learn these models. We experimented with a number of different classical POMDP problems as well as toy mini-grid problems. And lastly, experimented on a larger object search problem on a real robot. Thank you.
Okay, we present ManyFlow, a general robot manipulation policy via consistency flow training. So ManyFlow demonstrates strong generalization, like over multiple tasks and setups, including bimanual and humanoid configurations. And our policy is built on an expressive DIT transformer and enhanced with consistent training and that support multimodal data. And here, DITX support enables rich token-level interactions, and while the flow consistency enforces stable mapping from noisy samples to target distribution. And we evaluated our ManyFlow on 4 benchmarks, and it consistently outperformed diffusion and flow matching policies. And also, ManyFlow also suppresses pi0 on 4 robustness tests, and yeah, and it also like demonstrates superior scaling capabilities. Yeah, okay, thank you.
Hello. We address the problem of assisting decisions for agents with partial observability. To efficiently assist other PAM-DP agents, an agent needs to evaluate their value function. And it turns out that this is impractical in real time when the assisted agent performs online planning and replans at every step. We propose several heuristics to estimate the value difference due to assistive actions. And we found out that for the helper's decision making, estimating value in a relaxed deterministic version of the environment is both efficient and reliable. And we demonstrated this approach on this collaborative manipulation task, where one robot can assist another by moving obstacles to improve visibility and accessibility.
Hello. So in this work, we have proposed to use a preview action with curriculum learning to learn the long horizon robot manipulation skills. This can help learn the skills without the requirement of the reward engineering or reference trajectory. So the preview action includes constraint realization and virtual forces. So it helps the robot to learn to grasp the object with ungraspables without any indication for the non-prehensile manipulation. And also, when the initial push to grasp fails or not achievable in the environment, it can alternatively export out the pivot grasp to finish the task. So in summary, our framework can extensively help to increase the exploration efficiency of the policy. It helps to learn the long horizon counter-reaching manipulation tasks without under the sparse reward, and also it helps to explore out a variety of different skills with the same reward function. Thank you.
Hi, I'm James, here to present our work, FOMO 3D. Self-driving vehicles need to detect many types of traffic participants. Long-tail classes are especially challenging due to limited training data. And we use vision foundation models to tackle this problem. Vision foundation models generalize exceptionally well to rare objects. In this work, we leverage OWL for 2D detection and metric 3D for depth estimation. To perform 3D object detection, FOMO 3D uses novel multimodal fusion strategies to exploit prior knowledge from these models in conjunction with processing LiDAR inputs. On the nuisance benchmark, our model outperforms SOTA on both common and rare classes. Please visit us at our poster session for more details. Thank you.
Hi everyone, I'm Miles. We are presenting Neural Robot Dynamics, or NERD for short. NERD models learn the forward dynamics of a specific articulation under different environmental configurations. Once we've learned our dynamics model, we can use them to train policies, and they show good long-term prediction accuracy over 1,000 time steps when compared to a ground truth simulator. Nerd models generalize, so we can use the same dynamics model for multiple tasks, such as the sidestep motion shown here. And the core idea of our method is that we replace the solver in a traditional simulation pipeline with a learned model based on a transformer. We feed in the output of contact generation and collision detection into the model, and it predicts the state at the next time step. With our learned model, we can do things like fine-tuning on real-world data and observations. So if you'd like to learn more, please come to the poster. Thank you.
Hi, this is Jerry, and this is BV Calib, LiDAR camera calibration with BV Features. So have you also been frustrated with calibration before? Have you also been frustrated with calibration before, whether it's setting up the tedious process or searching for a good open source tool? Many of us have experienced this process before. Target-based methods use checkerboards or targets to align LiDAR and cameras, but require careful setup. Targetless methods instead use motion cues or learning-based approaches to learn and align sensors more robustly, which is what BV Calib follows. BV has demonstrated robustness and good performance on tasks here, so can BV also work in calibration? Here's our methodology. It's a two-tower approach with a calibration decoder transformer head. Here are our results. Across 3 different data sets of Kitty, NewScenes, and CalibDB, our internal indoor data set. As you can see, BV Calib outperforms all the other current state or open source methods. Here are some qualitative results. As you can see, BV Calib closely matches with the ground truth, while the other 3 methods are either very far away or very close to ground truth. If you're interested, please check us out. Here's our webpage code and model.
We will be presenting today with the following title in a poster 87. Imagine the language instruction, stop next to pedestrian, as shown in this image. Based on such instruction, our model predicts target region as green field. Our model, GenNav, covers single and no and merge target scenarios, which reproduce real-world scenarios. And our model, GenNav, achieved 10 times faster than baseline method, and it also surpassed in accuracy, as shown in these figures. We also conducted real-world experiment, as we will show in next slide. This result shows a great zero-shot performance of our model. If you have interested, please come by poster 87. Thank you.
Hello everyone, I'm Janan. We present reflective planning. Complex multi-stage manipulation tasks remain a fundamental challenge in robotics. And vision language models are promising candidates for robotic planning problems given their remarkable capabilities in processing visual information and natural language instructions by leveraging internet scale knowledge. However, as you see in the example, VLMs still struggle with long horizon reasoning and may hallucinate physically implausible solutions. To address these challenges, we present a framework that incorporates VLMs with reflective planning. Our method uses a VLM to propose actions and a diffusion dynamics model to imagine the future outcomes. The imagined future helps the VLM to reflect on its initial decisions and propose better actions. Our methods outperform state-of-the-art VLMs and model-based planning approaches such as MCTS. For more details, please check our posters right after this. Thank you.
Hello, everyone. In this study, we ask a simple question. Can large language model modelers to generalize to an autonomous driving framework? And we found that some modelers can be transferred and others need some adaptation. For example, we designed a tokenizer with a small motion vocabulary, and we found that our motion vocabulary can work well. And for another person embedding, and we found that with a proper person embedding, we can help the model understand the space well. And during pre-training, we observe the scaling law with the increasing of data size and model parameters. And we also introduced GRPO to reinforce the model to generate safe and human-like trajectories. And we sample and cluster trajectories to ensure the diversity. And here we will show some demos from Waymo open data sites, and more details can be found in our poster. And you can find our poster in desk 77. Thank you.
Hello everyone, please let me introduce Articulate AnyMesh to you. The main goal of Articulate AnyMesh is to convert meshes into their articulated counterparts in an open vocabulary manner. This allows us to avoid being limited by existing data sets and to preserve the geometry and appearance of high-quality meshes to the greatest extent possible. Given meshes from different sources, we first perform 3D segmentation. Then, we let a VLM reason based on some geometric clues to infer the joint axes and other articulation parameters of the parts. Finally, for surface-only meshes, we add a final step using a generative model for shape completion and texture generation. By generating the input mesh with a 3D generation model, our pipeline can perform open vocabulary articulated object generation. For application, Articulate AnyMesh can provide more diverse object data for policy learning.
Hi everyone, my name is Benjamin, and together with my co-author, we developed a junction state estimation algorithm, and we call it DORS, or Door of S, because it characterizes gateways in an environment, while also characterizes dead ends and centrality of states in the state space. How we do it? We simply compute an average entropy of the state occupancy distribution for multiple horizons. This allows us to kind of capture the varying time dynamics. And our results show that, for example, in point maze environments, this promotes high velocity movements, while in robot manipulation tasks, it accelerates downstream learning compared to some other baseline methods. For example, empowerment is kind of related to all this. Please visit us at the poster stand 64. Thank you.
Hello, I am Gloria, and this is Human-like Navigation in a World Built for Humans. It's easy to get lost in a building you've never been to before. That's what signs are made for. But current robot systems don't know how to leverage this information. Thus, we present human-like navigation in a world built for humans, equipping mobile robots with the ability to read navigational signs, reason about room number patterns, and even ask people for directions.
I am a delivery robot. Do you know where room 4322 is?
Yes, it's the last door on your right.
Sounds good, thanks.
With VLM-powered landmark selection, our method is able to efficiently find the goal, spending less time and traveling less distance. We achieve success in both real-world scenarios and our custom simulation environment. Please visit poster number 2 for more insight into our work. Thank you.
Hi, my name is Michael Amir, and I'll introduce Recode, a method for learning dynamic constraints to improve coordination in multi-agent systems. In Recode, instead of outputting actions, policies output constraints on the actions agents are allowed to perform. And this is inspired by human traffic laws, where rules require us to drive on the right-hand side or on the left-hand side help improve congestion and avoid accidents. When put on top of an existing expert controller, Recode enables those controllers to solve things they wouldn't be able to. Like here, where robots are trying to navigate to the top while being chained together. Or here, where robots must swap position and they spontaneously learn a kind of left-hand, right-hand rule to enable them to actually do so, kind of like human drivers do. Recode outperforms state-of-the-art offline and online methods, and it is significantly more sample efficient than end-to-end multi-agent reinforcement learning, thanks to the existing expert controller that helps scaffold it. It retains interpretability and safety guarantees, and yeah, please come to poster number 9 if you are interested in hearing more. Thank you.
Hi everyone, I'm going to introduce our work on off-policy Lyapunov stability in reinforcement learning. So Lyapunov functions give us the ability to provide stability guarantees to learn policies, but the Lyapunov function is dependent on the Lie derivative along the trajectory of the system. What this means is that most of the work in learning Lyapunov functions is done in model-based systems, with some recent work being done in model-free environments using on-policy data. Our method proposes, we propose a method that uses a model-free environment using off-policy data, which provides sample efficiency improvements, as well as maintaining the same stability characteristics. If you're interested, please come to poster 85. Thank you.
Hi, I'm Junan, and I'll be presenting our work, Uncertainty-Aware Latent Safety Filters for Avoiding Out-of-Distribution Failures. So word models allow us to encode hard-to-model safety constraints such as Jenga blocks falling and prevent them by synthesizing a latent safety filter using HA reachability analysis. However, there are countless ways that robots can fail, and no dataset can capture them all. So word models hallucinate in these out-of-distribution scenarios, failing to prevent unseen failure modes. So our research question is, how can robots avoid both known and unseen failures? Our key insight is to use the word model's epistemic uncertainty as a proxy for identifying unseen failure modes. We detect out-of-distribution word model predictions by quantifying epistemic uncertainty and calibrating a threshold with conformal prediction. We then augment the safety specification with these OD failures, enabling an uncertainty-aware safety filter to prevent both known and unseen failures. If you'd like to learn more about our work, please visit our poster number 8. Thank you.
Hi, my name is Shalin, and I'm a master's student at Georgia Tech. For multi-robot RL researchers, existing platforms tend to force a trade-off between optimization for multi-agent learning, robotics relevance, and open access sim-to-real capability. Multi-agent RL benchmarks are highly optimized but low fidelity, while robotics simulators are high fidelity but are not optimized for multi-robot learning and do not provide open access sim-to-real capability. JAX Robotarium unifies the computational efficiency of JAX with multi-robot learning and open access sim-to-real on the Robotarium. We first build a safety-aware simulator in JAX and a learning interface to integrate with multi-agent RL frameworks. We then design 8 benchmark coordination tasks and provide a pipeline for real-world deployment. We find that JAX Robotarium is 150 times faster in simulation, cutting training time from 3 hours to 10 minutes. And the support for large-scale sim-to-real evaluation enables us to study the gap caused by inter-agent interactions. Thank you, and come to poster 12 to learn more.
Hey everyone, I'm Tongshan. I'm happy to introduce unique closed-diff diffusion dynamics model with generative state estimation for closed manipulation. So we first address the challenging problem of estimating closed state using a diffusion-based perception model. The diffusion perception model is conditioned on point cloud observation and generates the closed state of template mesh in canonical space. Then we address the problem of modeling dynamics as the action condition generation process. We integrate our perception model and dynamics model with model predictive control and use cross-entropy method to solve the optimization. Our whole system is able to complete single-step and long-horizon closed manipulation tasks and generalize well across different embodiments and within object classes. Check more details on our website. Thank you.
Yeah, I think they didn't prepare sound. But I think that you feel that we are improved, right? So our previous training was very successful. But I'm not sure tomorrow. Because every life, it is like that. Maybe authors will prepare you in the first floor in post-session.
Hi everyone, I'm Izhuo. I'll present CogniPlan, uncertainty guided path planning with conditional generative layout prediction. So when human plan paths, our brain will typically construct a cognitive map that supports spatial reasoning, memory call, and forward planning. So in light of this, we propose CogniPlan, a path planning framework that leverages the synergy between conditional generative layout in painting and graph attention-based planning to enable both point-goal navigation and autonomous exploration in unknown environments. So we first train an in-painting generator given the ground truth layout type vector, and then we freeze the generator to train the downstream planner using deep reinforcement learning. We benchmark CogniPlan across a variety set of experiment and data sets in different environments and also on hardware. So feel free to visit our poster number 7. Thank you so much.
Hello everyone, I'm here to introduce our recent work on morphologically symmetric reinforcement learning. So our human body is inherently bilateral symmetric, so this allows us to mirror some simple actions very easily. However, when it comes to some fine dexterous tasks, we usually use our dominant side, which is called handedness. So one interesting observation is that for most of the current robot designs, such as bimanual systems or humanoids, they all feature such bilateral symmetry. So one natural question to ask is, can we achieve ambidextrous manipulation? In other words, once we learn how to do it on one side, can we simply transfer it to the other side? So here we introduce SymDex. The key idea is to incorporate these morphological symmetries in both architecture and algorithmic. So we evaluate our methods on 6 challenging bimanual dexterous manipulation tasks in both simulation and also the real world. In addition, we verify our methods that we can easily extend to multi-arm setup with more complex symmetry groups. Thank you.
Train once, plan anywhere. Kinodynamic motion planning via diffusion trees. Thinking about kinodynamic motion planning or low-level control, we have 2 main approaches currently. One is the classical approach, sampling-based planners, which use random actions to span a search tree. They have structured, scalable search, but are inefficient in their exploration. So, like most classical algorithms. From the learning side, we have diffusion planners, which sample from the distribution of expert trajectories. They perform highly efficient planning, but lack generalization and safety. We present diffusion trees, or in short, D-trees. These algorithms keep the tree structure from the classical approaches, but use diffusion policies to sample new actions. These actions are validated and only then inserted into the tree, maintaining safety. After training only a single map, our framework preserves generalization, provides collision-free trajectories, superior success rates, and a proof of probabilistic completeness and asymptotic optimality. Please visit us at poster number 50. Thank you.
Hi, I'm Alexis. I'm here to present force modulated visual policy for robot-assisted dressing with arm motions, a system that handles visual occlusions while adapting robustly to diverse natural arm motions. Large-scale simulation is good for generalization across diverse body shapes, poses, and garments. However, current simulators struggle with realistic force modeling for garments, limiting adaptation to arm motions under partial observability. To address this, we propose fine-tuning a simulation pre-trained vision policy on limited real-world data with multimodal feedback from vision and force. We first train a point cloud-based policy in simulation across diverse garments, poses, and body sizes, within fine-tuning on a small set of real-world multimodal data, introducing force-modulated visual policy. By conditioning latent visual features on force inputs, FMVP adapts effectively to arm motions. For more information and complete results, please visit our poster at number 89. Thank you.
Hi, I'm Suyang. Thank you for watching our presentation on sub-teaming and adaptive formation control for coordinated multi-robot navigation. During the coordinated navigation, robot teams are often required to maintain formation. However, rigidly maintaining formation is infeasible in complex scenarios. Therefore, we enable a new multi-robot navigation capability of sub-team division, formation adaptation, and team recovery. To enable this capability, we propose a unified hierarchical learning framework, including high-level deep graph cut for team splitting, intermediate-level graph learning for sub-teams coordination, and lower-level robot control. To validate our approach, we conducted extensive experiments in both indoor and outdoor environments using simulation and physical robot teams. Experimental results show that our approach enabled a novel capability of sub-teaming and adaptive formation control. Thank you for listening, and please visit our poster number 3.
Hello, this is Pierre presenting the Asimov benchmark. So how do we ensure that robots behave well in the real world? So to answer that, we need 2 things. One, we need to test behavior in undesirable situations, but most real-world data is boring, so we use image generation to augment it, turning safe scenes into risky ones. It's like giving robots nightmares, a virtual rehearsal for rare but dangerous events. From these augmented scenarios, we built a massive multimodal Q&A benchmark with 500,000 contexts, 3 million instructions to check does robot know what's safe and what's not. Second, we need a way to specify behavior. From the same real-world augmentations, we generate robot constitutions, interpretable high-level rules that guide robots, and most importantly, that humans can edit. The result is that we increased alignment with humans from 58% to 84% using generated and auto-amended robot constitutions, beating human written rules and holding up even under adversarial attacks. So our poster is number 10. Thank you.
Hi, I'm Anjali, and my work is on cost-aware discovery of contextual failures. Existing methods for failure discovery rely on assumptions that real-world robotic systems often do not meet. For example, it is not possible to conduct thousands of experiments on real robotic systems or describe all failures using well-defined cost functions. In this work, we propose a sample-efficient failure discovery method that uses expert feedback to design diverse failure scenarios relevant to the user. We do this using coverage-based Bayesian active learning pipeline. At each step, we optimize coverage across all failure modes and sequentially propose better candidates for experimentation. We validate our method across several robotic falsification tasks in manipulation and self-driving. Come check out our poster at poster 79 by the lobby for more details. Thank you.
Great. Wow.
Hi everyone. Today I'll present Long Range Navigator. So in this work we asked the question, how can robots make long horizon navigation decisions with no prior maps and using only local sensors? Traditional stacks make use of fixed range metric maps which are limited by sparse depth and compute. To compensate, outside the map they rely on engineered heuristics like head towards the goal to select intermediate goals, but these can end up becoming myopic. So our key insight is that a robot can reason further by identifying distant, affordable intermediate goals. We propose LRN, which is a learned mapping from visual information to affordable frontiers. With LRN, robots can leverage visual information to identify affordable frontiers for long-range navigation, and by doing so, Spot in this example can avoid the wall and reach the goal efficiently. Thank you, and come by our poster, poster number 6.
Hello, my name is Nicholas, and I'm here to present our work on steerable scene generation. Robot foundation models need large interaction data sets, but collecting them in the real world alone is slow, costly, and hard to scale. We focus on scene generation by generating realistic, task-relevant, and physically feasible simulation environments. We enable scalable raw data collection inside simulation. We take a two-step strategy. First, pre-train on broad procedural data. Then, steer generation toward downstream objective We explore three strategies: reinforcement learning post-training, conditioning, and the novel inference time Monte Carlo research strategy over partial scenes. The result is physically feasible, task-relevant simulation environments that are ready for our data collection inside simulation and also, of course, for evaluation. To learn more, please find us at our poster, number 62, in the lobby.
Hello, my name is Donggi. I'm excited to present our work on the Enter the Mind Palace. Humans interact with dynamically changing environments over days and months, building an understanding of them. To enable robots with the same capability, we propose a robotic memory bank, approach for handling long-term data accumulated over periods. As an example, consider the task of asking a robot to find a letter that can be used to change light bulbs. Our approach allows the robot to search temporal data efficiently over days and months, analyze trends to infer where the letter is most likely located, use a new planning algorithm to search the current large environment effectively based on these trends, and as a robot explores and gathers new information, it continuously updates the memory bank. Through this process, robots can achieve more robust, human-like reasoning in dynamic environments, solving lots of practical tasks. Thanks for listening.
Hi everyone, my name is Blake and I'll be talking about our work GraphEQA. Embodied question answering in unseen environments is a challenging task, requiring an agent to both explore using common sense knowledge of human environments, as well as ground its actions in the current context in order to confidently answer a situated question. It is therefore essential to maintain a concise memory to take grounded actions in the environment. We introduced GraphEQA, a framework that utilizes real-time 3D scene graphs and task-relevant images as multimodal memory for grounding a VLM-based hierarchical planner to perform EQA tasks in unseen environments. We evaluate GraphEQA on 2 benchmark datasets and in the real world in 2 environments. GraphEQA outperforms key baselines, achieving the highest success rates and lowest planning steps. Our results also show that scene graph grounding mitigates VLM overconfidence, and building a concise incremental memory is especially beneficial for long horizon tasks in large environments. Please come visit us at poster 66 for more information. Thank you.
Hi everyone, my name is Wei. Today I'll be presenting our work called DEXplore that learns dexterous manipulation skills from human demonstrations. Despite advances in human object interaction research providing valuable motion capture data, directly applying this data to robot hands is still very challenging due to the embodiment gap. We propose a unified single-loop optimization for dexterous hand control, learned from human motion capture data. It uses reinforcement learning with demonstrations as soft guidance. These avoid retargeting error and preserving human intent and overcoming traditional multi-stage overflow limitations. The learned policy is then distilled into a vision-based policy for the real-world deployment. For more details, please visit poster 21. Thank you.
Hi, my name is Henny, and I'm excited to present our work on using world models for embodied open vocabulary object localization. Humans explore unseen environments intelligently, using prior knowledge to actively seek information under partial observation. Can we teach robots to do the same? Introducing WOMAP, World Models for Active Perception, a novel framework for embodied open vocabulary object localization that combines the reasoning power of VLMs with the physical grounding capability of world models. We generate data using novel rendered views from Gaussian splats, trains a reconstruction-free world model from dense object detection rewards, and uses it to evaluate and refine VLM action proposals at inference time. WOMAP consistently outperforms the baselines in simulation and hardware experiments on challenging tabletop search tasks, and demonstrates zero-shot generalization to novel task conditions like lighting, distractors, unseen objects, and language queries. Please check out our poster at number 15. Thank you.
Hi, I'm James, and I'm presenting our paper on runtime learning. Here we want to answer two questions in our work. One is, what is the most useful and informative data? And two is, how can we quickly learn a policy when pre-training is impossible? To that end, we propose a runtime learning pipeline based upon Koopman theory. Take this example here of a simulated two-link arm following a reference trajectory. Our method, RKL, has better performance than many RL benchmarks with using up to 750 times less data. We also show how with very limited demonstrations, online updates are critical for learning at all. Finally, let's consider a soft robot doing a dynamic balancing task. This is a setting where pre-training or simulations may be in fact impossible, and so learning in real time is critical. We achieve up to 50 times faster learning when compared to RL benchmarks. Stop by poster 84 if you're interested in learning more. Thank you very much for listening.
Hi, my name is Anuj. My co-authors and I built a system that allows robot arms to lift heavy objects. Broadly, we do this using a diffusion-based trajectory generation system that obeys both kinematic and dynamic constraints. Our system exhibits low constant planning times with low variance, generates diverse multimodal trajectories to solve this problem, and demonstrates the potential to learn from the failures of multiple imperfect planners. We evaluate on a bunch of controlled and real-world objects. Obviously, our planner demonstrates good performance for sub-nominal payloads, as well as super-nominal payloads, showing that our system can maintain up to 67% of the robot's reachable space at up to 3x the payload capacity of the robot. We also show a bunch of quantitative comparisons, so come check out poster 71. Thanks.
Hi everyone, my name is Chris, and today I'm presenting Cupid. So, robot imitation learning policies are trained via supervised learning on offline data. Therefore, issues with the quality of the training data can adversely affect your policy's performance, resulting in low precision behaviors, brittle strategies, and even ignoring of task-relevant objects during execution. But what constitutes high-quality training data to begin with? In this work, we argue that high-quality training data is none other than the data that drives your policy's downstream closed-loop performance. We first introduce a technique that estimates each demonstration's contribution to performance by predicting counterfactual questions such as how would my policy's performance change if I added a new demo or removed an existing demo from the training set. We resolve these questions using a data attribution technique based on influence functions. We then leverage these performance estimates to automatically curate data towards filtering low quality behaviors, promoting robust strategies, and even disentangling spurious correlations, resulting in improved policy performance across the board despite using significantly less training data. Please come see me at poster 44. Thank you.
Aligning robot behavior with human preferences is crucial for deploying embodied AI agents in human-centered environments. A promising solution is interactive imitation learning from human intervention, where a human expert observes the policy's execution and provides interventions as feedback. However, existing methods often fail to utilize the prior policy efficiently to facilitate learning, thus hindering sample efficiency. In this work, we introduce Merrick, designed for sample-efficient alignment from human intervention. Instead of inferring the complete human behavior characteristics, Merrick infers a residual reward function that captures the discrepancy between the human experts and the prior policy's underlying reward functions. Residual Q-learning is then employed to align the policy with human preferences using the inferred reward function. Extensive evaluations on simulated and real-world tasks show that Merrick achieves sample-efficient alignment from human intervention compared to baselines. For more details, please check our paper and website. Thanks for watching.
Hi, I'm Scott. I'll talk about FLAIR on behalf of Ruijie Zhang and Jing Wang and other co-authors. FLAIR is robot learning with implicit representation alignment. So FLAIR is a simple modification on top of a flow matching policy where you align the representation of the DIT with the embedding of a future state. And we see that it robustly improves performance on simulation benchmarks and also on the real GR1 in our lab across a variety of manipulation benchmarks. Also, because it doesn't rely on having actions, you can co-train with human data. And we observe that co-training with human data with FLAIR improves the success rate on manipulating novel objects. If you want to learn more about FLAIR, come to poster 39. Thank you.
Hi, we present RoboMonkey, a framework for synthetic data generation and test time scaling for vision language action models. Our work first characterizes the test time scaling laws for VLAs. We find that action error consistently decreases across multiple sampling approaches as we generate more candidate actions. But this is computed relative to the ground truth action data. So how can we capitalize on these inference time scaling laws? We propose RoboMonkey, a two-stage framework. In the first stage, given a robotics data set, we construct synthetic action preferences based on the RMSE between actions sampled from a policy and the ground truth actions. We then fine-tune a VLM-based verifier on this synthetic data. At deployment, we sample a batch of actions, apply Gaussian perturbations to generate more candidate actions, and then use the VLM-based verifier to select the optimal action. We find that RoboMonkey effectively mitigates issues of imprecise grasping and task progression failures across simpler, real-world, and literal benchmarks. Please come see me at poster 48 to learn more.
Hi, I'm Jiang Ran. We introduce low-star, long-horizon dexterity via synthetic data augmentation from human demonstrations. In this work, we explore to learn robust long-horizon dexterity from a few human demonstrations using data augmentation data. We propose low-star, a system for automatic skill decomposition on synthetic data generation from human demonstrations for long-horizon dexterity. We evaluate our methods on three challenging real-world tasks: planning watering, light pulp, assembly, and liquid handling. We use only 15 demonstrations for each. Low-star consistently and significantly outperforms all baselines on all tasks. Thanks for watching.
Hi, my name is Yizhong Lin. I will introduce our work SimShare, Sim-to-Real Share-based Tactile Sewing. And here is our main framework. In the first part of our method, we have the share pix-to-pix, which is a conditional UNet GAN that translates simulated tactile images with share vectors into generated real tactile images. And the second part of our method, we have the share net, which is a Gaussian density neural networks that translates, that generates real tactile images. That predicts both contact poles and the share vectors based on the previous generated real tactile images. And we validate our methods on two share-oriented robotic tasks, which shows that our method can be transferred to the real world effectively. And if you're interested in our works, please come to poster 81. Thank you.
This is Rust. He waiting for more than 1 hour. Let's big hand.
Good afternoon, everyone. I'm Yutang, and I'm going to present Clone, a closed-loop whole-body humanoid teleoperation system. And Clone combines an MOE policy with closed-loop error correction, and it can execute long-horizon tasks while maintaining coordination with only minimal inputs from an MR headset. And by correcting the drift in real time, our system can deliver unprecedented tracking fidelity comparing with the traditional open-loop methods. And this allows the operators to drive the humanoids in an effective way with only hand-in-hand motions to perform tasks under an unstructured real-world environment. And Clone also enables a real-time teleoperation for diverse whole body skills, including carrying boxes, squatting, pick from the ground, wipe the whiteboard, and even boxing if you happen to have 2G1s and not afraid of breaking them. And welcome to our poster. It's number 65, and thank you, everyone.
Thank you very much, especially for attendance, because you make this session very special and impressive together. And then every paper is waiting for you on the first floor in post session. So please enjoy post session, and then please be here because today we will have welcome reception. The rain outside, so you cannot escape from here. So let's enjoy together. Thank you.